yellow color. So can you go to the next slide? This is the jet core, but animation, please. So as you move to 7th night or 8th, so this is a 6-hourly gap, as you know, HMWF wind product actually. So you get a trough, penetrating towards extreme North India. So this is, I think, 8:0 UTC. Next, can you go? So this is, as you know, that we have around 7 model, basic model, global model. So we have a UK Metafish, that unified model, which runs at our Noida center. We have a GFS, the NCEP part, which runs at our IIT in Pune. So we have our 2 global model. We are the center in Asia after, I think, Japan or China, having 2 global model runs 2 times. 0 UTC and 12 UTC at 12 kilometer resolution. So that is fantastic. Then we have also ensemble prediction system for both income and GFS. So that is our own model. Besides that, we refer ECMWF, as I was showing, also NCEP GFS and also JMA. So that is our basic things. Then we have our multi-model ensemble, particularly for rainfall and temperature. So that table shows what is that location over Delhi. If you take latitude, longitude, we take a airport actually, the city airport, Safdarjung. So that is the variation of next 7 days, covering maximum minimum temperature, wind condition, and rainfall. So, and also in the right side, you can see 8th, you are getting precipitation. If you see, so you see actually some rain in the right on the 8th. So based on this trend, why the model, as you know, that biased correction also we carry out, because actual prediction of the model surface parameters are very, very biased actually. Next. So that MME takes care of bias correction and also all models into consideration. Next slide. So this is very interesting that like ECMWF, wherever you click to get the meteorogram. So we have our system where we have a click, just give your, click, then you get the meteorogram. Not only for GFS, but we have taken all integrated, all the model meteorogram integrated into our system that we call Monsoon gram actually. Our objective is to get the meteorogram at each location. So that also shows some rainfall you can see. Even if you go for MME, you get some rainfall, that right yellow color. Next. So the forecast, as I was telling, that western disturbance likely to affect from 7th night. And initially it will give the Himalayan hills some light, moderate rain snow. Gradually on 8th, as I was showing, it will cause some precipitation, light rainfall adjoining plains. So Delhi has some chance. And regarding the fog condition, as you have seen, that we have very strong wind prevailing because ahead of the western disturbance. So that shows that happens actually. You get, previous slide, please. Previous. No, previous that, please. So this is the summary actually, the inference is that this is the western disturbance. Today the wind is like this, and the wind will continue to be strong till tomorrow morning. Thereafter from also 6th and 7th, thereafter from 8th, because of the easterly wind, because western disturbance, so circulation, easterly wind, so there will be moisture from the Bay of Bengal, so high humidity. So all things will be down. Your humidity will be high, your pollution will be high because you get higher moisture, higher pollution, and wind speed is getting 0 because of that western. So from 8th, you will get clouding, shallow to moderate fog, and also poor air quality. And maybe cloudy or light drizzle in parts of NCR Delhi, extreme north. Next. So that I was telling. Next. So that we are giving, you can see that we are increasing the minimum temperature from 7, 8 to onward. Next. Yeah. Next, please. So this is the air quality we have given. Next. Thank you.
Thank you, sir, for the weather briefing. Next, we are going to start the first session of today, small sat, CubeSat for meteorology, climate, and environmental monitoring. The first speaker of today's session is Mr. Shaikh Dargah Shaib. The topic is the influence of Indian monsoon phases on aerosol distribution and composition over India. Please come, sir.
Oh, thank you, ma'am. Yeah. Myself, Sheikh Dargah Sahib, project scientist at Indian Meteorological Department, Bangalore, MC Bangalore. So today is the influences of Indian monsoon phases on aerosol distributions and composition over Indian region. So this work under in collaboration with a National Atmospheric Research Laboratory, ISRO, Tirupati. Is it work? Yeah. So I will actually I will start with 1 or 2 slides in introduction, then comes to the results what I have found out. So if you see the right hand figure in the topmost, this is the when you see the on the top of the atmosphere in the clean environment over the Bangladesh and West Bengals. So in the typical days in the winter, this is the in the lower figure we see the fog is formed. That means some type of aerosols are formed in the atmosphere. By the definition, we called as the solid and liquid particles suspended in the atmosphere. We called as the aerosols. Aerosol is the big term. That is the ranges from the 0.01 micrometers to 100 micrometers. So and the number density is the typically found is the 10 to 10 to the power of 7 particle per centimeters cube. This will be the standards. This varying from the region to region. And the lifetime of the aerosols is also in the atmosphere is from hours to weeks. Actually, in average, we are spending the 1 week in the lifetime of the aerosols in the atmosphere. And there are different types of aerosols are present in the atmosphere. One is in the sea salt and mineral dust and black carbon. There are different. The size is also different. We exist. So based on that, we are predicting the interaction with the aerosols in the environment is very difficult to predict. So why we need to study the aerosols means actually this is basic slide. So that means the air quality and human health, the trade in the air quality and human health, and visibility reduction. This is the main. And agriculture is also impacting the agriculture productivity. And the atmosphere once the aerosols are entered into the atmosphere, the chemistry will also change, and cloud formation will alter the cloud formation, cloud SCC and cloud effect, and finally it comes to the radiative forcing, climate radiative forcing from the aerosols. So in that, actually we have see the from the based on that we took the aerosol products from the MODIS in the climate data. So distributing in the sizes seasonal distribution over the Indian region. So first we see the inter and pre-monsoon months and monsoon and post-monsoon, how the spatial distribution is evolving around the seasonal basis. So the MODIS is capture the seasonal variations. In the winter, we are getting the low aerosol values over the Indian region, and in the pre-monsoon, we are getting the high aerosol over Indian region. So in the post-monsoon and pre-monsoon winter, we are high GP is highlighted in the high, is always in the all the seasons, IGP is getting the high aerosol AOD values. That means high aerosol present in the Indian IGP region. So from we are also validating with the ground MODIS AOD with the ground observations. So based on the aeronet data and RF network observations, we are find out the correlation is finding with the R square is the 0.9 over the Indian region. This is in the daily mean we are taking. So from move to the actually we have seen the how the active days and break days varying the aerosols over the Indian region. So we have segregated the AOD over the active days and break days. So it is observed that active days the AOD is lower as compared to the break days. So that means in the break days the evolution is accumulated the aerosols over the Indian region. So particularly in the IGP, it is very high in the IGP. It's almost all around in the 1 AOD values we are finding. And next we see the how it is aerosol composition. It's varying from the active days and break days. So the Calypso is we are observing the from the long term data we are saying from 2006 to 2020 we segregated the active days and break days. So it is observed that the break days is a high aerosol loading. That means high extension values we are getting from surface to up to 5 kilometers. And also segregated the water, 7 type of aerosol types we segregated based on the standard model only from the Calypso. So polluted dust is the dominated in the active days and break days. So polluted dust in the active days we are seeing the 25%, and the break days we have in break phase we are seeing the 43% in the during the break days. That means in the elevated smoke is also observed during the active phase season. So why it is coming from the elevated smoke? It is during the active phase. So from that we have see the ice split trajectory model. Back trajectories we have tracked in the from 2010 to 2020. Sorry, 2006 to 2020. So that means 6% of black trajectories coming from the inland area from east side. So that's why we are getting the active phase season in the black carbon means what we call elevated smoke we are getting from the from there. So now we segregated in the strong days and strong monsoon season and weak monsoon years we have find out. So in strong monsoon season, a high AOD we are observed in the Indian region as compared to the weak monsoon season. The difference is high. From strong to weak is the central India. We are finding the differences high in the central India. So and also we try to same thing. So how it is the aerosol variable decomposition during the strong monsoon and weak monsoons. So there is no that much of a that means significantly we are not observing any during the strong and weak monsoons. But even though the small things are there, then the dust is dominated in the over the Indian region. So the almost 70% of in the dust is observed from the weak monsoon and strong monsoon years. So that means actually this is a overall cumulative monsoon season. So my conclusion summary is, so over the Indian region, aerosol distribution exhibits a different seasons for that different between the active and break days and strong and weak monsoon seasons. And higher AOD is showing the strong monsoon as particularly in the central India region. So distinct aerosol types are observed over the Indian region during the break and active monsoon season. No significant aerosol types are observed. That means significant. Some small things are there, but no significance are during the strong and weak monsoon years. Thank you.
I have time for a quick question if anyone would like to.
You showed that the AOD was very high over the IGP during the active phase of the monsoon. So you how can you just explain the physical mechanism, because during the rain there will be scavenging effect and the aerosol concentration should be less.
But in all the regions we are not in the single rainfall is occurred. So the accumulated one reason is rainfall occurred, but even though their transported winds is very high in that during the monsoon season. So they have transported to other seasons.
So dust aerosols are dominating?
Yeah, dust results are dominating.
Thank you.
Yeah,
Yeah.
nice work. But one of the slide you have shown that northern India, which is Punjab, Haryana,
Yes, yes.
the AOD is high during monsoon,
Yeah.
whereas it's very low during this December, January, February.
Yes.
But we see this opposite. During monsoon season, it should be
Actually, this is based on the MODIS data, sir. So in that, in the air, some small type of cloud is also taking as a CCN, cloud condensation nuclei. That also taking as a AOD as the in algorithms. So maybe that is the reason also one of the
maybe
we are
you
getting
can
high in the monsoon region.
maybe you can try monthly because December, January, February. So if you just see monthly, maybe December month you will find high AOD over this region. Otherwise, it
December,
looks contrary to what we see.
December month we are getting only black carbon things, sir. Smoke aerosols.
Okay.
Fog and due to the fog and these things. So December months we are getting the high in the IGP region. Rest of the things are in low only.
So this is one aspect.
Anyway, always in the IGP is in the high aerosol prone area.
This is one aspect you have seen seeing impact of monsoon on aerosol. But what about other way around? Impact of aerosol loading on monsoon.
This,
Have you seen that?
Yeah, this is the first. Sorry. Yeah, I have seen, sir. Yeah. During the monsoon is also high aerosol observed in the our Indian region. So because of winds is coming from the ocean side to from western side to the lot of dust is coming from the western regions to from Indian. Okay, thank you.
Questions for the speaker? There's always the coffee break. Our next speaker is Fujian Wang. Not seeing Fujian coming up to the podium, so we're going to move to Niti Singh. Okay. Give the title.
Yeah, good morning, everyone. Myself, Niti Singh. I am presenting my topic utilizing radio sound observation INSAT 3DR satellite wind index evolution in relation to weather regimes over Indian region. So I have taken the wind indices, that is the INSAT 3DR geostationary satellite product. So in every 45 minutes, we are getting this product, and L2B data I have taken for processing the wind indices. In here in one line, I want to say what is the wind index. It is the maximum possible wind gust that could occur in a thunderstorm. So what I'm doing here, then this indices I have validated with the radio sound wind indices. So the major contribution is here. The radio sound wind indices is still not calculated. So I have calculated this radio sound wind indices, and then we have validated with the INSAT 3DR wind indices. So daily the radio sound ascent, total 56 station from India, we have doing the ascent. So we have validated this data with this radio sound data. So once it is validated, then the obvious INSAT 3DR satellite spatial distribution is more. So we can get a more data via INSAT 3DR satellite. in this indices, this is a better indication for thunderstorm event. So before 3-4 hours, we will get the one indication that some phenomena is going to occur. And then this product is very, very helpful for aviation and the small aircraft and for the aviation user. So based on this product, aviation's user, they can take the decision before 3-4 hours. Either they can suspend the helicopter operation, or the forecasting they can do is there is some indication is there. Now, in detail, I want to say what is the wind index. Wind index is the potential of air masses available over the area at a particular instant of time, which can cause sudden downpour or microburst. Like the other indices, lifting index, it shows the upper this one. And the wind indices define the maximum possible convective wind gust that could occur in thunderstorm. So wind index is the suitable to estimate the gust strength in the severe local storm, such as thunderstorm, but not organized storms such as a cyclone. So in the later on, I will show the example also कि in cyclone, in other phenomena, we cannot capture this indices. So McKinnon in 1994, he has studied about the wind indices, and based on the observed and the model microburst, it designed to help forecast the microburst wind gust potential. And Pyron in 2004, he also defined the wind index is more sensitive to a lower temperature lapse rate, and it is a measure of downdrift instability, making wind index a better local microburst potential index than the other instability indices such as lifting index or K index or other. So the wind index measures the downdrift instability, whereas the lifting index shows the updrift instability. So this is the two major difference. If we will know the wind indices value, we can know how much the downdrift instability is there. And then it will be very helpful to define the thunderstorm phenomena. So microbursts are the small scale phenomena, and it is very difficult to predict. However, the sufficient knowledge of microburst evaluation can be applied to meso scale to provide some warning to public and as well as the aviation. So based on these indices, this is a very helpful product for the pilots to take the decision. Now I will show how in our INSET 3DR algorithm, they have calculated this wind index. The same formula I have taken to calculate this indices for radio sound. So here, the HM is the melting level height in kilometer, and G is the lapse rate. So lapse rate is the rate which temperature changes with the height in the atmosphere. And QL is the mixing ratio in 1 kilometer above the surface. And QM is the mixing ratio at the melting level. And based on this, we have calculated the RQ. And in this formula, I have put all the value, and then I have calculated the wind indexes. So this is the detailed flow chart ki how we are calculating that reaching the pressure level at the which the temperature reaches 0 degrees centigrade, and based on the interpretation method and other method we have applied, and finally we have find out the wind indices value. So this is the table where it shows that radio sound indices all the value we are getting. But here we are getting the in every pressure level, height, temperature, dew point, freezing point, mixing level, and the other value. Based on this radio sound value, we have calculated this wind indices, and this data is available on Vyoming websites also. So once we have validated this product, easily by INSET 3DR product, we can utilize it. And then the further RMSE, bias, correlation, everything is calculated. And we have find out that radio sound wind indices is overestimated compared to the INSET 3DR. And then we have taken the few case study. One case study is taken for Delhi NCR thunderstorm squall cases they have taken. And there we have find out the wind speed is the greater than 45 kT before the 3-4 hours of the event. Then the second case study I have taken for Patna airport. There the helicopter operation is suspended, and we have collected the data for 27th May 2021. And that time also the wind index value was the 30, and the visibility also dropped to the 1200. Further, this data is compared with the wind speed value also. So what we have find out, always the wind index value is the higher than the wind speed value, and that is also 30 times. It means the 5 times it will be higher than the wind speed value. So this is also one good indication. And then I have taken the 3 years data, 2020, 21, and 22, and I have taken the radiosonde data and as well as the INSAT 3DR data. And then we have categorized in the different category, like less than 10, 10 to 49, 49 to 79, and greater than 79. So most of the cases I have found in 10 to 49 cases. And in 2021, it is the 456 cases was there. And 2020, it is the 750 cases there. Now, I have taken the recent cyclone, that is the Fangal cyclone, that was in 30th November 2024, 1 week before. That time I have observed the wind index value. It was not shown. It is in Tamil Nadu and Kerala side, this cyclone was there, but the no wind index value was the captured here. And then below is shown the wind speed is also here, approximate 30 kT, 25 kT wind speed is there. But why no wind index is captured? Because this is the continuous phenomena. Once the sky is there, once the cloud is there, we cannot capture this phenomena. So this phenomena is very, very helpful for thunderstorm type of the events when it start the initial stage. And once the cloud formation is done and the sequential, the cloud is there, then we are not going to get this wind index value. And here this product study, so many persons, they have shown in rapid also. So this product is available in rapid also. So we can take the time series analysis also. So if you want to make a graph from last 6 hours, 7 hours, so that also we can make it here. And the same cyclone time, that this is the observed rain value. So that was more than 1000 mm, but this is also indication that this cyclone and the rain is also high, but the no wind index value was captured. So this is a clear indication once the cloud formation is there and the sequential phenomena is there, we are not going to get this value. This is only the indication for thunderstorm, and that also before the 3-4 hours. Then we have done the sensitivity analysis also, and other thunderstorm cases study also done here. Now I will come for the result discussion. So what finally we have find out here, that validation results show the radiosonde wind index is overestimated compared to the INSAT 3DR wind index. And wind index is always 3 to 4 times more than the wind speed. Then thunderstorm case analysis is done, and it shows before 3-4 hours, thunderstorm wind index values goes higher side compared to the normal condition. The lapse rate between the surface and the melting level is the most important atmospheric variable in wind index. Low wind index value result from the low level lapse rate and the relativity stability. And finally, this allow our forecaster to monitor how changes in the surface parameter that affect the wind index gust potential value. And this work emphasized the wind index accuracy for helicopter operation. However, the wind index information is derived by satellite, but always missing by the radiosonde. So that also we have calculated. And this proposed method is applied to estimating the radiosonde wind index, and the continuous, we are doing this testing, and we have collected the data from last 3 years, and the current data also we are collecting. Whenever some helicopter suspension or lower aircraft suspension is there, that time whatever the situation that we are analyzing, and the next work I'm going to propose that also. So then we are going to make this one most important indices for aviation related and aviation users. Thank you everyone.
Would anyone like to ask a question?
Ma'am, good morning. Since you said that this can be useful for especially helicopter operations, so let's say if I have a situation, day starts, we have some operations. So how we are gonna use this, because we have to continuously monitor this when the sky is clear, or when because when we have to launch some operations, we have to continuously monitor this thing on a rapid platform, or what we are supposed to do?
Yeah. We have to observe, and once suppose it is starting indicating, so it always give the indication 3-4 hours before. So 3-4 hours before, if we will say to our airport and the airline operators, they can avoid that route and they can follow some other route. So in that case, we can save lots of fuel and the economy also. So that analysis we are also doing. And one more, I have included danger associated with microburst and how pilots respond to them. So pilots are trained to react by increasing. If suppose some pilot, they are entered in that type of the situation. So there also they can increase the engine power, adjusting their flight path and taking over evasive maneuver to avoid the strong downdrift involved. So first, if they are getting the indication, better they can avoid that route and they can plan according that. And this is the.
Thank you. Again, if there are further questions, meet up during the coffee break. Our next speaker is online. He's supposed to be online. Mitchell Goldberg will be joining online from the City College of New York. He's formerly chief scientist for JPSS. Very famous. He's more famous than Alan.
Oh, no, I wouldn't say that. I think you're more famous. So anyway,
we can hear you, Mitch.
Okay, good. And I guess I will share the presentation. Is that correct?
Yes.
Okay, so let me get there. Hopefully, okay, so do you see my presentation?
I see a white screen.
Do you see letters?
No, I just see a white background.
Let me, I must be doing something incorrectly. And I will, okay, let me display Microsoft and PowerPoint. How about now? No, I have white screen. You see anything?
White screen.
Yeah, I see the white screen too. Let's see. Can someone, I did email my presentation. Can someone show that? Let's see. I will keep on trying. Let's see, what's wrong with this? Share. Okay, share my screen. Okay, I'm gonna. How about now? Oh,
I see Niagara Falls.
let's see what happens when I do this. How about now?
Still Niagara Falls. Want to share his?
That's kind of strange. I don't know where Niagara Falls is coming from. I know where it's coming from, but it's okay, so can someone
Can you share his presentation on the screen? I believe they're working on it.
Okay, let me keep on trying this. This is kind of odd. So what I'll do is I'll start giving my presentation and you can use your imagination. So anyway, I retired from NOAA last year, actually May of last year, 2023. And I have a new position. I'm a professor at City College in New York, working on atmospheric soundings, a lot of microwave and infrared soundings, and focusing on new things. So I'm focusing on the use of CubeSats, for example, to build out a microwave constellation, focusing on the application of CubeSats.
Which if I can interrupt, can you please give access to, you should have a message to give access to aomsuc14@gmail.com if you can give them access to your presentation.
Okay. Let's see. Oh, I see. Anyone with link. Done. Okay, now you should have access.
So it should be coming up shortly, and I'll just mention that Mitch will be talking about tropics, and I like to show off that I know what the tropics stands for. Time-resolved observations of precipitation intensity from a constellation of small sats. So we're talking small sats and microwave observations from those.
Exactly. And the interesting thing about tropics, it's basically a NASA-funded research mission, and it's being commercialized by a company called Tomorrow.io, and they plan to have a constellation of about 18 satellites. And with 18 satellites, these are CubeSats, you can stitch the data together and have temporal resolution of like 30 minutes global. So we're excited about that. So you can imagine a lot of nowcasting applications, looking at imagery. But before you can look at imagery from a constellation, you have to angle adjust, and that's called limb adjustment, basically making everything look like nadir. And oh, good, perfect. I see my screen. Okay, so if you can, just click on that one full. Okay, so that's the slide I'm on. Okay, so the nice thing is if you have a constellation and you do these limb adjustments, you can actually, they'll become seamless, and it will be not quite geostationary, but it will give something. It will give good information about monitoring atmospheric rivers, monitoring tropical storms, and things like that. And it can also be used in data assimilation, of course. So if we go to slide 3, the next slide, and I'm going to, did you move to the next slide? Oh, okay, good, because I can actually see, I have a little window that shows the slides, at the meeting room. So microwave imagery, as you know, is widely used by forecasters, and we love microwave imagery. I mean, one can say that we like it better than infrared imagery or visible imagery, perhaps, because visible and infrared imagery has issues with clouds and things like that. And this was a slide that we developed to promote why AMSTER 2 is really, really important, because it covers that, afternoon, early afternoon. And the thing that we don't like about microwave imagery is that it's just not enough. The temporal resolution is not good. So if you go to the next slide, this is imagery from tropics. On the right, you have on the left, so you have two different storms. On the left is from JPSS, 183 gigahertz channels. Tropics has a special new channel, 205 gigahertz, and so it's more sensitive to ice particles, and you can see more intensity associated with heavy precipitation. So that's pretty impressive. So again, if you imagine just having a large constellation. Okay, let's go to the next slide, and that will show the evolution, right? This just did not happen, 10 years ago, 20 years ago. It's a recent evolution from experiments first funded by NASA into now commercialization all the way to the end, Tomorrow.io. And there's another company called OMS that you see in the third to the left, where it says temperature only. That's also, they're also planning on putting together a constellation. And I'm still supporting NESDIS, NOAA, and NOAA has purchased or in the process of purchasing some microwave, commercial data from Tomorrow.io and OMS. to evaluate its applications. You know, how good are these new data sets? How important are they in applications? So I'm supporting the NESIS team by doing these type of studies. Okay, so next slide is the just before and after, right? Picture's worth 1,000 words. So if you didn't do any correction at all, limb adjustment correction, you would have the upper panel, so you can see the effects of you know, the different orbits. Oh, I should say tropics is in a low inclination orbit. And so it's basically like a trim orbit. So it's basically plus or minus about 37.5 degrees. And at the lower, you can see the limb adjustment, and then you can see features, right? So you can see atmospheric rivers and things like that. And the Tomorrow I/O constellation, which is going to be about 18, will be a mixture of polar orbiting orbits as well as these low inclination orbits. So why do we adjust? Next slide, please. So I think it's obvious. You know, imagery, especially water vapor imagery, are used routinely by forecasters to track flow and transport of moisture. And microwave water vapor channels have that advantage of much less cloud contamination. However, the temporal refresh is poor. I already said that. So now we have a constellation or beginning of a constellation that needs to be corrected and so forth. So that's important of a limb adjustment. Next slide, please. This is just the weighting functions of tropics. On the left are temperature, on the right is water vapor. A lot of the applications are being focused on the water vapor channels because that has the really additional important information that's needed for monitoring atmospheric rivers and tropical cyclones. Next slide. Next slide is basically, I think you have to click. Now there's a little button on the lower left, I think, that might animate this of the figure. But basically it shows that it shows that the weighting functions do change as a function of viewing geometry. And what we're doing is adjusting them. Okay, so I see you're on slide 10. This is just a nice picture of geostationary upper tropospheric water vapor, which we're all familiar with. If you go to the next slide, slide 11, this is a snapshot of tropics on left side without the limb adjustment, with the limb adjusted on the bottom. You can see the features are more details, and you can look carefully. The features match nicely with the geostationary. Next slide is that's also an animation. The only way you can animate is if you click in the lower, if you use your mouse and you click in the lower part, lower left of that image, there's a little movie button. So I don't know if you found that, but if not, that's okay. So unfortunately, the animations are really important to show. But anyway, this slide basically shows if it was animating, go back for a second, slide 13. If you were animating this, it would basically be these like spaghetti ribbons, and it would be every hour it would be moving along, and you can actually see beautiful animation. Especially there's a tropical cyclone at the bottom. You can see this is the daily composite at the bottom, and you see this tropical cyclone, not tropical cyclone, some low pressure system east of Japan, and that basically you can see the motion based on just a few of these in orbit. So we're excited about that. Okay, next slide is slide 14. We basically adjust weighting functions at nadir to look like, adjust weighting functions not at nadir. So on the left is 64 degrees zenith angle, which is pretty far out there. And we just adjust it to nadir. We fit the weighting functions based on these papers I wrote many, many years ago. Next slide is, and also, it's also a little bit of an animation, but it's a two-step method where we adjust for the weighting functions, fitting weighting functions. And then also, but we use the real data too to adjust for instrument artifacts. So that's an important stage. Okay, the next slide, and I'm almost done. This is just a picture of channel 6, temperature channel that has the biggest limb effect before and after. So you can see how nice the limb adjustment works. And if you're averaging data, next slide number, the next one, you got to limit just if you're averaging data. You just get nonsense, obviously. So this is the top slide is if you just average over a month. The bottom slide is if you limit just and average. Okay, slide 18 is basically, the next slide is just the limit adjustment. One slide more, next slide, is the limit adjustment of every single channel. Just show you an example of that. So it actually looks very, very good. The next slide is that we're looking at, more quantitative analysis of observed minus simulated using ERA5, building these tools. And if you go to the next slide, slide 20, the next one, we're looking at also another important question, especially with data simulation, is because you have to quantify, data simulation, you got to get everything right. And so we're looking at differences between satellites now. So this is difference of, we're screening out the precipitation. This is channel 11 in the middle. And so that's in the middle is real data. The bottom is simulated data from ECMWF. So it compares quite well. The next slide 21, is basically the difference now between measured and simulated. Let's see. And then if you keep on going on, this is now the difference between two different satellites. And that's where we get into these G6 double differencing techniques, where you look at differences between measured versus computed, or satellite versus satellite, but you have to take into account the time of day difference, which is huge with these satellites, and you get this double difference. Let's see. So where are we? Okay. So, I'm sorry. So this slide basically shows that the one that is on display, that it basically shows the difference between measured versus the two different satellites of real data. And at the bottom is a map of the mean hour from the two different satellites, two different CubeSats. So they're very, very different. The next slide, so you expect differences. The next slide is basically now simulated minus simulated, taking into account the time of day based using ECMWF. And then the next slide after that is the double difference. And so when you look at the double difference, if you go back one slide, I'll make my point that if you take, you see how close these two different satellites look really similar after you do the double difference, which is important. So again, that's going to be a major effort of intercalibrating all these satellites. Next slide basically tells a story about that. I don't have to limit just to nadir. I can limit just at different viewing geometry. And then if I do that, I sort of get the bottom curve where I'm getting many, many layers of the atmosphere. So we can actually create very, very simple imagery. And so the next slide, this one, basically shows if you only limit just to nadir, you basically get just the right panel, 4 channels. But now I multiplied by 3, and you're getting more layers. And if you look at the next slide here, it looks like you are providing more information. This is like a vertical cross section along longitude, and you can see that you're getting more details on the right through this limit adjustment to different angles. So the last slide is a summary. So the data looks very, very good. This is a new area, a new frontier of using these small sats along with these reference instruments. So having something like ATMS as a backbone is really, really important. The limit adjustment enables us to have a lot of different imagery applications. We are working with forecasters in the US to get feedback of how they can use this data. I just gave a presentation to them just a few weeks ago. And we're going to do more comparisons. And thank you very much.
Thank you, Mitch. Are there any questions? We have one question.
Thank you for the presentation. there are really exciting possibilities with all these constellations coming up. What I was interested in is, are we also going to get channels 35 gigahertz and 89 gigahertz or somewhere near to them, because that we use for monitoring of tropical cyclones. And also the second point, how fast we will be able to get the data. So the revisit time will be increased with constellation, but once the scan is done, how fast we will be going to get the data. Thank you.
Yeah, in terms of the latency, they are working on that and they're hoping to get the data within 30 minutes. That's their goal. In terms of the lower frequency channels, you would need a big antenna and you just can't do that with CubeSats. But that's 200 gigahertz channels, that the new one is pretty impressive. So and I think that's really a key channel that will be used for imagery. And I think it will rival those other, the traditional channels. So yes, thank you for your question. And
Thank you, Mitch.
sorry
We're
for
out
the
of questions.
difficulty.
We're running out
Sorry
of
for the
time.
technical
So
difficulty. So anyway, have a great meeting. Sorry I couldn't be there, and wish you the very best. And it sounds like it's going so well. Thank you.
thank you, Mitch. Our next speaker is the title of the next talk, as we wrap up, is Spatio-Temporal Variability Analysis of the Solar Energy Resources of Sustainable Energy Application using INSAT 3D Dataset.
Good morning, everyone. The topic of my presentation is spatio-temporal variability analysis of solar energy resources for sustainable energy applications using INSAT 3D dataset. So in this, basically, I have taken a product of INSAT 3D, which is GHI, Global Horizontal Irradiance. It is used to estimate how much solar potential an area has. So I carried out this study for 3 years. 2021, 2022, 2023. These are the results. These are the month-wise visualization of the GHI data. Initially, in the month of January, the southern India has more radiation as compared to the North India, and as the sun moves northwards, the GHI values increases. As the red color indicates higher GHI values, yellow color indicates lesser, and green indicates even less. So that was 2021. This is 2022 and 2023. So we can get a rough idea that from this, that GHI values change according to seasons only with the motion of sun, basically. Through this, we could identify which district had maximum GHI values and which district had least GHI values. So these are the numbers as well as the districts that were identified. Now we plotted the GHI values because this thing gave us maximum and minimum values. You cannot make a decision based on maximum and minimum value, but you have to know that what is the value that stays for a long duration, because it is an investment that you're going to make. So for that, we identified that median would be a better, we should know how the data is actually spread throughout that month or duration that we are observing. So we plotted a box plot. The median indicates around middle value of the data, and we could identify if the interquartile range was high, so we could understand that yes, the data is little spread. And this is basically of year 2021, 2022, and 2023. Thank you, sir. Okay. So basically from this, we identified that GHI values for India, all average, these are the months on the x-axis, and on the y-axis are the GHI values in kilowatt hour per meter square. And on an average, the GHI values, median values range from around 4 till around 5.5, you can say, in the summer season, pre-monsoon season. Then through these analysis, we could identify that the states, southern states and the states of central India had experienced more GHI values. And so we plotted their GHI box plots. This is for Gujarat. So you can see the interquartile range has reduced. That means the data is not very spread. So the estimate that you can get from these GHI values will be a fair estimate of how much energy, solar irradiation you can expect from at that place. This is for Maharashtra, year 2021. That side is 2022, and this is 2023. So the pattern remains almost similar across the year. So, but it varies seasonally. This is for Tamil Nadu. So in the pre-monsoon season, we get around 6.5 to 7 kilowatt hour per meter square GHI. And in the November-December season, when Tamil Nadu experiences northeast monsoon, the GHI values are very low. This is for Rajasthan. You could observe that the interquartile range in these states is less as compared to when we saw in India's case. This is for Madhya Pradesh, Karnataka, Andhra Pradesh. Also, so these were the states that we found that had more GHI values. But what we identified was, I underwent a report from RBI's website, Handbook of Statistics on India's States. It had data regarding state-wise per capita availability of power. So from there, I identified that all India average was somewhere, this was for 3 years. And these states has per capita availability of power lesser than all India level. So I tried to see what is the GHI pattern in these states and can we use solar energy to increase the availability of power in these states per capita. So, and to assess this, we've adopted one of this methodology to make a qualitative assessment of how much GHI value is good, marginally good, moderately good, highly suitable, or most suitable. So this was found in a research paper. So we've adopted this only. What this shows is, say for Uttar Pradesh, this 97 means in the month of January, 97% of the values had median GHI between 2 to 4. So in the month of January, most of the data, almost all of the data showed marginal suitability of Uttar Pradesh for solar energy. Similarly, this is the distribution. So none of these states has very high GHI values in the band of 6 to 8 or 8 to 10. But most of the states almost have moderately or marginal suitability. So moderately is even good. 4 to 6 range is good. From this, we identified that the states, the northeastern states, in these states, most of the states are, you can see that northeast, the entire northeast is the comprises of those states which has low per capita availability of power. And this also has a different terrain. So we could identify that, see, in the case of Nagaland, almost all the data is clearly in the moderately suitable range. And in Manipur, it's clearly visible that entire data is in the range of 4 to 6. So we could propose that this is similar for other states also, similar thing, for 3 years. That was, first was for 2021, then for 2022, and 2023. So basically what we could conclude is that most of the states, these are the suitability indicators and these are the years for against the respective states. And that in Northeast, we could explore more of solar energy. It has potential, but given the hilly terrain, maybe different kind of technology would be required. But yes, the state has potential. So we can explore that. Thank you.
I think in the interest of time, we're going to just move on. So if you have questions for the speaker, please talk to her during the coffee break. Is Anil Kumar Singh in the room? Maybe we can have questions. Sure, you have a question.
Thank you for giving me chance. By the way, I'm very glad to see the solar energy presentation, which is my field. And actually, this is not a question, so it's a small comment, your presentation. So actually, GHI is not a good index to represent the solar energy. It has to be converted into the power. So you should calculate the POA. I think you might heard about that. A plane of array of solar panels. Nobody installed solar panel on the ground horizontally. So it would have angle and the direction. So you should calculate the POA, and that calculation would be way more different from GHI patterns. So the more strictly, it has to be calculated as peaks and hours or capacity factor rather than GHI. Yeah.
Thank you. And I just got solar panels on my house, and one of the best things to do is just look at the power being generated from day to day, whether it's cloudy or not. So we're done? Yep, so it's time for coffee break. Take all the questions you've accumulated for the speakers, track them down, and start peppering them with questions while they try to drink coffee. And thank you for your attention. We'll start again up in 11:30.
स्टॉक में आप थे कि नहीं मुश्किल करता है नहीं चाहिए इनके रेंज में ऐसा होता है मुझे नहीं पता इतना दिखेगा रजिस्ट्रेशन करते होंगे मेरी पगड़ी मेरी करेक्टिंग पड़ता है हाँ वो मुझे पता है उसमें वो प्रॉब्लम नहीं ज्यादा हिमावारी की एनिमेशन देखिए एकदम सीमित है, कहीं नहीं दिखाई थी वीडियो तक भी व्हाट्सएप पर भी जैसे रील बनती हुई दिखती है। तो मेरे पास 380 इमेजेस हैं 15 मिनट के 380 उसमें देखेंगे बहुत अच्छा दिखेगा। याद ही नहीं होता 20-25 ग्राम भी चेंज आता है वो बनता हुआ देख सकते हैं जेट कोड किधर हाँ एक देख सकते इसकी वजह है क्योंकि अगर वो तो दिखेगा नहीं तो क्यों देखेंगे। मेरे को भी दिखता नहीं सब मैंने यूज करनी करूँगा अब जेट की जो वेन्यू है भाई वो इसके प्रोसेस में नहीं दिखा है नहीं दिखने हो फिर ज्यादा क्या देखने आपकी मतलब तो डिस्प्ले में क्यों नहीं होती अच्छा अच्छा ये भी बात तो इनका कवरेज एरिया नॉर्थ साउथ वो भी कम है वो दिल्ली दिखाया आपको 60 डिग्री तक कल दिखाया 60 अगर नॉर्थ पर कवरेज नहीं तो नॉर्थ से सिस्टम आता हुआ दिखेगा नहीं ट्रक बनता हुआ दिखता है एज इट इज फॉर्मिंग यू कैन सी इट इनमें नहीं दिखता ठीक वो अच्छा ओके 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 Okay, okay, okay. So ask IMD person whether you are giving data to them. Not data, whether you are participating. He said no. You want IMD to play, you to join. I will talk to them. I will talk to them and try to see what best can be. Yeah. Thank you very much. ये बैठे हैं क्या यहाँ पे? ये बैठा वो इधर बैठे और ये को हटा बुला था कल आज बोला है क्या लगा ना What do you control them? ये फोन लगवाया हूँ क्या तो उठा नहीं है
हटाने वाला है तो हटाने वाला तो है सर ठीक है लेकिन यहाँ कुछ है नहीं ऐसे कर नहीं
Okay. Chat करो अभी ठीक है अच्छा से बात कर हाँ ये दिया ना Yeah. So session started I मेरा भी सर हम एक्चुअली कर लेते हैं ठीक आप स्टार्ट करिए फिर आप हम अपना फिर आप that's 1 minute the session ये दे देगा आपको सर ये दे दिया थैंक यू आप आपस में बात करें अच्छा कोई बात नहीं सर आप बाकी बाहर एक और अगर पोस्टर सेशन वाला हमसे अप्रोच करे
Anybody here whose poster is not evaluated yesterday? Anybody is present here? You can
very interesting. They can
So we start. Okay. So so my name is Manik, and I've come from NOAA. I'm the Deputy Director for G6 Coordination Center. I'll be chairing this crucial session on application for weather prediction. In the context of the AOM SUC, numerical weather prediction actually occupies a key role because it connects the acquisition of
and Leo from Hokkaido University. First of all, we would like to apologize for not being able to join you.
So happening. Okay, so shall I start? Okay. Yeah, so numerical weather prediction actually occupies a key role in the context of meteorology actually, because it connects the data acquisition from various platforms with the final output that we are looking for, which is the predicted values or weather prediction. So in this context, actually, I have very good talks that I see on the agenda today. The first one is application of OceanSat-3 retrieved AOD in the WRF chemical model. The second one is influence of air-sea coupling on windfield structure of tropical cyclone by Diana. And a third one is the assessing the impact of INSAT 3D sounder data assimilation on tropical cyclone Fani simulation using WARF model by Vikas Yadav. And the fourth talk will be assimilation of INSAT 3D rapid scan AMV in the WRF model by Adil Mohammed. So these are very good talks. I hope, I'm sure during the talk you will have a lot of questions. Feel free to ask them. So let's get started with Aman Wahid Khan from ISRO. Aman, please take the stage and let's know what you have to say on assimilation of OceanSat.
Yeah.
So the first slide, please. The starting slide. So yeah, this work is done in collaboration between the Space Application Center and IIT Delhi. So I am registered there as a PhD student also. So like the basic title of this talk focuses on the assimilation of INSAT 3D and OceanSat 3 retrieved AOD in the WAFCAM model. So we know that one of them is a geostationary satellite, the INSAT 3D series, and the other is OceanSat 3, the recently launched satellite. That's a polar satellite. So we'll discuss in this talk how we can complement the high resolution data from the OCM3 with the continuous data from the INSAT observation, and how we can incorporate that in the WAFCAM model to improve the model analysis. Next slide. Achha. Okay. So this is the basic overview of the talk. So introduction. So we all know that how aerosols, they play a very important role. So like how it affects day-to-day weather. So like you can see like the air pollution, this is over Delhi. So also from the industries, and we have the stubble burning also. So all this, it impacts the air quality. And also, we also know that besides affecting the air quality, aerosols, they play a very important role in affecting the cloud microphysics and the radiative balance of our atmosphere. So it is imperative to study them. And due to the limited number of ground observation, so it is important that we should look into the satellite component as well. So over the Indian region, we have two polar satellites, which from which we measure the aerosol optical depth. So the MODIS is the US satellite, and the OceanSat 3. This is the recently launched mission. So this is the payload you can see. So OceanSat 3, it consisted of four major payloads. So one of them was the Ocean Color Monitor, OCM. So using that at SAC, we have retrieved aerosol optical depth. And you can see here this image. So this is the monthly mean AOD for the month of January. And we have validated this product as well using the internet observation, and we got a very good correlation of 0.87. So and this product is now made operational since last year, and it has a retrieval uncertainty of 0.06 plus minus 0.26 AOD. So so this is the OCM3, and the other Indian mission is the INSAT 3D series. So these are the geostationary satellite constellation. So the advantage of geostationary satellites is we get continuous observation of AOD. So we get the observation every 30 minutes. And if you combine it with multiple INSAT 3D satellites, say 3DR, 3DS, you will get even every 15 minutes. So these all are the Indian satellites from which we can monitor the aerosol optical depth. So the WRF came, so it is a weather research forecast model coupled with the chemistry. So it is widely used for air quality monitoring and prediction. So we have used this model in our study to incorporate the satellite data, the Indian satellite data in the model to improve the model analysis and forecast. So this is the basic methodology you can see. So we have the observations, we have the background. So background is we get from the WRF chem model. So here for the assimilation, we are considering the GOCART aerosol module. So which consists of 15 aerosol species consisting of dust, particle, sea salt, black carbon, organic carbon, and sulfate. So this comprises of the background of or we can say the first case of the model. And we calculate the background error in this background state. So this is calculated using the NMC. So once we have this observation, the satellite observation and the model information, so then we perform the data assimilation. So data assimilation is done using the GSI, which is a Grid Point Statistical Interpolation. So it's a NOAA package. In that we have developed the methodology for assimilating the Indian satellites. So you can see like this minimization is happening using 3D bar. And so it consists of minimizing the first part is the minimizing the the error in the model. The second part is minimizing the error in the observation. So you can see so our aim or objective is to find X, which is the analysis AOD. So and XB is a background state. B inverse is again the model background error, which we observe, which we get using the NMC method. And the other is the minimization of the observation error. So Y0, we know we have the observations from the Indian satellite, And H is the forward operator, which is again part of GSI. So here we have used the CRTM model for the calculating the AOD from the individual species. And the R inverse is the observation error. So like we have discussed in the first slide, so the observation error for OCM3 is 0.06 plus 0.26 AOD. So that is the observation error we will be giving. And the final term so is the constraint. So these are all included in the GSI, which we have used and to assimilate the Indian satellite observation. So here you can see the results of the assimilation of OCM3 retrieved AOD. So here you can see that we have performed this exercise for the month of January 2023. So every day, daily, we perform 24-hour forecast. We update the analysis after assimilating the OCM3 retrieved AOD, and then we give a 24-hour forecast. So you can see, so the first one is the 0-hour, the control experiment without assimilation, and this is the analysis after assimilation. So there is, and we have compared it with the MERA2 reanalysis product. So it's a standard product which consists of multi-satellite observation. It's a reanalysis AOD product. So you can see, like, so after assimilation, the model analysis is improved substantially. Also, the 24-hour forecast also, if you look, so we see there is a good improvement in the forecast as well. So many of the features, especially over the western part, or the eastern part of India, is like now being part of the assimilated forecast. So quantitatively, how much improvement is there? So this is shown here in the scatter. So you can see, so like the after assimilation, so the bias is improved. It is improved from 0.55 to 0.2 roughly, and the RMS is also improved from 1 to 0.6. So roughly like around 40% improvement is there in RMS, and correlation is doubled. So from 0.4, you can see like there is a large underestimation before assimilation, and after assimilation, this underestimation is greatly improved. So, and we get a high correlation of 0.8. So, and this figure, it shows the land average AOD values. So you can see like the green one is from the reanalysis product, the blue one is the control experiment, and the red is the assimilated field. So you can see like after assimilating, so for the month of January, you can see for the complete month. So after assimilating, the aerosol fields are much closer to the reanalysis. So this shows that we have successfully assimilated, and there is our analysis is more closer to the observation after assimilating the INSAT OCM3 AOD. So in the same month, there was a like on 6th January, so there was an extreme pollution event over the western part of India. So for this also we have assimilated, and we have, you can see, so like this is the first case without assimilation, and this is the analysis after the assimilation is done. So you can see that after assimilation, there is substantial improvement in the analysis. And so we have compared with again with the MERA2 reanalysis product. So you can see like, so there is like the complete thing was missing in the first case. So one thing to notice is like there is a large amount of overestimation in the MERA2, and its resolution is very coarse. So its resolution is around 2.5 by 2.5 degrees. So it's like a rough comparison. So that's why we have compared it with other independent satellite product as well. So we have the MODIS product and the INSAT AOD. So this overall, it tells like there is an improvement, and the improvement is roughly around 45% in RMST and 40% in the correlation. So one of the limitations of which I have not seen some of the results here. So one of the limitations of Oceanside 3 is like we get this product every 48 hours. So there is a lag. So you get an observation, and then after 2, you get your next observation after 2 days. So here comes the importance of a geostationary satellite like INSAT 3D series. So there we get continuous observation during daytime every 30 minutes. So in this experiment, what we have done is there was an extreme dust storm event which happened over India in June 2018. So we have assimilated like the this INSAT retrieved AOD in the model, and we have shown that like this is the product INSAT 3D, and we have assimilated this product in the model, and we have shown that there is a substantial improvement is there after assimilating in the analysis as well as in the forecast. So here we have also assimilated the MODIS product to give a comparative idea, because globally, like right now, many of the reanalysis products, they are assimilating MODIS, but the INSAT data is not going. So the primary reason is because of the quality. So the quality of INSAT is poorer because it's a geostationary satellite, and so its resolution is coarser, is also coarser. So, but what we have shown here is like in spite of the MODIS giving better statistics as compared to assimilating the INSAT AOD, the impact of INSAT observation is much larger. This is primarily because the amount of observation or the amount of data which is being ingested when we are estimating INSAT is larger because it's a geostationary platform. So that's why. So the impact is much larger. So what we have done is we have averaged over this box region where the actual dust storm event happened, and we have averaged the AOD values over this region. So and we can see. So the black one is the reanalysis. The blue one is the INSAT AOD assimilation. The green one is modest, and the red one is the control experiment. So you can see that after assimilating the INSAT AOD, it is giving the best correlation with the reanalysis. While modest gives closer, it is better than the control, but the INSAT gives the best fit when you are comparing with the reanalysis. How much is the improvement? So this improvement, it translates to roughly 50% in the when we are assimilating INSAT, and it is 30% when we are assimilating modest, and which eventually this reduces because we are increasing the forecast length. So the forecast is provided for 5 days. So as the forecast length is increased, so the forecast, so the improvement also it diminishes. So this next what we did is we combined the OCM3 AOD and the INSAT 3D AOD. So you can see here also, like, we observed that the maximum impact which we observed for after assimilating the INSAT AOD was in the first 24 hours. So what we did is we studied a forest fire event which happened over the Uttarakhand region, and so this is the forest fire event which happened over the Uttarakhand region. So what we did is we combined the OCM3 and INSAT 3D. So we assimilated INSAT OCM3, then we generated a forecast. After 24 hours, we again assimilated the INSAT 3D hours data, and then again we generated 24-hour forecast. So the assimilation was performed in a cyclic mode, so that the limitation of OCM3 which comes every 2 days, that can be accommodated. So here in this we have assimilated the OCM3 data into 3DR data in a cyclic mode. So every day we have assimilated this data, and we provided a 24-hour forecast. So and then we have seen that there is a substantial improvement. So this here you can see the from the satellite data also you can see. So here the fire started and then it spread, and the maximum spread came on the 25th April. So this event happened in April 2024. So the maximum spread of the fire was on 25th. So it shows the impact of assimilation. So this is a mirror 2 analysis which on 25th April, which shows the forest fire over the Uttarakhand and the Nepal region. So while when we are doing no assimilation in the control experiment, we are not able to capture this. But when we are doing assimilation with respect to the OceanSat 3 and INSAT 3DR data, we are able to capture this event, and that improvement is present in the analysis and forecast. So the one parameter which we observed which can be used as a tracer was the organic carbon. So once we have assimilated in a cyclic mode, and what we observed is we can use organic carbon as a tracer to identify this forest fire. So we can see, so the forest fire initially on 23rd, it's not present, and then slowly as the forest fire is getting intense, the organic carbon content is also increasing. So which is maximum on 25th, which we also observed from the satellite observation, and then it diminishes after 25th. So but again what we have done is we have averaged. So over this box region we have averaged the AOD values to show the impact. So you can see that blue one is the reanalysis, the green one is the control experiment without any assimilation, and the red one is with assimilation. So you can see clearly that while after we assimilating, the analysis is improved. So and this again the cyclic nature you can see. So after every 24 hours we performed an assimilation. So that's why we are getting a continuous improvement is there. So this again, it highlights that we have to use both our geostationary and polar satellites in hand to hand and together to complement this effort. So in conclusion, we have assimilated the OCM3 observation for the month of January, and we found that it is matching where the analysis is closer to the observation after assimilation, and yeah, so and the high resolution OCM3. So the OCM3 product is available at 1 kilometer, while the INSAT 3D is available at 10 kilometers. So we have shown here that how we can use both of these data together in conjugation and to improve the model analysis and forecast. So this will greatly improve the uncertainty in our model analysis and improve the forecast, improving like for the weather prediction capabilities related to the extreme events related to forest fire, dust storms, pollution episodes, and this has huge potential in when we are doing assessment of the impact of aerosols on weather phenomena like the thunderstorm or the tropical cyclones. So this is a very emerging field in which if you want to understand the impact of aerosols on your extreme weather events, so you can you can get a very updated aerosol field so that your model has better representation of aerosol, and then you can see its effect on the the weather, day-to-day weather and extreme weather events. So that's it. Thank you.
Thank you, Aman. That was a great presentation. Any questions? Okay.
Only for clear.
And I haven't got any chance to comprehensively share the eroded from cities or area as well as from facilities.
Yes, in CDPDR is already published. Is under
But comparison of both.
Okay. So I didn't mention yet. So like when we were assimilating the OCM3 data along with the INSAT 3D. So since like you mentioned, because there are only two different satellite products having their own. Since because both of them are two different products having their own error uncertainties, so what we did is we corrected, and we know that the INSAT 3D, like the OceanSat 3 is much accurate product. So we corrected the INSAT 3D R product in this case and to considering the Ocean 3 as a reference so that the error uncertainty is like better in that case. Thank you.
Any other question? Okay, thank you, Aman. Great. So the next speaker is Diana Siregar from BMKJ.
Hello everyone, I am Diana from BMKG, together with my colleague Swen from Ibrahim and Leo from Hokkaido University. First of all, hello everyone, I am Diana from BMKG, together with my colleague Swen from Ibrahim and Leo from Hokkaido University. First of all, we would like to apologize for not being able to join you all in person at 14th Asia-Oceania Meteorological Satellite Users Conference. Here, we are talking about influence of Earth's heat coupling on the windfield structure of tropical cyclones. First, I would like to give a brief overview of the process by which tropical cyclones form. Tropical cyclones, or TC, is a phenomenon developed over the warm ocean because it produces moist air condensing into huge clouds. Condensation releases heat energy, makes the upper level become warmer, so the winds move outward, and the dry air descends. The results are downdrafts occur in the eye, and strong updrafts occur in the eye wall. Internal processes within the cyclone restore the structure after an external perturbation characterized by wind bands and the eye wall replacement. This random co-produce intense rainfall, and the eye wall replacement is a secondary eye wall that tries to replace the inner eye wall. Actually, PC winds trigger the oceanic mixing and uprolling under the PC core. This mixing would produce less enthalpy flux. As we know, the less water vapor, the less convection, and a decrease in wind speed. The impact PC can cause heavy rains and destructive storm winds. So, to reduce its impacts, scientists contribute to improving PC weather forecast by studying its complex physical dynamics, like PIMO Expo 2021 did, The results show wind gradient and eyewall structure are associated with AC intensity variations, but they don't evaluate influences of environmental parameters. Since PC is a couple of RC interactions and its influence is controlled by synoptic flow, the motivation of our study is to investigate the sensitivity of PC wind structure to ocean feedback. Here, two numerical models are used. First, WRF stands for Weather Research and Forecasting and Atmospheric Model, and COCO stands for Coastal and Regional Ocean Community as Ocean Model. At WRF, we use two grids where the first domain with top size of 9 kilometers and the second domain with 3 kilometers is a multi-nest with higher resolution. For the simulation cases of cyclones, we use force and couple model. Then, to know the storm intensity, we assess the Saffir-Simpson hurricane. And to verify the ability of our model in estimating storm strength and intensity, we use best track from the International Best Track Ascribed for Climate Stewardship. In this figure, we can see that force model gets FSC from GDIS, stands for Global Data Assimilation System. And couple model, WRF gets SSC from PROCO, and PROCO gets momentum heat and water practice from WRF. Next, we are talking about the variable used for the models. First, for the TC parameter, we calculated the maximum surface wind speed and the translation speed. For the translation speed, we determined the total distance traveled by storm between 2 hours before and 2 hours after being a certain position. Second, the TC ocean response. Here, the delta FFT as the difference in maximum cooling between 2 days after TC passage and 2 days before TC passage. Next, environmental parameter. We analyze 3 items. For the background FFT, it is a local FFT condition at pre-storm FFT. Then we calculated the particle wind shear to remove the vortex over an area of 500 kilometers by considering only the background. And for the shear computation, we determine the difference of the background wind between 200 hectopascal and 850 hectopascal. Low. It is the average background wind shear for all particle levels. The last, the TC windfield structure, we use tangential, radial, and vertical winds. Here we calculated the radial wind gradient for 2 areas. First, I wall. It is an area between I and FMW, radius of maximum wind, and near core area that 3 times FMW. On this figure, you can see the highlighted green area. It is the wind gradient. We determine this area as the gradient in wind speed between minimum and maximum profile curvature. Then all these variables are visualized using a compensating method. We extracted the variable of a cross-section and average over a given time step, and then appended the variables into formula diagram to depict temporal evolution. Here for the results. In our study, we used 2 cases of cyclones. First, TC Irma, developed in the Atlantic Basin from August 31st, 2017 to September 11th, 2017. And the second one is TC Chami, happened in the southeastern part of Japan from 22 to 30 September 2018. Both TCs occurred in the same month, but different years and places. From this figure, we can conclude that our TC follows a similar track of best track, ADT RRCS, that the amplitude of intensity is underestimated compared to the ADT RRCS. Next, for the FFT cooling of TC Irma and TC Chami. As we know, force model use GDIS, so cooling is more absent on both force models. In contrast, for couple model, it has a significant SST cooling. So, these figures of couple models, we can see that both couple models show lower values. It is also interesting to see that this triangle that is more evident as a response to the different FST in both models. We saw this triangle moves slower than this EMA, so it could generate a decrease in SST due to intense upwelling. Here for the results of shear and synoptic flow. In the first figure, we can see that the jet stream in the Atlantic basin can generate easterly waves, which may favor Istiqamah. Thus, the cyclone moved westward following synoptic flow across the North Atlantic Ocean. Moving to the second figure, as is examined, the synoptic pattern was slightly complex as it turns to the north twice. You can see that the shear was weak at the first half and increased as it makes rainfall in Japan. Here, we use wind gradient as a good proxy to analyze the DC intensification associated with internal dynamics in the inner core. For the evaluations of this structure, if you look at wind gradients, the couple value was lower than first model, except on the peak condition for PC Irma, but the difference was not significant. And then at astronomy, the strong intensification on September 24, then it started to decrease, and the cyclone didn't intensify anymore due to the SST cooling. The difference between couple and post model at PC Irma are not significant. So we focus on physiognomy to analyze the internal processes of this structure in the cooling period. Okay, on this figure, we can see the eye wall with that cement was building upward. It means that there was a change in size of the cyclone. Next, for the vertical velocity, see there was a second eye wall replacement on September 26 to 28, which was more evident on the first model. Here we analyze that the first eye wall was not collapsing rapidly, so it led to the double eye wall. In the couple model, a second eye wall also happens, but the cooling limited the enthalpy flux. So on the third figure, you can see here the distribution of the total heat flux concentrated only at September 25, then decrease. So the secondary eye wall cannot manage to intensify the cyclone. Now we can see the physical structure for the first period, September 24 to 25. For the tangential wind, there was not much difference between two models, but couple model was lower than first model. And the vertical velocity, more updrafts in the eye wall up to 13 kilometer vertical levels, and the difference of both model was weak. A similar condition on radial wind, more inflow at lower level and outflow at upper level, whereas in couple models. For the second period, September 26 to 27, we can see clearly that the tangential wind was weaker. Updrafts were more chaotic because of less convection, and then the radial wind at upper level was less concentrated. Actually, all these conditions occur in response to the oceanic feedback. Then we come up with conclusions. First, we can know that the slower moving PC could trigger intense upwelling and SST cooling. As a result, the cooling limited the total heat burst, leading to negative feedback on PC intensification. So the eye wall replacements failed to maintain the DC intensity in the couple model. Due to the less enthalpy flux, a decrease in tangential wind, less concentrated radial wind, and less updrafts in the inner core of cyclone. I think that's all we have. Thank you very much for your attention. And if you have any questions, I'm happy to open for discussion.
Thank you, Diana. So I guess this is a recorded presentation. Is Diana online right now? Diana, are you online? Okay. So we moved, thank you for the presentation. This is very useful information about air-sea coupling, and I'm sure that members here at EAM SUC would stand to gain more and more traction on this crucial topic because it directly influences the field structure of cyclones. So thank you. And so we now move on to our next presentation by Vikas Yadav. Vikas will be talking about the impact of INSAT 3D sounder data assimilation. So Vikas, stage is yours. We have like 12 minutes of presentation, then right now. Okay. Just a moment. Actually, just wanted to know if Adil Mohammed from CUST is there. Are you online, Adil, or are you here in the meeting premises?
Is interested to present it.
Okay.
इसको BMKG से है।
अच्छा BMKG का एक नहीं BMKG का तो ऑलरेडी
तो उसका टाइटल और ये कौन सा प्रेजेंट है वो पता होना चाहिए।
खाली स्लॉट है तभी करना है।
अच्छा
नहीं
आप करना चाहते हैं आप कर लीजिए दोनों कर ले ठीक है ओके यार विकास
Thank you, sir. Myself, Vikas Yadav. I am honored to present the findings of our work on the behalf of Dr. Sanjeev Kumar Singh, Dr. Yogesh Kant, and Dr. Devasis Mitra. So, as we know that 90 to 95% of the data used in numerical modeling comes from satellite. Therefore, building on this concept, our topic is assessing the impact of INSAT 3D sounder data assimilation on tropical cyclone Fani simulation using the WRF model. So, further improving the forecast to decrease the impact of disaster over some region. So, as we know that there have been improvements in the data assimilation techniques along with the enhancement in the remote sensing instruments measuring the atmospheric quantities. So, also there have been improvements in the quality and the range. So as we discussed that 90 to 95% of the data used in modeling comes from satellite. Therefore, to effectively anticipate the future state of the atmosphere, we need to accurately incorporate these satellite data in the simulation. So here we are using INSAT 3D sounder data for our study to that we will be assimilating on the WRF model. So this is the study region of our study. Here we have taken tropical cyclone Fani as our case study. So it's sustained from 26 April to 4th of May 2019 in Bay of Bengal region. So here are the data that we have used. We have used ANSWER GFS model data. Then, as I already mentioned, I have used INSAT 3D sounder data. And for validation, we are using IMD best track for tropical cyclone Fani along with the maximum sustained wind data. So we have used WRF model version 4.5.1 with moving nested domain. The parent domain resolution is for 24 kilometer and nested domain is at 8 kilometer. We have used grid point statistical interpolation system, which is a unified data assimilation and analysis system. So in this particularly, we have used three-dimensional variational data assimilation technique. So it is the table summarizing the context of the model configuration and the parameterization scheme we have used in our study. So the data assimilation process uses the WRF model So the data assimilation process uses the WRF model. So while incorporating the observations to better model forecast. So here we have performed two experiments. One is CTL run and other is INSAT run. In CTL run, we are using conventional observations, and in INSAT run, we are using the INSAT 3D sound data along with the conventional observation. So total 4 simulations we have performed starting from 29th April. So further moving on the results, this figure shows the brightest temperature sounder observation over the study region on 29th April and 30th of April. So we have calculated the analysis increment, which is the difference between the result and the background. So here we can see that in figure A, there the temperature analysis increment ranges from minus 0.8 to 2 degree Kelvin, and that U wind ranges from minus 18 to 6 meter per second, while V wind ranges from minus 4 to 3, and the moisture ranges from minus 0.6 to 0.7. So here we can see that there have been adjustment in the study region. The values where we can see the values where they are positive, like this, and there have been negative values also over the study region. So there have been adjustment in the simulation. So this is the 72-hour track and forecast error from initial condition 00 of 30th April. So here this red one is the MD best track, and this blue one is the INSAT run. Second experiment, the first experiment is that CTL run, green one. So this figure shows the track forecast error. So here we can see that for about initially up to 24 hours, both are both are leftward bias. Inside both experiments, CTL and INSAT run. Later, for next 12 hours, they got deviated towards rightward. Then that INSAT run means followed the MD observer track more accurately in comparison to CTL run, which after 6 hours got deviated towards rightward. So here we can see that this bar graph that in the that CTL run is showing the less track error in comparison to the INSAT run is showing the less track error in comparison to CTL run for different lead time hour. So this is the second one. It is also showing 72-hour track. So here we can see that initially that CTL run from initial to up to 48 hours, it is following the MD observed track, but later got deviated. But seeing the CTL run, it follows the MD best track from initial to up to 18 hours. Later, the deviation is more in comparison of the INSAT run. So here we can see that INSAT run again showing less track forecast error compared to CTL run, except this 72-hour lead time hour, where we can see that INSAT run is more deviated in comparison of the CTL run while comparing to the MD best track observations. So this table summarizes the average track error of tropical cyclone Fani. So this is the this column shows the INSAT run track error, which is having lower values as compared to CTL track error. So the green column, we can see that there is the improvement in INSAT run compared to CTL run. So these value ranges from 3% up to nearly 14%. So here both the experiments in we have compared the simulated maximum sustained surface wind and observed MSSW. So here we have calculated the coefficient of determination R square. So the more the value is nearer to 1, the better the model is to forecast. So we are getting R square value near to 1, more it is more nearer to 1. Therefore, we can say that INSAT run is having a better forecast. So here is the conclusion. So we can say that there have been improvement in the track simulation error of INSAT run compared to CTL run. that ranges from 3 to 14%, and that there have been significant improvements in the tropical cyclone intensity simulation. So, to achieve more robust results, more cases to be studied in future.
Thank you, because that's a very nice presentation. So any questions on Vikas? Yeah.
Yes, nice work. Just I want to ask whether you have assimilated the radiances or the product profiles. Is it radiance assimilation or product assimilation? What from sounder? Sounder radiance assimilation or profile? Profiles you have. You are not doing radiance assimilation. Okay. And then second question is, you have only analyzed your track error, no? Track, but what about landfall time? Because I've seen that they are hitting coast at different time. So whether there is any change, improvement, or something in that?
Like I have not mentioned in the slide, but we have like in the first simulation we have landfall location error for CTL run is means showing higher values, nearly around 47 kilometers, and for inside run it is 4.7 kilometers. So improvements, and for likewise for the second simulation also like 25 nearly 25 kilometers for CTL run, then around 5 kilometers for inside run.
Okay, but the suggestion that you should try to assimilate radiances and also try to see that all sky radiance, if you can simulate and make it better. Okay.
So any other question? So I have one question actually. Can you go back to that last slide where you say surface winds? Yeah, this one. So here actually the spread of this INSAT run is lesser. I mean, looks like. So do you? So does it say anything about like it's not? I think it's not just the correlation that you're finding, but also is there anything else that this plot says, like because the spread is less than what you say over there? I mean, is less noisy or more signal or?
Sir, I have no idea about like.
Okay. Yeah, thanks. Thank you. So, so we have a change actually in now. So earlier, actually, Adil Mohammed was supposed to present. Now we have a confirmation from Ulil Hidayat from BMKJ, Indonesia, and he'll be talking about rainfall potential from Himawari 9 for early warning systems in Indonesia. So Ulil is online. Ulil, can you please start? It's a very interesting topic.
Good afternoon. Can you hear my voice?
Yes, loud and clear.
Okay. I will try to share screen. Okay. Okay. All right, good afternoon. Hello, my name is Solidet and I'm from BMKG Indonesia. And in this occasion, I will present about the result of our project, the rainfall potential product from Himawari 9 for the warning system in Indonesia. We try to bridging the empirical and machine learning approaches. So for the introduction, Indonesia is a complex country. It means the weather pattern is really complex because there's several factors. And this makes Indonesia become really vulnerable to meteorological disaster. So,
Hidayat, 1 second. Can you make your presentations in the slideshow mode?
Oh, yeah, sure. Yeah.
Thank you. Thank you.
Okay. So my institution, BMKG, we try to develop product based on satellite data called rainfall potential or RP. This product try to forecast the rainfall for next 1 hour into 4 categories like moderate, heavy rain, and very heavy rain. And this product is widely used in extreme weather analysis in Indonesia. However, the accuracy and performance of this product is still not yet been truly evaluated. So we do this project to assess the quality. Also, we try to provide several alternative approach to enhance the quality of this product. Okay, so the data and methods. In this project, we use two data. The first one is Himawari 9 data, especially the band 13 plot top temperature. And the second one is GSMAP data as the validation. It means the observational data for rainfall. And the domain is in Indonesia, and we took data for 1 month in January 2024. We try to use several methods. It's auto estimator, IMSRA, NLI, and NLR in here. Also, we use several machine learning approach. It's include machine learning linear regression, convolutional neural network, and random forest. We try to see which one provide the better result. And the flow chart is start, and then the data we do pre-processing, and then we do processing and the result validation, and then end. This is detail, the more detail about the processing part, the empirical and the machine learning or AI. We divide the result into 2 parts, part 1 and part 2. The part 1 is the result by output by rain rate value. So it's only about the rain rate value, how good the model predict the rain rate of the value. And the part 2 is by the category. So we use 5 parameters to assess the quality in part 1. It's include RMSI, MIA, correlation, bias, and percent bias. And the result is, for the empirical, it's auto estimator, IMSRA, NLR, and NLI. The most better result is NLI. And we can see that by looking for the RMSI, the value, also the correlation one. But although the machine learning part is good result in this one, like RMS is really low, but the bias and correlation is really weird. And it's really clear when we see the scatter plot. You can see that auto estimator, IMSRA, NLR show good enough result. It means they can see the pattern of the rainfall, but for the machine learning part, it's really weird, especially like this one, CNN. The model only can predict up to 10 millimeter per hour, and this is not good. So we do part 2. The part 2 is the output classification by rainfall potential category. So instead we using activation regression, we try to using classifier. In CNN, we're using CNN classifier. For random forest, also using random forest classifier. And here's the result. So we try to divide by 5 class. The class 0 for no rain, the class 1 for slight rain, the class 2 for moderate rain, the class 3 is for heavy rain, and class 4 for very heavy. And the result is in class 0, NLI is the model that has good performance compared with the others. In class 1 is IMSRA, class 2 is random forest, class 3 is random forest, and class 4 is auto estimator. Although in class 4, almost every model failed to detect the pattern of the data because due to some imbalance of the data. And then you can see that more clear based on the confusion matrix. Also, I want to note something that the existing algorithm is auto estimator has overestimate, slightly overestimate, because they tend to classify the category slightly above the actual category. For For example, it predicts the moderate, but actually it's only slight or even no rain. And in here, this for the machine learning part, you can see that random forest is actually enough good model to predict the category, because yeah, especially class 0 and class 1, also in class 2, but in class 4, the random forest model failed to predict it. And we still try to develop the model so it can predict that well in class 4, as well as in convolutional neural network. And then to see that spatial pattern of the case, we can see the case study. So in case 1, we try using a flash flood due to heavy rain in Agam, West Sumatra, 11 May 2024 in 9 UTC. And you can see that the existing algorithm is auto-estimator compared with the observation in here, the left corner, GS map, is really overestimate, right? And then you can see the NLI and random forest. It's almost have the same pattern, especially in slight rain and also in moderate, but for the heavy rain, in the actual, there are no heavy. We still try to develop this product. Also, there are some heavy rain-induced flood in Buyung Brau in 15 March 2024. And in here, you can see that slight rain pattern in NLI and random forest. It's almost similar. And also, there's some moderate and heavy rain on it. Okay, so the conclusion. The conclusion number 1 is the existing random rainfall potential product using auto-estimator algorithm is tend to overestimate and classify range events above the actual category. So we provide several another approaches. And for empirical method, analyze the method with the best performance. And from machine learning method, random forest demonstrate the best performance. Although NLI performs well in light to moderate rain category, random forest is likely better at capturing patterns, moderate and heavy rainfall events. So, and also this product still requires further development. We have to say that, especially in particular in model development, more data is needed to accommodate class with very limited data, especially in class 3 and class 4. Validation with observational automatic weather station also is necessary using pixel to point. Yeah, that's my presentation.
Thank you. So thank you, Hidayat, for a great presentation. Any questions for Hidayat? Yeah. Yep.
Hi, sir. Thank you for the presentation. So I was wondering to ask, is it a completely supervised classification that you are doing?
I'm sorry, can you repeat that question, please?
Yeah, is it a completely supervised classification that you're doing?
Yeah, it's completely unsupervised, to be honest, for especially in random forest and convolutional neural network.
Okay, so as far as I understood, like you were comparing between RF and CNN. So is there any, and you were saying RF was slightly better. So is there any sort of improvement in the generalization in case of CNN? Have you seen that? Because
Yeah,
like it's a more stable model, right?
yeah, that's true. In this case, due to some imbalance of the data in nature, of course, because the heavy rain case and also moderate rain case is really seldom compared with the slight and no rain. The random forest is the most suitable method, I guess. It's because the performance is really good to catch the pattern. In other hand, the convolutional neural network is catch the pattern of slight rain. We have said that, but for the moderate and heavy, it's how to say that? It's hard to detect that. I guess maybe it's the overestimate of the model, and also for some node that we use undersampling method in random forest. in here we'll use like almost for very heavy case, we just left like that, 16 case. For the other case, we use the same case, it's 8,000 case. So we try to undersampling that, and the result is like what I presented before.
Okay, I understood. Maybe probably increasing the sample would have given better with the CNN, you feel. Okay, okay.
Yeah, thank you very much. Yeah.
Thank you. Thank you.
Good question. So,
Okay. Thank you very much. I'm Toshiyuki Green of JAXA. I'm so glad to you are using the GS map data. And also that you know that GS map rainfall estimation over the land is not so good. And in JAXA, it's an internal discussion started to provide the software to the real-time calibration of GS map using the AWS rain gauge data. And hopefully this software will be introduced maybe the next year's Asia-Oceania Medical Satellite Users Conference. It might be a kind of the public domain software and it is of some help for your work. Thank you very much.
Thank you very much for the information.
thank you, Toshi, that's a great news, and I'll record this in the minutes also for the session. Yeah, so I have one quick question actually, that you say that the random forest performing best, but you also mention, as I understand, like in the fourth category, it is not doing well in one of the classes, and you say that there is class imbalance also. So how do you plan to deal with the class imbalance?
Thank you for the question, sir. So to handle the imbalance of the data, we try to do some undersampling, also some oversampling actually. So we try to oversample the data using small module on Python, but it turns out the result is not that good. So instead of oversampling the heavy rain case, then class number 4, we try to undersampling the others, especially for class 0, class 1, class 2, and class 3. And the result like that, like I presented before. Yeah, that's the method that we use to handle the imbalance of the data.
Okay. Yeah, thank you, Hidayat. So if there are any more questions, please. Okay, so thanks a lot for all the presenters in this session, to Aman, Diana, Vikas, and Ulil. So this brings us close to this session. Thank you all for being here and participating in this session. So thank you. Thank you.
So now it's time for lunch, so we can come at ground floor and again gather here by 1:30.
for a great presentation. Thank you. Thank you, Rad, for a great presentation. Any questions or? Yep.
Hi, sir. Thank you for the presentation. So I was wondering to ask, is it a completely supervised classification that you are doing? Completely.
Answer for
You are comparing with
population and neural network.
each talk is 15 minutes. Hopefully the speakers will not go 15 minutes, so there's time for some spirited Q&A before we change, so. Take it away.
Excuse me. The presentation. Can you please load the presentation? So good afternoon. So topic of my presentation is enhancing short-term weather forecasting for Indian region using WCF geo products and PyStep nowcasting. So to begin with, so we all know about severe weather events. So severe weather events are like very chaotic in nature, and it's hard to like predict them. So and also they cause a lot of economical loss and damages to property. So we need a reliable prediction system for severe weather events. Okay, and if we talk about reliable weather prediction system, and if we go for a long range or a mid range forecasting system for severe weather nowcasting, so it might not work actually. So what happened, these severe weather events are very rapidly evolving in nature. Like, so it is very short lived. So we need something like which can accommodate near real time data very quickly. So we go for nowcasting applications. So the advantage with nowcasting is like it can accommodate input which is coming in near real time, and it can update itself with a near real time information. So that is very helpful and useful for capturing the evolution of this severe weather events. So that's why we are going for this. And one more thing, if you talk about nowcasting, one more thing which is important about this is like the input data which we feed. So the input data should also be like continuous, and it should come in a like update itself in a frequent amount of time. And so it should have a good spatial coverage if we want to talk about a bigger, larger domain. And also it should have a high spatial resolution. So we can directly go opt for satellite data. But the problem with satellite data and predicting severe weather events is like sometimes these satellite data directly do not associate with the severe weather events like thunderstorm, lightning. So we need products, like secondary products, which can directly associate with this severe weather events. It's like if you talk about thunderstorms, so we need some product like convective initiation kind of product, which can directly give information about this thunderstorms activity. So for this purpose, we use NWC SAF geo application, which take this in the satellite data and generate this meteorological products. So again, one more critical thing about nowcasting model is this model should be reliable enough, and it should use algorithms like which can capture the evolution and movement of this severe weather event. So for this purpose, we are using PyStep based nowcasting model in our study. So starting with WCF. So this application is built by EUMETSAT, European Meteorological Agency. And for this, we require two important things like satellite data first, and it also accommodates NWP data. So for satellite data, we use MSG IODC savory data, all the bands. And NWP data, for this study, we are using GFS 0.25 degree data in this whole model. So this application, what it does, like it's for before we start this application, we have to configure this application properly for our desired domain and desired region. So we configure it, and we configure the, like there are different files like NWP files and satellite files. So these system files has to be configured like according to the what data you are using it. Like if you're using savory data, then you have to accordingly you have to configure it with savory data. And like if you're using GFS data, then NWP model also be configured to that data. Then this model have different algorithms for different products. Like there are many products like cloud types, convective initiation, thunderstorm. So they have different algorithms, and for each algorithms they are using different ancillary data also. So so this when we execute this algorithm, first of all, what we do is like we map the NWP data, and this mapped NWP data along with the satellite data is then executed with the algorithm, whichever the product you desired, that algorithm will execute. And then we get the desired meteorological input. Okay, so this is the first product which we are getting from the NWS Geo. It's like cloud mask, though it doesn't seem much, but it's very important to have a good cloud mask product. So it will be used further in like evaluating with other products. Like if you talk about precipitation related products, then it will be used. If you talk about SST, then it will be used. So cloud mask, what it does, it like delineates the pixel, whether it's a cloudy pixel or non-cloudy pixel, that kind of information you get. Alternatively, we have another type of cloud mask product, which give also information of the pixels which are contaminated with snow. So that also we have. And these are the satellite inputs and NWP inputs used in this product. Again, other interesting product is like cloud microphysics product. So here you will get cloud top phase, cloud ice water path, cloud liquid water path. So for cloud top phase, it's very important, like you get information about, I think it's not visible, I guess it's visible. Oh, so cloud top phase, you get information like what kind of phase it is, like icy cloud or liquid cloud or like mixed type of phase cloud is there. So that kind of information is very useful when you talk about some aviation activity or like talking about precipitation information. So these information are really, really good. So again, the satellite input and NWP inputs are given here. You can take that. And again, there's one more important information we are getting from NWS Geo. It's the cloud type products. So what does it do? Like this cloud type products, it distinguishes between different type of products. You have from low level clouds to upper level clouds, from like high level opaque cloud to like semi-transparent cloud. It distinguishes, and that distinguishing is very important for like meteorological purpose. Like if you talk about high opaque cloud, it can directly relate to your CP clouds. So you are talking about thunderstorms, so you need that information, right? So this is very important product. Again, there is some satellite input and NWP inputs which we require to use this generate this cloud type product. Okay? So yeah, again, there's one more important product, which is a convective initiation product. From this image, if you're not able to see, there is, this side some convective initiation cells are there. So in this image, I've just enlarged it and showed in this cell. If you can see some pink, yellow colors, the dots are there. So these are some convective initiation cells. So if we talk about some convective storm kind of thing, so first information you require if you want to predict this convective storm, first information you require is like the convective initiation, whether there is any sign of convective initiation or not. So this product gives you the probability of convective initiation, probability of thunderstorm. So this you see, this is the scale, like there is a probability of 0 to 25 probability to have the thunderstorm activity initiated. So this is the scale, and here you get the convective initiation of cells. Okay, again the desired satellite inputs and NWP inputs for the this is also very interesting product which is generated by NWS Geo. This is RDT, Rapid Developing Thunderstorm. So what it does, it uses a convective initiation product and other products which I have told you, and generates a polygon kind of a thing where this rapid developing thunderstorm activities are there visible. So it gives you how these thunderstorms are evolving. If thunderstorms are there triggering, or it is in a mature phase, or it is in a reciprocating phase. So that kind of information we get. Also, we get the like. If you see the arrows, we also get the information like which direction they are probably heading. So these two products, convective initiation and rapid developing thunderstorm products, which we are getting in like nowcasting mode also. So we are getting like max 30 minutes lead time, 60 minutes lead time, and 90 minutes lead time. So same with rapid developing thunderstorms. So we can get it till 90 minutes lead time. So we have this product also. So again, there is some convective rain rate product. So this convective rain rate gives a convective rainfall intensity information about it. And they have some alternate product as well, like convective rain rate, which is derived from cloud physical properties. Okay. So why it was needed actually, this CRPH actually it was showing better result than CRR. But what it does like uses some channels which are only available in the daylight, like visible channel and all. So it was available. This product was initially available only for daytime, but then they what they did is like for nighttime they generated a pseudo visible channels and all the channels which is required. So they follow the different nighttime algorithm for this product. Similarly, they have a precipitating cloud products. So it gives a likelihood of precipitation, whether this cloud will be precipitating or not. We have a like category from 0 to 100. So that is the probability which will tell that this the probability of this cloud to be precipitated. So again, we have two products like precipitating cloud and precipitating clouds using cloud physical properties. Okay, so two algorithms are there. So again, this product was better, but then again it was available on the daytime, and they have a different mechanism for nighttime products for this one. Okay, so here the requirement of PC and PCH for satellite input and NWP inputs are given here. Okay, so yeah, so some analysis we have done is like there is one case study, Wayanad. There was some heavy rainfall event we have observed. So if you see, what we did is like we take a special region of Wayanad in Kerala, and we generated some cloud fraction for calculated the cloud fraction at every pixel, cloud fraction with different type of cloud, and the fraction of convective rain rate. So and then we took a mean, and then they took a mean of early convective rain rate and this type of clouds. So we see that this black color dashed line you see, if you observe, this is convective rain rate here. And if you see that this green and the red color line, red color line, it's closely resembling the pattern of this convective rain rate. So these are the green color light. If you the green color line, if you see, that is a your high opaque cloud, and then red color is very high opaque clouds. So we can see that information that how convective rain rate is associated with opaque and very high opaque clouds. And this, like we also see that there is a positive correlation with high opaque and very high opaque cloud with convective rain rate associated with it. Simultaneously, we have seen that what kind of phase we observe with during the convective rain rate. So we see that where this again the black color dashed line is showing the convective rain rate for this period, and this yellow color line or mustard color line, you see this is a ice phase. So this ice phase is closely resembling the pattern of your convective rain rate, and again we got the positive correlation with this convective rain rate. Okay. Yeah, this is one study we try to do. Like now we have the products. Now what we do with the products, like we can further integrate it with a nowcasting model and generate a nowcast from that. So this is one CRRPH product, like a convective rain product. Okay, so what we did is like we integrated it with a 5-step based nowcasting module. So it is a optical flow and autoregressive process based nowcasting application. So that application, we feed the data and we generated the nowcast for next 90 minutes. This data is available in a 15 minutes cycle. Then we generated like 6 time steps further, and 90 minutes nowcast we have generated. So the upper two images are the nowcast, and this is the observations which we are getting. So it's closely resembling the nowcast. And there's this GIF images we have created. You can see the pattern of the clouds, how it's moving. It's kind of. So the summary of like this is the satellite data is play a key role in our this short-term nowcasting, and this critical meteorological products can be derived from NWSF geo products, and also like products like convective initiation and talk about rapid developing thunderstorm will be very useful when we talk about Indian terrain regions, because it's very complex. Like there are like many parts in India which are having problems with this developing this thunderstorms and convective storms problems. And yeah, integration of 5 steps was successful, and we can further enhance this forecasting activity using this 5-step for this. Thank you.
Okay, thank you very much. We have time for a very quick question.
Thank you for the presentation. So the last slide, second last slide that you showed, pi steps, using pi steps, you tried to nowcast the rainfall. So the input you used for pi step was a rainfall product generated from NWC SAF, right? So unless that rainfall product detects a rainfall cloud or any rainfall cell or pixel, so will the pi step also try to tell you that where the next rainfall will start, or it will, like a optical flow, it will only tell you that once the rainfall is there, in which direction or how fast it will be moving, or it will also try to nowcast where there is no rainfall right now, but after 1 hour or after 2 hours, there will be a rainfall in that case.
So very good, because it's a very interesting thing is like what I told you about nowcasting, it keep on updating itself. So what they do is like for this spy step, we used some we can decide the this one. We can take a set of images, like past images. Like suppose you can decide like you want to take a 1 hour set of image. So it is these data we can use for training the model. So it keeps on updating the training data set. So if for 1 hour there is no rainfall, that it will not show you the rainfall. But then next image, whenever after 15 minutes some rainfall activities appeared, then it will again show that rainfall moments are there. Then it will be.
Thank you.
Okay, then we move on to the next presentation. That is on Himawari 9 observations of volcanic ash dispersion over Indonesia area. Do we have the presenter here? Pardon? Oh, it's a recording. Okay. Are they ready? Okay.
Good afternoon, everyone. I am Adinda Dara Fahada. As one of the members in Public Meteorology Directorate BMKG, will present about volcanic ash observations conducted using Himawari satellite over Indonesia area during 2023 to 2024 period. We will explore BMKG's role, the technology used, and the significant findings regarding volcanic ash dispersions. First of all, about the purpose from this project are the research. This observation started from mid-2015 until now using Himawari 9 data via satellite application. Those observations recorded and archived, but no further analysis about the eruption, such as type, pattern, and duration. So that the research aims to identify the significant volcano, type of the eruption, dispersion pattern, and how long the eruption lasted. And then the volcanic ash meaning is a mixture of rock, mineral, and glass particles expelled from a volcano during a volcanic eruption and flowed less than 2 millimeters. Also, for the addition of information, groundwater near a magma chamber can be flashed into steam and be the source of ash particles for some eruptions, so that the Himawari can observe these particles in the atmosphere. And also, due to its jagged edges, volcanic ash particles which travels further in the air could be very corrosive and potentially dangerous for airplane machines and will pose a significant threat for aviation safety. BMKG operates two meteorological weather offices, or MWOs, in Ujung Pandang and in Jakarta, which responsible to manage flight information region in Indonesia airspace. These offices are responsible for providing SIGMET information related to volcanic ash, tropical cyclone, and severe weather phenomena. BMKG follows a structured approach for satellite data processing to monitor volcanic activity, which documented in Technical Guidance of Satellite Data Processing number 2.6 about Himawari, RGB volcanic ash product processing and visualization. By retrieving and analyze several sources of information from VAAC Darwin and PVMBG to confirm the presence of volcanic ash clouds, conducting routine observations every 3 hours frequently during emergencies. The utilization of 3 RGBs to ensure the presence of VA clouds such as RGB PMKG VA, RGB ash, and RGB SO2. Between 2023 and 2024, Himawari detected 2,264 volcanic ash events, with 87% occurring in 2024. Mount Lewatobi is the most prominent source of volcanic ash dispersion activity, and there were 4 other mountains recorded significant eruptions, such as Dukono, Ibu, Semeru, and Ruang. BMKG Public Meteorology adopt and modify the original ash RGB invented by UMETSAT and JMA by adding 3.9 micron, sensitive to high temperatures. This combination allows us to identify hot volcanic ash clouds, cold clouds, highland, lowland, and sea regions effectively. According to our findings, the 5 significant volcanoes are classified into Strombolian and Volcanian type of eruption, where the likelihood or the intensity of the eruptions also divided into 2 categories. The first is effusive eruptions, which means the eruptions are mild into gentle explosions. And the second classification is explosive, which means the explosion categorized into violent and big explosions. The second significant eruptions revealed from Mount Dukono and Mount Ibu, which located on the same island, Ternate Island. Type of eruption from these volcanoes is effusive Strombolian, which means mild to moderate explosive eruptions and continuous or periodic lava flows. This is also in line with the pattern of eruption that Himawari observed, which is eruption with small explosions, hot, thin dispersions of hot volcanic ash and low intensity of SO2 gases. Next is Mount Semeru, which has almost the same character with Mount Dukono and Mount Ibu. Eruptions observed rarely and accompanied with slight thin volcanic ash dispersions. The next significant volcano is Mount Lewatobi, which has explosive Volcanian type of eruption. According to PVMBG and Volcanism Program, this volcano has moderate to violent ejection pyroclastic clouds. This information also confirmed by 3 RGBs, which indicates the presence of high concentrated SO2 gases and thick hot volcanic ash. As an additional information, Mount Aeroso-based explosion also observed by Maumere radar. The ash column height reached 5 to 9 kilometers height. Last dramatic and significant volcanic ash dispersions observed by Himawari is Mount Ruang, which happened at April 17, 1300 DC and lasts for 3 weeks. Himawari observed 125 events for 3 weeks, where the eruptions continuously happened with big explosions and thick volcanic ash dispersions. For the first explosions that happened in April 19, 13 UTC, several lightnings struck when the first blast of volcanic explosion happened. And then from Himawari, the first explosion was considered as rich water vapor and recognized as cold, thick, high-level clouds, followed by high concentrated SO2 gases and hot ash clouds. So for the conclusion, the KGVA RGB or Himawari 9 images are beneficial as validator for volcanic ash information noted in SIGMET information as supportive information for volcanoes historical data, and also quite representative to inform the real-time dispersion of hot volcanic ash clouds. We just need to combine the RGB ash and RGB SO2 to require and determine, to determine the volcanic ash contents. For further research, information need to be gathered not only from the geostationary satellites, but also from polar orbiting satellite to validate the presence of volcanic ash dispersions. Danyafan, thank you very much.
Since this is a recording, if you have questions, you can email the author.
We move on to the next presentation on training in WMO RA5 during 23-24 by Australia Bureau of Meteorology, Dr. Bodo.
Okay. That's the presentation that was just downloaded from, yep. That's it. You got it. Great. Thank you. All right. So I'm very pleased to meet you on the podium once again. And I'll be talking about the satellite meteorology training in WMO Region 5 during the past year. It's the Australian VLab Centre of Excellence experience, and it gives you a bit of an idea, I think, about the sort of engagement that we've done across the region. We'd love to have in the next year, when we're doing our report for AMSUC 15, we'd love to have India there as well, engaged and so forth. And I think there are already some parties that are interested in that from IMD that have approached me. So that's something to look forward to. I thought I'd start off by just giving you an idea about the Australian VLab Centre of Excellence. So maybe just a brief overview, if you don't know. So the Centres of Excellence, they work closely together with one or more of the satellite operators, such as the Japan Meteorological Agency, the Korean Meteorological Administration, and the China Meteorological Administration. And they are established in all of the WMO regions. Here you can see Region 5, and you can see Australia there as well. And the idea is to meet user needs for increased skills and knowledge in using satellite data within the region. But they also serve a really useful test bed. So the satellite providers can actually forward that information, and they'll get that it gets converted into local case studies, which provide feedback to the satellite provider as well. Just to give you an idea, my supervisor is Dr. Mick Pope, and he's also the head of the Center of Excellence. That's me there as the main point of contact. Past supervisors have included Roger Deslandis, Peter Davidson, and Duncan Tippins, and they've kind of moved on, and I've just stayed, sort of like a barnacle, just stayed, because it was really, really enjoyable kind of work here. You can see too, important contact, our principal sponsoring satellite operator is the Japan Meteorological Agency, but there are other, and of course, over the last year, we can see there the little that area over Java, we have the Indonesian VLab Center of Excellence that have joined, and we've done close collaboration with Ani and colleagues as well there. And of course, we have connections with CMA, KMA, the USA, that includes CIMS, it includes CIRA, it includes NOAA, NASA, and so forth, and with EUMETSAT. We have also this year celebrated our 11th anniversary. So perhaps just some very quick highlights of what we've been up to over the last 11 years. And it kind of is a segue into what's likely to happen in the future, in the near future as well. Our first regional focus group meeting was October 2013. We've been collaborating with our principal sponsoring satellite operator since that time. We actually had the National Himawari Training Campaign before Himawari 8 was launched. We used polar orbiting data, existing satellite data to replicate the products that were going to be expected to be used once Himawari 8 was in orbit. So it's actually giving the forecasters a look into the future so that we're better prepared for when the data did become available. Over this time, we've had 122 sessions. We've had over 4,000 logins. And of course, most recently, the Indonesian VLab Center of Excellence have joined. So to give you an idea, that's the number of attendees, the number of sessions, but where did they come from? Well, this is the total area. And so if you divide 4,015 by 122, the average number of attendees to these almost monthly sessions, almost 33. Where do they come from? On average, the strongest contributors to the sessions have been BMKG Indonesia and Australia. We've also had strong contributions from Japan, JMA, Korea, and China and the USA, Hawaii. But you notice, as we start looking a little bit more detail, it's right across the Australasia Pacific region. And India, we want some statistics for India for next year. So it's a little call out to maybe India and maybe even going out toward Iran and Saudi Arabia and Oman, but recognizing, of course, that we have to deal carefully with the Oman Center of Excellence because that's within their own regime. So maybe more collaboration. All right, so this gives you some idea over the past year what we've come up with in terms of actual sessions that we've conducted that have now been recorded, that are now available, that you can download. Typically, we have to between 2 and 3 sessions in an hour. I separate them out. So the little half hour, 20 minutes, 15 minutes recordings. Here's an example of what we've covered recently over the past year, and just a little bit more detail, a little snapshot. During February of this year, our first presentation from JAXA. You've heard a bit from JAXA during this session. Yorishida-san gave a very thorough introduction into the JAXA Global Satellite Mapping and Precipitation Dataset. This included an example. You can see the example on the top right-hand side there, which was from a tropical storm over that region. That was typhoon number 7, Lan. It included the validation of JAXA data against surface observations. During the July meeting, Omura-san from one of our VLab contacts from our principal sponsoring satellite operator showed a great online resource that JMA have created. And you've seen that before, the 283-page online book explains how to utilize satellite data in analyzing clouds. Also, you'll notice that Zuzue-san, also of JMA, showcased JMA's rapidly developing cumulus area product, and more about that in the next slide. It's kind of the segue into convective initiation monitoring tools, and our previous colleague talked about one of these. Well, we've kind of we have additional convective initiation tools that have actually been developed by, in this case, JMA, the RDC8 product, but also we've illustrated Dr. Scott Lindstrom, who's in the audience here. He presented Lightning Cast during more recently in anticipating thunderstorm formations by utilizing machine learning. It's there. We've recorded it. Let me know if you're interested. You can download the recordings, listen to them, and get back to us if you have any questions. Of course, we've also highlighted this, AMSCC 14, in 2 of these meetings, just making colleagues aware of this event before time. We have at Christmas time, we'll have it again during December, a Kris Kringle. Everybody puts in their favorite case studies of the year. This was last year. So we had Yamada-san, the eruption, volcanic eruption of Mount Ulawan. We've had Jordan Girth, one of our champions, a fire event over Hawaii. We've had the Ella Marie Sorino from the Philippines, a cold surge over the shear line over the Philippines. We've had Rion Salman, a champion from Indonesia, MSCs over the Banda Sea, and we've had our own Scott Lindstrom there giving the tornadoes over Myanmar. So there's a lot of regional resources there. Recently, we have been collaborating with the new Indonesian VLab Center of Excellence. So in January, I presented my contribution was mountain waves over Tasmania. In April, we're looking at fog and low cloud, how it used to be detected, how it's detected now. In May, we looked at aviation turbulence event, and again, feedback from operational forecasters at the time. Ultimate street cred, straight from the coalface of forecasting. In July, introducing the flooding case studies. If you're interested in flooding case studies, we've got lots of them because we've had 122 meetings and 2 or 3 presentations at each. It's an encyclopedia. And finally, I gave a presentation of a sea and swell event affecting Australia using satellite data as well. Finally, I'd like to wrap up by just making you aware that the recordings are all on this webpage. This will be shifted over the next year onto a Moodle webpage. And I'd like to thank you.
Thanks, Bodo. We do have time for a question or two. If anybody has one, just put up your hand.
So this is.
Yeah, no,
Always
my voice will go. I just wanted, can we have some collaboration and we can have a VLab Center of Excellence in India too?
Yes, I fully agree with you. Already, Dr. Mitra's, we're going to have a meeting worked out. I've already sent, in fact, this morning, before breakfast, no, it was just after breakfast, I ended up sending out an email to Dr. Mitra just highlighting how we'd like to collaborate because we've got so many case studies. I mean, we've basically had the westerly disturbances amongst other things. These will make very useful first case studies that can be introduced into these sessions. But certainly, I'm going to have to wrap up this session. I'm going to have to do a summary of AMSCC 14, and that will be a WeLab session. I'm hoping IMD colleagues might be able to contribute either in resources or in also presenting themselves. I give people the options. I know people are busy, and so with collaboration doesn't necessarily mean that you have to present, but I can present on your behalf, but I would like to get material from you as well. So it's something, it's a collaborative endeavor. Thank you.
Thanks, Bodo. In the interest of time, we're going to move on.
Okay, now we move on to the next presentation by Dr. Garge. So she will explain. Good.
Good afternoon, everybody. I am Gargi Rakshit, working in the Satellite Meteorology Division of India Meteorological Department. Currently, I'm working with the observational perspective of the extreme weather events. And in this connection, I would like to present my work, atmospheric variability and predictive insights of lightning-related disasters in India, case studies, Orissa and Gujarat. Two case studies which are very much contrasting, I will be presenting. So it is needless to say that lightning is a spectacular and at the same time very dangerous natural phenomena which causes several and significant fatalities and injuries. And if we speak about the Indian perspective, it is mostly frequent during the pre-monsoon and monsoon season, when it is conducive for the development of the convective cloud. But here I will present two disastrous lightning events, one which occurred during September, that is during the monsoon time over Odisha, and over one Gujarat in November 2023. Before going into the research motivation, I would like to show the geographical scenario of the two study location. That is, one is Gujarat and the other is Odisha. So first, the lightning disaster is over Orissa. It occurred on 2nd of September 2023. Here I would like to add that over Gujarat, lightning is already declared as a state-specific disaster. And lightning is very much frequent during the monsoon season over Orissa. But contrastingly over Gujarat, especially during the late November onset of winter season, lightning is not that frequent. So it is an anomalous. So going back to the research motivation that I would like to find out that what are the associated atmospheric parameters responsible for these two disastrous events. The atmospheric parameters which is responsible for the lightning disaster over Orissa is same, whether it is same over Gujarat or not. So in my study, I have used the IITM lightning location network data along with the satellite data of INSAT 3D, 3DR and outputs of ERA5 reanalysis outputs. So before going detailed into the study, I would like to show some snapshots of the newspaper cuttings that it describe how disastrous the event was on 2nd of September that occurred over Orissa. 61,000 lightning strikes in 2 hours. 12 people were killed. And for Gujarat, it is like 24 fatalities were caused. What explains the unseasonal rain and lightning strikes in Gujarat? These are some of the snapshots of the newspapers. Now, what is the ground truth? This animation shows the hourly lightning strikes which occurred over Orissa during 2nd September 2023. And it is overlaid on the cloud top brightness temperature which is obtained from INSAT 3D. Here it can be seen that the magenta color patches are the sites of lightning, that when the lightning has occurred, the cloud top brightness temperature is very low. It even reached below -70 degrees Celsius. And the enhanced activity of lightning was during from 6 UTC to 10 UTC. And the dissipation occurred after 12 UTC. But the initiation started in the northwestern region of Gujarat at 4 UTC. Now, sorry, that is for Orissa, not for Gujarat. Now for Gujarat, the scenario was much more dangerous. The lightning initiated in the early hours of 26th of November and it occurred up to like 14 UTC and it dissipated around 18 UTC. And this is very, very anomalous because the time is around, that is 26th November 2023, and this time period is not favorable for the occurrence of these disastrous kind of lightning events over a state like Gujarat. So I have consulted some published result. This result I have taken from a paper by Yadava et al. Published in 2020, and it shows that during monsoon season, the flash density is usually high over Orissa, but during November period, the flash density is not so high over Gujarat. So indeed, it is an anomalous event for Gujarat. Now, this anomaly has been estimated from the IITM lightning network data for 26th November using 5 years of data we are having. And here a strong positive anomaly is observed over Gujarat for this 26th November event. So here I would like to add that lightning events are generally associated with thunderstorm and high atmospheric instability. So to look into the scenario that whether the atmospheric instability was high before the initiation of the lightning event, here the contour plots of convective available potential energy has been shown. And as I have already shown in my previous slide, that lightning initiated around 4 UTC over Orissa. So if we see the scenario of Cape around 2 UTC, enhanced patches of Cape over the lightning affected areas over Orissa is seen. So from this day, we can say that the Cape can be used as a precursor, as an indicative parameter for the impending or upcoming lightning strikes. But whether this can be used for Gujarat, let's see. Here, even if the Cape is high along the coastline of Gujarat, but the Cape is not so high over the lightning affected region over Gujarat, but it eventually enhanced during the lightning episode, but it cannot be used as a precursor for the Gujarat event. So I have investigated further of the scenario of the cloud microphysical properties. And here it is seen that for Orissa, enhanced patch of cloud ice was observed during that 2nd September. And as it was the monsoon time, the cloud liquid water was also high. And the cloud liquid water was high after that enhanced patch of that cloud ice was observed. So supporting this fact, we have observed that what was the scenario of rainfall. So the hourly rainfall was after the lightning event, the rainfall has been like we have experienced rainfall over Orissa. For Gujarat, it is seen that yes, enhanced patch of cloud ice water was observed, and it was at comparatively higher altitude, around 600 to 250 HPA, and the cloud liquid water was also high as well. And whether there was rain, yes, there was rain, though it was not that intense like Orissa, but it was high. Now, here, what we have seen from my previous slide, that yes, the atmospheric instability that is Cape, which is indicative of the atmospheric instability, it can be used as an indicative parameter for the impending lightning episodes during the monsoon season. But it is not valid for the winter season or in the late of post-monsoon season. So I have studied a deeper insight over the lightning catastrophe over Gujarat, which is very unusual. And it is seen that this is the cloud top brightness temperature from inside 3D, and the cloud top brightness temperature value, which is below -40 degrees Celsius, has been like indicated by this blue color, cyan color, magenta, and red color. And a clear impact and clear signature of western disturbance has been observed over Gujarat. Now, from where we are getting the moisture during this time, during this unusual time. Here I have calculated the vertically integrated moisture transport from the ERA 5 data, and it is seen that moisture incursion from Bay of Bengal and Arabian Sea has accumulated over Gujarat. And during the phase of moisture incursion, this lightning disaster has occurred. And over this, I am not sure whether the wind plot of 850 HPA is visible or not. Here, a cyclonic circulation over northern Arabian Sea is observed, and it has shifted over Gujarat, and it has created a very conducive environment for the incursion of moisture from the water bodies. So, it can be said that an unexpected interaction between atmospheric system, that is a cyclonic circulation over the northern Arabian Sea, resulted into incursion of moisture over Gujarat, where the intense lightning has occurred. And the western disturbance originated from the Mediterranean Sea brought unseasonal rainfall and thunderstorm. A part of this work has recently been accepted in JS, and it is under press. It will be available online soon. So I'd like to conclude that the study reveals that the cloud top brightness temperature can be used as an indicative parameter, because when the cloud top temperature is very low, it forms a conducive environment for the formation of cloud ice. But while CAPE, that is the convective available potential energy, is useful parameter for predicting lightning event during the monsoon season, its applicability diminishes during unseasonal event as observed over Gujarat. Such episodes often result from complex interaction between synoptic scale weather system and larger climate dynamics. Secondly, this investigation underscores the need of enhanced meteorological forecasting capabilities and the development of more robust statistical model to understand and predict lightning occurrences across the diverse geographic and climatic regimes like India, because India is not a temperate region. It is characterized by tropical climate, and we are having a diverse kind of rainfall. And finally, the findings highlight the critical importance of incorporating lightning sensors in our future upcoming satellite, which will be launched from India. And addressing these challenges could significantly mitigate the impact of lightning-related disasters, saving life, property, while advancing the scientific understanding of atmospheric variability and extreme weather phenomena. I would like to acknowledge India Meteorological Department, Director General of Meteorology, Dr. M. Mahapatra, sir. And I will also like to acknowledge IITM for providing the lightning location network data. Thank you. And any questions?
Thank you very much. Do I have time for a question or two? I'll ask one. Okay. I'm in the mid latitudes, and when I see a lot of lightning, typically there's also a lot of hail. And I wonder if there was any hail with any of these two systems, or was it just too warm?
Good afternoon, everyone.
Yes, sorry, sir, I couldn't understand your question.
When you have a lot of cloud ice and a lot of up and down motions, you can create hail. And when I've experienced in my country a lot of lightning, typically there's also a lot of hail. But I'm just wondering, as I was thinking that, I figured the freezing level here might be a little bit too high.
It is around 5 to 5.5 kilometers.
Okay, so it's just a little too high for the hail to make it down to the surface then. Yeah.
I have one short comment.
Yes.
In your presentation, you mentioned that the unexpected interaction.
Yes.
Between Western disturbance and something like that you wrote. Yes. But it is not unexpected.
It is expected, but the phenomena was unexpected. Yes, true, sir.
The interaction was expected.
Yes, yes.
If you see bulletin the IMD, they mentioned that
it is expected.
Because of from easterlies and western disturbance, there will be an interaction. Okay, and based on that, perhaps warnings were given, definitely.
Yes.
Adequate warnings were given based on that synoptic situation and expected scenario that will occur.
Yes. I will remove the word unexpected.
Okay.
Thank you, sir.
Yeah, I make next one. Okay, the next presentation is on analysis of extreme rainfall events using satellite estimate rainfall data set case study on monsoon 2024. You are here.
Good afternoon to all. First of all, I would like to thank organizers because I got very good opportunity to present here. So my topic is analysis of the extreme rainfall events using satellite estimated rainfall datasets, case study on monsoon 2024. So, introduction. High resolution satellite rainfall products are vital for real-time rainfall monitoring and nowcasting applications. Geostationary satellites provide an unprecedented cost-effective opportunity to estimate precipitation over a certain region at finer spatial and temporal scales. 4 distinct rainfall products are operationally generated in real time from VHR measurements of the satellite through multi-mission meteorological data receiving and processing system, MMDRPS, which we are using in IMD. 4 rainfall products are based on different algorithms, have different spatial resolution. Details of these operational rainfall products will be presented. In addition, comprehensive evaluation of these rainfall products are needed for their integration in any specific application and further improvement in the rainfall retrieval algorithms. Let's go. So subdivision-wise rainfall distribution in August month 2024. So there are during this month 5 subdivisions received large excess, that is thick blue is large excess, and 8 received excess, and 18 received normal rainfall, that is green in color, and 5 received even deficient rainfall. Then if you see low pressure systems that is formed in August month, past 7 years, if you see from 2017 to 2024, in 2024, we received so many systems during August month. 1 cyclonic storm, Asna, and depressions, 2 depressions, and 3 low pressure systems formed during August month, which is not there in previous years. And there are low pressure days also more in August month. And these are the systems formed during August month. So track of deep depression, that is on 2 to 5 August, and track of cyclonic storm Asna also is there, and track of depression is mentioned here. So in August month, there are actually 1926 occasions rainfall happened with more than 64.5 mm rainfall. In that, 105 were extremely heavy rainfall, means greater than 204.4 mm of rainfall. So these here red marks are shown. So those are extreme rainfall events, and blue, it is indicating very heavy rainfall, and green, so with a heavy rainfall. So you can see here extreme heavy rainfall events. There are a total 105 were extreme observed by observatories, and this is overall actual rainfall happened over Indian region during August month. Of course, from July onwards, the rainfall departures are positive departures are observed from July to up to end of half of the September. There's a good rainfall occur. This is all we got. Then number of heavy rainfall events during last 5 years, if you see from 2020 to 24, July month, generally, July month, we have more extreme heavy rainfall events. Of course, in 2020, 165 August month, it is reported. But if you see in 21, 22, all different years, in July month, it is more. After that, followed by August and September, June. Then impact due to extremely heavy rainfall, we all know. Like most probably here, I want to mention like flooding in riverine catchments usually happen whenever extreme heavy rainfall, if it is continuing in particular area. Then these are the satellite pictures. In August 3rd to 6th, low pressure area is formed. So this low pressure, due to this low pressure as well as depression, so it is indicating so much of rainfall. There only we got extreme heavy rainfall events as well. This is from 3rd August to 6th August, and this is 26th also. We have Asna cyclone. So during this time, these are the satellite pictures, and this is the track. So in this area only we received most probably more amount of rainfall, that is extreme heavy rainfall events. And this is also like what happened from May to September. Even SST also reduced, so that's why even quite rainfall amount also increased. And this is model based 3 months average from May to June, July. That is June, July, August, July, August, September, like that up to end of December it is shown. Then whenever these low pressure systems are there, means usually we will give this type of warnings. So wherever red warnings are there, means there extreme rainfall events possibilities there. And this is June month. So because I'm studying monsoon, so I'm going through one by one, month wise. June, these are the extreme rainfall events here happened, and there only flood situation also happened. So extremely heavy rainfall events are shown. There are 904 occasions. In that, 35 were extremely heavy rainfall events. And if you see satellite picture here, hydro estimator product only we have taken. Even hydro estimator also given. This is a daily one product, one image we will get, means a cumulative of whole 24 hours. This is the picture. Here also it is shown. So if you go through backside, here I have taken only one day there where low pressure is occurred that day, imagery. So if you see, I have taken, means I just mentioned only whenever low pressure systems are there, then extreme heavy rainfall event shown by our satellite observation as well as I'm comparing with surface observation. So in all cases, satellite observation is more and surface observatory observations are bit less. So here during July month, this is what extreme heavy rainfall events, and here flood situation also happened. And this is a satellite picture, hydro estimator, where it is showing the values. So red is indicating more than 30 mm of rainfall. That is all indicated here. This is rainfall occurred. And this is in August month, the same thing. So this is a hydro estimator, and these are the satellite observed rainfall data sets and real observatory observations. And then this is in September month. And this is hydro estimator rainfall. And this is extreme heavy rainfall events. Particular dates only I have taken. They in that days only we got low pressure systems. And these are the conclusions. With systems associated extreme events are more than monsoon trough associated rainfall, and reported rains are less than satellite derived rainfall. Satellite derived rainfall product picking all rainfall reported through observatories, and even more than is reported. Satellite derived product also may consider for verification of rainfall. This is just because wherever there is no observatory as well as radar observatory also not there we can utilize satellite. And overall, June to September, El Nino effect is reduced and rainfall amount increased compared with last 5 years. Neutral El Nino southern oscillation conditions developed in July and continued till September. I would remain neutral till end of August. Neutral El Nino southern oscillation conditions prevail. I would remain neutral So first half of the monsoon season, 2024 got normal rainfall. After that, above normal rainfall is recorded. Thank you. Is there any questions?
We have time for a question or two, if anybody.
Yes, please.
Hello, ma'am. My question is, what data you have used for the surface observation?
That is our IADP, means our IMD observatories.
And ma'am, my one more question. In the highest mountainous region like Uttarakhand, so deployment of ground-based network is not possible everywhere. So in the IMD press release, there is mentioned like district-wise rainfall. Suppose Dehradun, 225 mm is rainfall likely to occur. So ma'am, since we know that the deployment of ground-based network is not everywhere, so how much area rain gauge covers? Like, what is its range?
Actually, normal observatory range is 50 kilometers, but so that's the reason. Wherever such observatories are not there, then we can utilize satellite observation for some.
But ma'am, in mountainous region,
Yes,
like I have noticed and I have read several papers in which there is mention in higher elevated areas, it is like overestimate the rainfall.
Yeah, but in at that particular areas, you can somehow you will get from satellite observation. That much only I can say. Is even our AWS stations also there in that areas. Even maybe in coming years, radar network also will come at that particular areas. That is also there. So
thank you, ma'am.
Any other questions? Thank you.
So next presentation is on urbanization and climate dynamics modeling meteorological variability in Bhubaneswar. By Dr. Mishra. He has not come. He is not here. So go to next presentation. That's yours? Yes, next. Please go ahead. Next is on impact of shed over the Indian region using INSET data, a decadal study. Good afternoon.
I'm going to present this southern hemispherical equatorial trough. How it is going to affect our Indian monsoon over the Indian region. Is actually this set is the one equatorial line. 0 degree to 10 degrees south is the southern hemispherical equatorial trough is going to when it develops. This is the set, and when 0 degree equatorial to 10 degree north is a net. Means when set is developed below the equatorial line, then our monsoon is going to be when set will develop, means the monsoon is going to delay will be there over the Indian region, and one paper is there that Prasad paper is there in which they have defined set as southern hemispherical equatorial trough activity index that they have defined 1 to 20. They have classified the 1 to 20 if and in which one is for this means how rain is going to be if 1 to 2 means one is for rainfall is will go good over the Indian region, and 10 20 will be the drought condition will be the over the Indian region. I'll show that see, there are two things are there, NAT and SAT. When SAT is developed means it's not going to, monsoon is not going to dominate over the Indian region, and another is a convective zone of south result weak monsoon condition over the Indian. When SAT is weak, close to the equator means I'll go through the our wait. This thing. This is our satellite. Wait. No, sir. Yes, sir. Wait. It's not coming. This is our equatorial line where this when cloud is there means it will develop over the equatorial line, and when more cloud is there means SAT is going to develop, and what we have done, we have taken the satellite data and we find out the average of the weekly average of the cloud, and this cloud cover data block less than 20% cloudiness have been counted as cloud free, and this daily cloud data has been used to obtain the weekly mean cloud cover. What we are doing, that we are taking the cloud data or satellite data L1 bead, and then we are finding out the mean cloud every weekly, and then we are seeing the SAT is there or not. If SAT is developed means before we are checking out before the monsoon season, this 4 months, June, July, August, and September, and we will find the pre-monsoon, and this is our rainfall 2022 data. Here we can see in the June that rainfall is here in the June, and then July is rain was there, and then 4th July here we can see the good rain over the Indian region. These areas SAT was developed, then here rain is very in this June, and then July is rainfall is good. Here we can see that our equatorial trough, this cloud, if more cloud is there means this is 0 to 10, and then 0 to 10 degree of the south and 10 to north. Here more cloud is there means SAT is developed, here less cloud percentage is less here. Means when during monsoon time, when cloud will come from Mascarean height to and southeast, and then it will from equatorial line it will move towards the southwesterly monsoon, and then our cloud is very few. It's means cloud zone is freely here. Here is condensed cloud is there means here SAT is there. It will directly is going to affect the monsoon rainfall over the Indian region. Due to SAT only the onset monsoon over the Kerala region is going to delay also. Similarly, we have analyzed weekly data for this July and 3rd July to 9th July, and then 10 to 16. And similarly, we weekly cloud percentage, we find out the weekly only. Here set is inactive. This area here we can see that cloud set is inactive, means a good rain is there. Also here this is fully cloud free zone, means set is inactive, and here there is chances of good rain over the India. Similarly, we find out for the August month weekly cloud percentage. In this period also, that deep depression also formed in the Bay of Bengal, and the 19 to 23rd August over the Bay of Bengal, and third depression during the 2 over the Bay of Bengal and 1 over the Arabian Sea in that time period. And this is when set was developed over the equatorial sea here. Here the cloud was there, that this region. This maximum cloud zone, northward movement of maximum cloud zone, this thing is going to move toward the northward, and this cloud zone over the equatorial troughs, if this cloud is it's across the full equatorial line, means it's going to this maximum cloud zone is means confined over the equatorial trough, means going to bad monsoon over the Indian region. Similarly, we find the OLR, this above the 200, and then so already I discussed the develop. This is our study of the full from 1965 to 2022, and how much rainfall departure is given here, and we classify into different category, means like minus 21% to 25%, which year comes under. Like 1972, it comes under the minus 21 to 25%, and then 16% to minus 20%. Different we divide into different categories. Here that our this set activity index, we classify this in from 1 to 20, and if one or two means this is good for the rain, and 2 sign index value is the similar, and like normal. This is like 10 or 11, this is similar only, like 12 13 is similar. So 2 sign index is similar only, similar 1 to 21 means this is good. There is, if psi index is 1 means there is a good chances of rain over the Indian region, and 2 means it's going towards the drought condition. And between 10 to 13 means it's normal only. So how we psi index, we here 1 to 20 is there, classification is there. This is the one paper of this in which they classify the psi index, means southern hemispherical activity index, in which classify this suppose psi number is 1, means set completely absent during April. Means there is no cloud zone, maximum cloud zone is there over the equatorial line and northern hemisphere equatorial trough active in all week of the April and May. In May, night lies between the equator 5 north, and in May it shows movement northward, and May is up to 20 north. Similarly, when we move toward the side index like 14 to 20 is going towards the drought condition and less chances of the rainfall over the Indian region. We have find the correlation between psi and the rainfall. That I'll show the table. This is our Indian region for this. This correlation we marked for the between the psi and the rainfall over the Indian peninsular northwest India and two regions with the useful long range forecast. This we study the data to 18 to 22. This we find out the this monthly April May we find out the mean cloud zone over the equatorial for 2018 and we find the compare with the our rainfall like it's below the normal. Similarly for 19 above normal, and similarly for 20 and 2021 and 22. And this is the index of what we find out. And April to May before pre-monsoon. Last week April between 10 north to 10 south. Here we can see this much only is going to cover our this only few cloud zone is only few areas going to cover only. Set develop first week of May only. This comes under the psi the set activity index under 10. Similarly, we find out the full month like weekly, like first this is the first week, second week, then third week, then fourth. We plotted the visible count plot, average visible count plot over this equatorial trough. So our next plan is to this. We are going to this cloud. We are going to quantify. Means now you can see only cloud zone. You can see over the equatorial trough, and then we visualize the how rainfall is going to over the Indian region. Now we are planning to going to quantify this cloud zone, and then we can give one some quantity value that's a cloud. Then we can easily we can put into the machine learning, and then we can predict these things also. Thank you, sir.
We have time for questions if anyone would like to ask them. Nope.
Application now.
Okay, we can announce them.
Announce the quick. Next presentation is about application of FY satellites for weather analysis and forecasting from CMA by Quinn Bania. It's end of the So we come to end of the session, and I thank all the presenters for their nice presentations and further discussions during the question hour.
Thank you, Bhatia sir, and thank you, Scott. Now, for next session, session 5, first I want to confirm who are the participants are here. S59, Indian AF Saswat Kumar Singh. Yeah, first we will check from here. Civic Saxena, Civica Saxena. Then Jharna from NIT, okay. And the Rajate Temo, he already presented in that room. Morning, he was not well, so he has presented there. So the tea break is at 3:30. We'll take 5-minute break and then we will start this session early. Next session, we will start 3:10. Yeah. Session 5, application for weather analysis. We'll request everyone kindly after 5 minutes, we'll assemble here and we'll start the next session. Thank you.
Hello. Hey, good afternoon, everybody. Sorry to cut off your conversations, which I'm sure are very interesting, but we're going to move on now to session 5, part 2, which is the application for weather analysis and nowcasting. My name is Ben Churchill. For those who didn't see my presentations or introductions yesterday, I'm the director of the WMO Regional Office for Asia and Southwest Pacific, based in Singapore. It's my pleasure to be one of your chairs for today, and I'll hand over to the co-chair or allow you to introduce yourself.
Yeah, I'm Dr. Neeti Singh, and I'm from IMD. So we'll start this session.
Thank you very much, Dr. Singh. So we actually have a shorter list of presenters today, so we're going to be moving quite quickly. We're actually starting ahead of schedule. So just a bit of a heads up, we're also planning to merge session 8. So after the presentations which will follow, we'll bring the other group into this room for a bigger audience and to continue the presentations. So without further ado, I'd like to just actually ask, do we have Shashwat Kumar Singh in the room? Yes, we do. Great. So Mr. Singh will be delivering a presentation on a data-driven approach for precipitation nowcasting for aviation application. I see from your uniform you're with the Air Force. So yes, thank you very much for coming, and we look forward to your presentation. Thank you.
Can you please load my PPT? Excuse me, can you please load my PPT?
Yes.
So good afternoon, everyone. Today I'm here to present my topic, which I have done this work in the collaboration with ISRO. And this work is mainly done to ease out the problems which we face during especially the low altitude missions, which are basically done during extreme weather events. And we have seen in the past that many events have happened where Air Force has pitched in and where the situations are not conducive, but still we have to perform, and we have gone and we have delivered. But we are here to understand the problems which we generally face and how we can resolve them. So if we will have a look that what are the major characteristics of the air operations, especially when we do during the hostile situation or extreme weather events. So all these operations which are basically done during the severe events are basically quick and very short operations, and for that we need very precise short-term forecast. On that basis, the pilot will go and deliver their particular task on the ground. And at the same time, when this kind of situations are there, we don't have any options to wait for the clear weather activity, because as soon as weather are little familiar to us, we generally go and complete our task. So we want the real-time decision making that has to come from the meteorological officers which are there in the Indian Air Force. So this particular thing was done by me to help that forecasters who are going to tell the aviators whether to go or not. So at the same time, a lot of training is also being done in the especially low flying activities, especially during training time, where cadets who are not very familiar with such a situation, at that time also this particular precipitation nowcasting going to be helpful. So what is the necessity for this? So first is that we want the quick, accurate, and the short-term prediction, especially for the HADR operations, where we have to go and evacuate people, help people during the extreme events. At the same time, we want the mission-specific short-term weather predictions. So what is the need? I know if you go on the internet, you will find a lot of information about the meteorological domain, but all is available over a very, you can say, on the background, you will have either some map, or you have some topography map, but we want to be very specific that in which zone, which valley we are moving in. So there is a need to overlay this particular information over the ATS routes or the control airspace, so that we will be very confident before going to for any task. So this was the idea behind doing this work, and then it was been the objectives were decided on that basis, and we can see that the objective was how we can generate the precipitation nowcast, because most of these problems, most of these situations will generally come, especially in Indian subcontinent, when there will be a heavy rainfall activity for a prolonged period, or there is a microburst activity. So considering this situation, these objectives were decided where we wanted to test the model, which uses the satellite raw data or radar raw data, and then it will give a nowcast for the next 3 years. And also we wanted to see validate the nowcasting capability of the model, which was done. So our coverage, the study area was taken. First was for satellite data, all the entire Indian subcontinent, and for radar data, only the Trivandrum radar, which was available to us. So that's why it was done for that area only. So basically the 3 data were used. One is the insect 3DR HM data, which is readily available on the MOSDEC, and then the radar data, which is also available on the MOSDEC. But the metadata for the validation, we have our own repository of metadata. So where we have data of every half an hour, which uses this particular thing for the validation. So I have used this PyStep framework, which is a Python based. There are a lot of modules which are basically given in that, where first it does the extrapolation, then after extrapolation, since we are dealing with the weather systems, so we cannot, 2 weather systems can behave in 2 different ways. One can grow, one can dissipate. So in order to cater all these things, they have a concept of scale filtering, where what it does, depending upon the DBZ, it distributed the complete domain of the coverage of the data into different scales. And then also it gives for the ensemble, because in order to cater the chaotic nature of the weather, they have the provision of this stochastic perturbation, where we used to change the particular variables, maximum 21 variable, and then we can generate the ensemble nowcast also. So the methodology for 2 different is given in this particular flowcharts for satellite and radar, where what we are generally doing, we are training the data set from the last 3 hours, and then we are generating through the model, we are generating the results. So in order to test this particular model, what we have done, we have taken only heavy rainfall events which have occurred over the Trivandrum region, and this is the data which we have collated for 2023 year. These are the 4 times when Trivandrum has recorded more than heavy rainfall, more than 64.5 millimeter rainfall. Here we can see this area and this the case, and here on the right we can see how the weather has been recorded on 1430 written result. Then it was improved, especially how the weather has behaved over that particular day, over that particular location. So we have generated the nowcast, and when we have using this model, and we have compared also the actual data, we can see that it is very beautifully capturing the overall movement of the synoptic system. And at the same time, when we are seeing the radar nowcast, we can see that we can match the timings above and when the weather has improved. So here it is without any ATS route imposed on that. Just I put the location of the location where the data has been collected, that does radar, and then we have just put the generated the nowcast for the next 3 hours. And this nowcast will be again generated after 15 minutes when the data will come. So there will be no issue of whether the dynamics, what is happening in the atmosphere. After whatever happening, it has been recorded in radar, then this particular model will start working. So the next comparison also of radar, also we can see how this actual radar system has moved and what we have generated. It is majorly capturing the spatial extent of that, and that is one of the good indication as far as the operations are concerned. We know how much time this particular system is going to be there over that, and accordingly we can shift our time of launching of operations. At the same time, one more case where they have received extremely heavy rainfall, where 211.4 mm rainfall has been recorded. For that also, the model is predicting is capturing the spatial distribution is very well captured. We can see what this is the actual radar image and what this we have generated for next 15 minutes, what we are capturing. So we wanted to test this particular model. So what we have done, we have calculated some confusion metrics. We had done a calculation of critical success index, POD and HSS, as well as the false alarm ratio. All these indices were calculated for this, all these cases. So these are the for the satellite cases for all the 4 cases, and we can see the POD is more than 0.6, 0.7, and that is what we required. And for radar also, the POD has increased significantly because since we know that density of this radar data is much better than satellite, so we are getting more than, and the false alarm ratio is very less compared to what we used to get in WRF models output. We have so here also we can see I talked about the different scales. As soon as we are increasing the scales like of that particular domain, we are getting higher probability of detection in false alarm ratio, and as soon as the time increases, the reliability decreases. That is the case for every forecast. So this is just an example. So what we have done, we have just superimposed the different air control routes, and we have superimposed the nowcast. And now we know if I'm sitting here and I have to decide about any mission, we have to wait for 1 hour. Since that this particular system will move on, and then we can see. And we can launch it accordingly. So that will be a very prior good information for us. Can you please click, excuse me, can you please click on this link? Can you please click? Yes. So just to integrate, we have developed one WebGIS platform where what we are doing, we have put the overlays of all these air routes, and above that, this HEM nowcast is there. And for the next 15 to 30 minutes, we have overlays. If anybody is interested, he can how this particular movement is going to see. And for the development of this WebGIS platform was the only region here we have a capability of zoom in. I will show how. Let's say if I am interested in seeing the Trivandrum and what is going to happen, which routes it is going to affect, I will get a fair idea that how it is going to be affected by this particular system. So here in this way we can zoom in over this. And we can put any information as a save file over this particular platform. We wanted roads, networks, anything we can put. Can you please close this? Yes. Next. So my conclusion is that after doing all this thing, that this model is very fairly predicting the weather is fairly good. The POD is more than 0.6, and for radar is more than 0.7. The verification also indicates very good, very less false alarm ratios, and as well as this particular WebGIS portal is very helpful as well as the decision making is concerned. These are my references. With this, I'm finished. If you have any questions.
Well, thank you. Thank you very much, Squadron Leader Singh. We will call you by your correct title. I found that very interesting, and we often are faced with extreme weather, but one thing we don't actually think often enough is the first responders and humanitarian assistance, and we need to have them in very safe conditions. And so this is a very practical application that you've developed with the available technology, and I think this has many applications, not just within the Air Force and humanitarian, but across the region and the world. So congratulations on the presentation. Thank you. I will open up for any questions.
I want to ask one question. Is this tool openly available for users?
No, ma'am. This we have developed with the collaboration with ISRO also. So I was in CSTEEP program. So I took this project and worked on this. With the help of them, I have developed this.
Okay, and radar data, which data you have used in this?
Tells radar data, MOSDEC.
Which product you have used? Radar, which?
MAXJET.
MAXJET. Okay, and for training, how much data you have taken?
Only 3 hours, past 3 hours data.
For training?
Yes.
Only 3 hours data.
Because this particular algorithm works on the optical flow algorithm.
Hmm.
So you can give more, but 3 hours is the minimum which you can give. So you can give for 1 day also, but since the output we are getting in the less data, we have tested for that also, but it is very well performing for the last 3 hours. Since it is updating every time, after half an hour that one file will go, again the new file will come. So six set is very latest only. So from there it is, because if you will go for, since we are dealing with the weather, if you will take more data earlier, then there is a possibility that some weather activity was there, it will capture. So we, whatever in the system currently happening in the weather, we are only capturing and we are telling where it is move. It will move.
It means you're considering last 3 hours data and that input
So for satellite, it will be only 6 data.
Yeah.
And for
Half
radar,
of
it
the-
will be 12 data.
Okay, thank you.
And just a follow-up question, just to clarify, so this tool has been developed for use by Air Force and other.
Currently for Air Force only.
Yes, so it's not a publicly available service, right? Yes, but let's just maybe imagine that it could be. Obviously, there are sorts of considerations there, but I found it very, very inspiring and interesting. So thank you very much. Any other questions? Yes, we'll take one more. Sorry, just for the online.
Actually, Airport Authority of India is asking us to IMD, India Meteorological Department, to develop something like that. Would you like to collaborate with IMD?
Definitely, sir. You can take a part of ISRO also, and no issue, sir.
Because we can go ahead on this collaboration.
Yes.
Okay,
Because we
thank
face
you.
this issue on ground, so we developed this. We have that idea. You are most welcome, sir.
Thank you. I think you've asked the question I want to ask and you've given the answer I wanted to hear. So thank you very much. Okay, so round of applause again for Squadron Leader Singh. Thank you so much. Okay. Collaborate. That's the key word. Would you like to
So
introduce?
now I would like to announce now the tea is ready. If the usual our time is 3:30. So what you will suggest, can we go for tea and then later on 3 presentation is there? So based on your wish.
I agree.
Okay, then we'll take the tea and after
We all
15
need to have
minutes we will
a
be here.
health break, stand up, talk to each other, but please resume in how many minutes?
15 minutes.
In 15 minutes. So at quarter to 4,
3:45.
3:45. Thank you. We'll see you back here then.
इधर देखिए कुछ बोले एक्सप्लेन करें कुछ national policy. ठीक है Okay. Maybe.
So I'm just a bit concerned that time is slipping away, but I'm also concerned that we haven't got enough people in the room. But what I do want to check is whether we have the next presenter ready to go. We do. Great. I think we might kick off and then allow people to drift back into the room. We have 3 presentations left in this part 2 of session 5. The next one is from Shivika Saxena. No. Reschedule.
Industry, manufacturing,
Is the next one.
That is what
Right. Okay. Okay. So this is happening live as we speak. Very good. I'm happy to allow you to take the podium, but can so which presentation? Okay, I think that's coming because we had to do these first. And then...
That was
right.
All I got from Dr. Vipi. They have made this rescheduled and they are told we are merging with the session.
Yes, I understood that we were merging these session. Yeah. Yes. Maybe we could just wait a few minutes for Dr. Niti Singh to come back,
Yes,
and then
yes.
we can clarify.
Sure.
Okay. So we'll just resume in 5 minutes when Dr. Singh is back. Thank you. Is Shivika in the room? Ah, very good. Are you happy to wait for a few minutes? Well, good afternoon, everybody. Welcome to what I've just labelled the mega session. So we're going to merge two sessions together into one room. So we have a bigger crowd, we have more presentations. It's going to be very exciting. There'll be people coming in during the presentation, but to keep things on track, we're going to make a start. But just to explain, we're going to put a temporary pause on session 5, part 2 on the weather analysis and nowcasting. We're going to shuffle things around a bit, so bear with me. So next, we're going to have a presentation from Indian manufacturer and service providers. And so that's coming up now. And after that, we're going to flick across to session 8, performance and calibration of satellite instruments. And then we're going to loop back to where we were before to finish off session 5, part 2. So get comfortable, get excited. And I'm now going to pass the floor or invite to the podium the presenters. So perhaps, I'm sorry, I don't have your names on a list. So when you get to the podium, could you just introduce yourself? Thank you very much. Yes, please. The floor is yours. Thank you very much. Enjoy.
Could we have the presentation, please? Sure.
It's motivating every day you work in space tech, but there's a different level of motivation when something you have put will go up there in space, capture images of the Earth, and then hopefully we can use that to make the world a better place as well. Excel is in the business of Earth observation, and our first set of satellites are built around core component of a satellite that is called hyperspectral imagery. We started actually 3.5 years ago with only wanting to do analysis of satellite data. And while we were working with these data sets, we realized that yes, they're good for a lot of use cases, but there are so many things that we need to be seeing about our Earth's health, about the phenomenon that's occurring around the globe that you can't see. Hyperspectral collects data across multiple bands of the spectrum. which means you get multiple levels of information of a given image that you take off Earth. And the analytics that goes behind looking at these images allows us to help the agriculture industry, the oil and gas industry. It will allow us to better predict crop health. It will allow us going ahead to make sure that we are aware of what kind of pollutants are present in what kind of regions and try and be on top of issues as and when they occur or even before they occur. The short-term vision is utilize the satellites that go up and the hyperspectral data that comes down to create a health monitor for our planet. And what that means is to be able to see how things are changing globally, how these things are going to change in the future, and see if we can predict certain things so that organizations, governments, people can take better decisions to make the world a more better and sustainable place. When we look at the technology that we build and the kind of impact that it can have on ground, it in itself is a big source of motivation for everyone at Pixel. We have to go ahead and solve problems that are not being solved right now. India is something of different service when you live and people know that the role is actually going to be impactful. That makes a difference. 3, 2, 1. It's just like liftoff, transfer.
Hi, everyone. My name is Kshitij Khandelwal. I am CTO and founder at Pixel. And let me start by saying that it's an honor to be here in front of this audience, the experts and luminaries of the world of meteorology and meteorological satellites. We draw a lot of inspiration from the work that happens in the scientific domain to build our satellites. And I would just like to start by talking about what we do at Pixel and how we see ourselves playing a role as an industry partner in today's scenario and as the world gears up to look at climate change as a problem. Again, it's not a very technical session, so I apologize to come here without a lot of numbers and graphs and charts, but I'll try to keep this as something worth your time. I don't really need to preach to the choir over here, but the impact of adverse weather conditions is very well known. It leads to loss of livelihood, whether it's Puerto Rico or Assam, if there's a flood, if there's a hurricane, if there's any sort of issue that impacts the geography at a massive level, it will lead to an impact on the livelihood of the people. There's destruction of critical infrastructure that takes years to build, that takes millions of dollars to build. And of course, it has a very deep economic impact that the region struggles to get out of for years and years. So when we look at remote sensing as a solution, as something that helps with understanding the impact of adverse weather, it's not something new. It's been happening through people like you for the last 20, 30, 40 years. And we have seen the impact that an early warning system can create on a farmer. I come from a place called Akola. It's in Vidarbha, Maharashtra. For those of who that know the region, it's a drought-prone region in India. Lots of famines over the years, and the quality of the crop. There's a lot of crop failure basically that happens in the region, leads to farmer suicides. Hailstones happen one good season, and I've seen hail happening, and farmers don't know what to do. It leads to destruction of crop. You get into the whole mess of crop insurance, and it's just a very, very difficult scenario for regions like that. And it's obviously not the only region in the world that faces issues of that caliber. Globally, with the impact of satellite imaging, with the ability to forewarn people, with the ability to predict what's going to happen, and if not predict, at least assess the damage of what has happened, build the right measures so that the next time there's an adverse weather event, we are able to build strongly for it. This is an image from ISI, one of our colleagues in terms of the space industry. The images that they've built have been able to detect flood impact assessment at a very detailed level at different parts of the world. We ourselves have built satellites that have taken images of some disaster-prone areas and seen how the impact of those images have been. Some of the sessions today have also mentioned this, but as we look at the weather satellites of tomorrow, we realize that there is not as much need to put, or for lack of a better word, cram as many payloads as you can into a single large expensive satellite that takes 7, 8, 10 years to build, and then build it for 20 years, have the budget, have a behemoth budget to build those satellites and operate them. Because over the last 15 years or so, there's been this revolution with smaller satellites coming up and taking that mandate. The revisit you want can come with lower Earth orbit satellites. If they're very small in size, you can make a lot of them. The cost of sending a kilogram of anything into lower Earth orbit has gone down from about $30,000 to $35,000 10 years back to something around $6,600 as of last week. And it allows you to do much faster manufacturing deployment. When we look at building these smaller assets, we are looking at building cheaper assets. We are looking at iterating over multiple assets in very, very rapid steps so that you can get to a perfect payload very quickly. And in general, it also de-risks the entire mission, the entire project that would otherwise go on for 15, 20 years. Obviously, you can't beat physics. Aperture sizes have to stay big enough for resolutions, good resolutions. You have to keep cooling the systems. You have to build the payloads according to the requirements of the mission. But in general, if we look at optimizing the system for smaller satellites and many small satellites, it allows us to de-risk the system. And obviously, as these satellites go up in low Earth orbit, it becomes more of a global system than just a localized system that's generally in the geostationary orbit. So this first and foremost creates the ability to share data between multiple countries. And second, it also allows up and coming countries that may not have the resources, the agencies, the history to build large, multi-payload systems to do it in a smaller, much faster manner. Coming to Pixel, we build hyperspectral satellites. So when we started back in 2019. And I'm an electrical engineer. My co-founder, Aves, he's a mathematician. And neither of us were experts in remote sensing. We had no idea how to build remote sensing satellites. So we started looking at satellite data. And we started realizing that you need a higher quality, more scientific data to come into the commercial domain for people to create day-to-day impact. And a lot of free data is available. Sentinel at that point of time was our benchmark for higher resolution multispectral data sets. And we're looking at the impact of it in agriculture. We were looking at the impact of it in climate, energy sectors, forestry. And we said, what are the type of payloads that the world will need 10, 15 years from now? And that's how we centered on hyperspectral imaging. We're looking at a bunch of companies doing it from drones. And the idea was to see if we can do it at a commercial scale from space. I'm not sure how many of the people here are from NASA or NOAA, but obviously Hyperion and EO1 allowed us to think of the payload in that manner. As of now, we are launching 6 satellites next year. And the idea is to have daily global coverage. We want to get down to a resolution of 5 meters, which means these are satellites with decent apertures. They go from 0.4 to 2.5 microns. So the idea is to do visible, near, and shortwave infrared imaging in about 200 plus bands. And the idea is to take it to the level that Planet currently has its satellites at. Even though obviously there are questions about calibration of the data and the quality of the data coming into picture. At a macro level, having a daily revisit, having regular imaging at 5 meter resolution allows you to identify changes at an unprecedented level. For those uninitiated to hyperspectral imaging, it's essentially the electromagnetic spectrum imaged in tiny wavelengths. So instead of taking wide bands of the EM spectrum, as you would in a multispectral or a pan-chromatic system, you try to take minute bands and you try to identify the spectral signatures of different chemicals on Earth. In that regard, our goal since day one has been the same. We want to build a health monitor for planet Earth. We want to be able to understand what the problems are. To do that, you need to be able to see what the problems are. And we are poised to essentially detect, monitor, and predict changes around the world at a very high level of detail. Hyperspectral imaging is what we've started with, but as we move ahead, we would like to bring in multiple payloads into our constellation so that we can build our goal of having a health monitor for the planet in a very comprehensive manner. This is one of our first satellites that was deployed on a Falcon 9. So we said, okay, fine, we don't have a lot of money, we don't have a lot of time. What can we do to start with? So we decided to start with a 30-meter resolution hyperspectral payload, invisible near infrared. And we essentially had a different concept. Instead of using spectrometers, gratings, we moved to having filters applied on the detectors themselves. And it was proven in the biomedical domain. There were ground-based detectors of this quality, but no space detectors, space-based systems that did hyperspectral imaging with Fabry-Perot interferometers on them. So we said, okay, fine. Let's see if something that exists on ground can be taken to space. We started with our 30-meter payload. We built 2 more demos, scaled it from 30 to 20 to 10. And over the last 3 years, basically, we've launched these 3 demo satellites. We have a multitude of images from them, and we were able to sufficiently say that the data has a decent commercial quality. This is La Croix in France. I'm quite sure a lot of you would know this as a calibration site. I apologize if it's not being rendered in the best of ways on the presentation, but this was first light for us. So obviously you start with taking calibration sites. We then started looking at different areas. This is Abu Dhabi. We were trying to take image for a manufacturing company that was looking at one of the industrial areas over there. These are false color composites, but essentially this is our new generation of satellites that we're building. It's called the Firefly. It's going from our history of 30, 20, 10 to now 5 meters. We've established that this is exactly where we see the commercial gains. And it kind of continues the history of rapid eye satellites. It ties into the Sentinel data as well, which is at 10 meters. So scaling it down to 5 meters at a hyperspectral level is a big addition for a lot of our customers. As you can see here, we do everything in-house. So everything from assembling the cameras to assembling the satellites, to designing the satellites, manufacturing, everything is taken care of from start to finish at Pixel. Obviously, we don't build every single part ourselves, but we have a very, very healthy supply chain that allows us to do that. And this was a picture taken a couple of weeks back. We built 6 satellites over the last 2 years, and we will be launching them soon. So 16th of Jan on the transporter mission, and 1st of April, thereabouts, on another SpaceX Falcon 9. I think just coming down to our capabilities and why we are presenting in this conference here, we do believe that weather satellites are the next evolutionary step for us as a company. We have seen the capabilities at a hyperspectral level. In fact, we put our own money, venture capital funding that has come to the company to do a lot of R&D on the detectors, to do R&D on the systems. And we believe that, the precedent that's set by companies like Tomorrow.io or Spire shows that the capabilities that small satellites have in this domain is very, very high. So we have a huge clean room in Bangalore. We can pretty much build about 24 satellites in a year. Throughput in a year would be about 24 satellites. These are not gigantic ton-class satellites, but I would probably put their mass around 200 kgs a satellite. The idea is to use our constellation to have daily global access. We're getting NOAA licenses for all of our satellites. So we want to ensure that we sell our data in the US. In fact, we were recently part of the NASA CSDA. So the idea is to provide a lot of this data for scientific applications. And as they launch on 16 Jan, we hope that most of the people here would love to take a look at the data, give us their feedback on how to improve the systems, and work ahead. We've been able to do a lot of it because of the contributions of the scientific community. So we readily look forward to it. Coming down to the specifications, we build these hyperspectral satellites at 5 meters of resolution and 40 kilometers of swath. So we did not really want to compromise on the swath of the system so that we could build more number of satellites, but not have to have a large constellation to do global coverage. As of now, the capabilities are visible near infrared. We're launching a short-wave infrared satellite next year. As some of you here would know, the sensors have a slightly longer lead time. And we are essentially looking at 200 to 250 plus bands on the entire system. Just trying not to repeat things, but we've also figured out the image processing side of things at Pixel. So we not only do the payload integration, the satellite development, the launch, but we also operate these satellites ourselves. We generally don't build and sell satellites to others or build and sell payloads to others, although we are now open to it. But the idea is that the end-to-end chain of everything from the person deciding the detector to the person working with the image exists at Pixel. So it allows us to understand the deficiencies of the data, basically working to understand how different noises creep into the system, maintaining good SNR, maintaining good geometric calibration, which probably is the most difficult piece of the lot, is quite important. So we have an automated pipeline that does level 1B, 1C, 2A images. This is the Sentinel standard that we've copied, given that a good chunk of the world uses it. And the idea is that we should be able to offer any image of the Earth within 24 hours. So we have built the system so that it can deliver at a very rapid pace as well. If our licenses allow, we could do that in 6 hours as well, but I would like to keep our commitments in the bounds of our licenses. We also have a platform called Aurora. So when we started, we realized that we were working with a lot with ArcGIS, we were working a lot with NV, and it became a slightly, I'll skip the team part, I'll come back to it. But essentially, we were trying to work with different platforms, and it came to a point where we realized we needed very specialized people to work with these platforms. And for some of the applications that were a bit more simplistic, it became a tedious job to work with them. So we developed a Earth Observation Studio. It's a pretty simple web interface that allows you to analyze spectral information. So you can work with different indices, create your own indices for different applications, compare between images of different dates. We have this active. We also host a bunch of Sentinel data on the platform. So please feel free to reach out to us to test it out. But essentially, if we look at the existing ecosystem of geospatial analytic solutions, we realized that that was just very, very fragmented, and we had to work with a lot of different solutions. So this came purely out of us being very inconvenienced, and we decided to build Aurora as a platform to do that. We're looking at hosting more data. So as scientists look at working on applications that not only require space-based information, but ground-based information, if someone's doing surveys, if there's soil moisture data, if there's any sort of ground-based data sets, we've built it such that multiple workflows can come into picture. You can look at satellite data coming on a regular basis, going into your workflows, working on machine learning models that you have developed, or maybe we have in stock, and getting outputs as histograms or images as you wanted. I will not harp about the capabilities of the platform, but I do want to talk a bit about our manufacturing capabilities. As I mentioned earlier, we've recently gotten into contract satellite manufacturing. We don't want to make your typical run-of-the-mill satellites. Our aim always has been to build the best-in-class satellites and bringing those technologies down to a form factor that allows us to build it rapidly, to do it quick, obviously within the bounds of physics. As of now, 3 in space, 7 more go up next year. And these will be the highest resolution hyperspectral satellites ever sent to space, unless the US DoD has some that we don't know of. And these are also India's first ever private imaging satellites. So this is what we've been doing the last 3 years. The company's been up for the last 5.5 years, and we're poised to deploy a constellation of 24 satellites in the next 2. Coming to just the expertise that we have, the team is at the moment around 223 people as we speak of. 223 people as we speak of. That includes, and that's not just in India, it's a cross-border team. We have engineers, scientists in the US as well. We have some people who worked with JPL before. We have some people who worked with Maxar before for geometric calibration. So we've tried to really pick the best possible people we could find. The team can do anything and everything from building cameras to satellites to analyzing information and having a platform that turns this big data into actionable information. That said, we've also been fortunate enough to have some amazing advisors. Dr. Shanti Rao at NASA JPL has been advising us for a while and is also an investor in the company. Dr. Samudraya, some of you may know him from SAC Ahmedabad, has been a beacon for us as well. And as far as investment goes, like I said, we never really depended on contracts to get started. So we've raised investment from what I would say are some of the most comfortable investors to raise money from. So we've been able to raise 100 million over the last 5.5 years, and that funds us for our satellite constellation. So all the non-recurring piece, not the mission-specific non-recurring, but setting up a facility, having a team that knows how to build things has been taken care of in this channel. In terms of the programs that we're working on, we recently received a grant from IDEX. This is the IDEX Prime Challenge for building a multi-payload satellite bus. We are building a system with a hyperspectral camera from visible to short-wave infrared. And we're putting a mid-wave infrared camera on the system as well. So these are two payloads that will fly on the first prototype. We're looking at bringing in synthetic aperture radar in the next few prototypes of the system. We are also pursuing other opportunities with the Ministry of Defense for their IDEX and Make in India challenges. Apart from this, we've been providing our demo satellite data to different agencies, different companies for the last few years. When we started building these satellites, we never thought that, okay, this is the demo satellite, we're going to sell the data from this. But because of the interest that's been there, the limited data that was available has been provided to multiple agencies at this point and universities as well. So if you are interested in analyzing it, working with it, comparing it, we're more than happy to provide it. Apart from this, there's a lot of work that we're doing with NASA and NRO at the moment. And we were also winners of the Maritime Oil Spill Challenge Award that happened in the US and India. I think these are just some of the studies that we've done so far. So we were working on doing some oil spill detection using Aurora, the platform that I just spoke about. So the idea is to use all of these platform capabilities at different levels. This is also a segment where a lot of our customers are, whether it's energy companies or mining companies. They not only use it for just doing right-of-way monitoring or doing an understanding of oil and gas leaks, or if there's any sort of pollution, tailings dams that are coming up, but also for exploration purposes. And I think just coming to the topic of satellite-based metrology, this was a picture that we took with Somnathji, he's the chairman, ISRO, and we've recently set up our facility. It's been a year. We've built the first 6 satellites over there. And I think as we move into the next few years, we understand the challenges that the world faces with climate change. We understand the need to be able to monitor our weather, essentially. And we recently proposed multiple concepts to the IMD. This slide just shows the evolution of the type of payloads that we're building. So our hyperspectral sensors have been validated in space. We built the highest resolution hyperspectral satellites. They are going up a month and a half from now. We're actually flying to Vandenberg to integrate them a couple of weeks later. Then we are moving to expand our EO constellation from just 6 satellites to total of 24 satellites. So 12 to 18 more satellites will be launched in the next 2 years. That leads us to have sufficient enough capability to build bigger telescopes. So looking at aperture sizes more than 600 mm, we are looking at working with more exotic materials, more exotic detectors, and that's something that we're quite excited to do. I think this is just a summary of some of the concepts that we try to propose. The inspiration has been the various meteorological satellites that have gone up over the last 10 years or so. And from sounders to imagers to scatterometers, I think the capabilities that we are proposing here are going to be game-changing if applied as a part of the constellation. Just coming to the constellation itself, we've proposed two configurations over here. One is a configuration that focuses on a higher resolution and a more global coverage. So we've just given the satellites a moniker of Vayu after the god of wind. And the idea has been to build a constellation of 4 + 4 + 6 satellites, all in the lower Earth orbit with different types of payloads, but primarily scatterometers, 4 satellites with scatterometers, 4 satellites with sounders, and 6 imaging satellites. We've done an analysis of how this constellation would look like, but essentially the idea is to provide a very, very regular coverage over India. So if you look at the presentation, we are looking at providing a 3-hour revisit for the scatterometers and sounders and a 12-hour revisit for the imaging satellites. The second configuration that we're looking at has a much faster refresh and a more localized coverage. We're looking at 2 larger geostationary satellites and 4 lower Earth orbit satellites for the scatterometers, because you can't really put them for geo. And over here, we're looking at a refresh rate of 3 hours for the scatterometers, same as the previous one, but a 20-minute refresh rate for the imager and a 1-hour refresh rate for the sounders. Again, this is just some of the analysis that we've done. Yeah, this is just more news. This is a picture of our integration facility that we opened last year. And that's it. Thanks a lot for your time, for patiently listening, and I'm happy to answer any questions. Just checking if there's any questions or any doubts. Yes, sir.
Thank you, Shirish. I think it's an excellent presentation. Configuration which you have shown is really remarkable, and I think that is a required of for weather agencies. Particularly, if I can make out the hyperspectral and all those things, they are really, really great, because they do not have they're not only having an impact on day-to-day forecast, but also in weather forecast in the NWP model. But now the concern is that because since the data is very high quality and very large amount of data we are receiving, the most important part for the weather forecaster is that retrieval products. So somehow I have not found any retrieval products. Means how we are retrieving the atmospheric products, say OLR, QP, or vertical profile of the atmosphere, temperature, humidity, or carbon or emissions, whatever. So the retrieval part plays a very, very important role for us, whether it is a temperature or it is a wind or whether it is whatever I have mentioned. So we are looking forward to see you soon from that end. Yeah. And that could, I think, would be the best part of it. And then second, nowadays the satellite agencies are also making their payload in accordance with the AI ML techniques. Mm-hmm. So in ESA, we have seen that some of the techniques, they are putting the AI ML into the payload itself. So whether we are, you are also looking up to that, or India can also see in that perspective that your AI ML technique will be applying on the payload itself. So this is my question. Thank you. But your presentation is very nice. Thank you.
So I think just to talk about what we're doing on board the satellites, this entire chain from raw data to L1B, L1C, and L2A also exists on the satellites. But again, the accuracy of that chain is impacted by not having access to ground data. So some of the earlier corrections we do on the satellites. We also have enough compute to accommodate models in the future. So we do over there firmware updates on the satellite. And there is the capability to deploy, let's say, a segmentation model on the satellite or a model that can do target identification. The requirement is not just for weather monitoring, also for defense, where they don't want to deal with a lot of data. They want to deal with concise information. So the hardware has the capability. And as we go to launch 6 satellites next year, it will be a litmus test in seeing how much we can, reduce the amount of unnecessary data that's coming down and focus on getting concrete information from the satellites. But to answer the question around using machine learning techniques on the satellite, on board the satellite itself, the compute is there, the power is there. It's just a matter of having the right algorithms and implementing them on the satellites. In fact, when we go to conferences, a lot of university students have tried out different algorithms, and we're happy to test any that different agencies here would have, post them on the satellites and see the impact of those. I think the best possible outcome is to see how we can work, on the shoulders of experts like all of you to try out these applications in space directly. Again, these satellites, the 6 that we're sending up, are not going up with a mandate of weather monitoring because the resolution is too fine. But as we switch gears and build lower resolution, higher SWAT satellites, it would be interesting to see how we can bring those models in. That said, I think we have the capability to do it. It's just a matter of having the problem statement in front of us and maybe 6 months to a year worth of time to do it. Capability-wise, I don't think it's an issue.
Thank you very much for presentation. And I'll just say one very quick thing from the World Meteorological Organization perspective. This is very inspiring to see. More and more we're seeing these companies, private companies in the private sector, trying new things, innovating with microsatellites and constellations. And this is the future unfolding before our eyes. So the WMO has what's called an open consultative platform, which is a long way of saying public-private engagement. And we like to see this sort of work happening because it has so many potential applications. So thank you very much for your presentation. I'll probably take one more question because it's been very interesting. I don't think there's a person in the room who's not fascinated by what we've just seen on the screen and heard from our colleagues. So any questions? Yes, all the way up the back. I see you. Yes, I'm going to run up here with the microphone. I'll come to you.
It's about calibration. So when we see the data from planet, so they're also having constellation for the Earth observation, right? So only planet, they have 3 to 4 bands. Yeah. Still, when we look at the image for the same region, which is again from the different satellites, we see the data quality is something different. Like for being 2 to 3 bands, they're not unable. We see LED quality. So you are maintaining 200 plus bands. So how you are come up with, these calibration issues?
That's a great question. So the first thing we realized is we don't want to build a camera to fit a satellite. We wanted to build a satellite to accommodate a camera. And that means that the aperture size of the system is such that we can resolve the image at Nyquist. And the other thing that we look at is we also have propulsion on these satellites. So we maintain a certain altitude. With Planet, what happens is when you have hundreds of satellites at different altitudes with different inclination profiles, it can sometimes lead to a change in the imaging parameters. For example, the sun angle parameters, or if you would look at just the resolution of the system, it can vary from system to system. But over here, one of the things that we have ensured is that the orbital profile of all the satellites is very close to each other in the constellation. The other thing that we've also done is we have 2 IMUs on the satellite. We have a couple of star trackers. So the idea is to ensure that from a image construction and geometry standpoint, we have a very high quality system. Coming to the radiometric calibration side of things, we've done, I would say we've done sufficient calibration over the last 8 months on ground. The first images that we will take will probably be of Gobabeb or LaCroix or some calibration site here or there, because we want to constantly keep taking these images for ensuring radiometric consistency between the different satellites. I will not go out and promise that the images are going to be perfectly similar to each other. We all know the discrepancies that come on the detectors, degrees worth of difference in the temperature, and it can lead to changes in SNR and things like that. But we have enough confidence that the system that we've built will have a very low standard deviation when it comes to the image quality, and we'll also ensure that if there is something, if there is a change, we take it on the highest priority, because the radiometric quality of the system matters the highest to us. So again, now it's a question to all of you actually, all the users of the data. Please tell us if you don't like the data, if there's any issue with it, and we'll fix it. If we can on these satellites, if not on the next few satellites.
Thank you. Thank you very much. Round of applause again for Pixel. Good luck for the launch, for your next launch in a couple of months, and good luck in the future. Thank you very much. So there's been a slight change of plan again. So we're going to hand back to our hosts because we're moving to a felicitation session. So over to you.
Actually, some of our guests will be leaving early because they have other prior commitments. So we'll be facilitating our chairs and co-chairs of these sessions. I would request Ben Churchill, sir, who's Director of WMO Regional Office for Asia and Southwest Pacific, and K.C. Sai Krishnan, sir, who is Head of Satellite Meteorological Department of IMD, kindly come and facilitate our guests. I'll be calling out their names and kindly facilitate them. I would like to first invite Alan Wong, sir. Who was the chair of first session, the space program and data access updates. I request Scott Lindstorm to kindly come and accept our token of appreciation. Bodo Zeshke, sir, kindly come and accept our token of appreciation. Mr. R.C. Bhatia. Pradeep Kumar Thaplial. Manik Bali, sir. I request Sai Krishnan, sir, to kindly facilitate Sir Ben Churchill. I would like to invite Ms. Zoya to kindly come and accept a token of appreciation. Sir, please don't go back. Dr. A.K. Mishra, Mitra, sorry. Mr. R.K. Giri. Shubin Balakrishnan. Dr. Neeti Singh. Dr. Satya Prakash. Dr. Gargi. Mr. Chinmay Khatti. Chinmay sir. Okay, then I would like to invite Ben Churchill sir to kindly facilitate Sai Krishnan sir. Thank you so much, sir. Now we'll be proceeding with our oral presentations, starting from sessions of hall number 2, and then we'll proceed to sessions of hall number 6. So our first session is now characterization of radiometric uniformity and stability of ground side for post-launch calibration of INSAT 3D-R at IMD by Dr. A.K. Vitla.
For session 8, performance and calibration of satellite instrument, session chair is Dr. Pradeep Kumar Thapalial sir and K.C. Sai Krishnan sir. So I will request both of them kindly come and sit.
Start? Yeah. Thank you, sir. How much time before you start?
10+5. Yep.
Good evening. Thank you. Before I start my presentation on characterization of radiometric uniformity and stability of ground site for post-launch calibration of INSAT 3DR or 3DS, now we are going to at IMD, I would like to have a glimpse of what exactly had happened earlier. This is the activity of joint Calwell team has been started since 2030. It is almost a decade back activities. Earlier, we thought that this work has to be initiated by the ground calibration and all. Then we decided that there must be in situ calibration because, as I mentioned in my earlier talk, that INSAT series of satellite has changed our perspective to see the weather phenomena. Now, INSAT 3D, 3DR, when it is launched, so the paradigm shift has been occurred, and with in terms of products, in terms of its assimilation to the model and all these things. So after that, you have seen that the number of you can say the committees of CGMSs and G6 have come into the play, and then everybody is looking up to the quality data. So for the quality data, we are in the process of how we can make our data product very, very useful. Now here, what Insect 3D are and Insect 3D, we have a IR calibration at the ground, but the visible calibration we do not have onboard calibration. So for onboard calibration, some of the things that is to be required, that the first thing is in situ calibration. So our team, that is IMD and ISRO team, has jointly we can say ventured into to find out the ideal site. But prior to the site, radiometric calibration quality of this data needs to be looked on. So some of the things like sensor performance, ground processing, calibration, visual quality, radiometric accuracy and consistency, data product used for weather and climate application. So these are the overview tasks which we had in almost a decade back. And then slowly we have gone through, and then we have found that there are many methods are available worldwide. One of these vicarious calibration method is a reflectance-based approach that is applied for visible calibration. As I mentioned, that visible we do not have onboard calibration. So here, reflectance-based approach we applied, and then there are we had a search on to find out the ideal site. And that site was first we have gone to the Jodhpur, that was in the Rajasthan state, and then we have went to the Jaisalmer. After that, we have identified this site at Bhuj. So it is observation is not initially traceable against an absolute scale. It is a cannot engage in the logic of testing for systematic errors. So if an observation cannot independently establish its time dependent bias. So this is the collection of surface data, and from the instrument side, we have gone through like ASD hyperspectral radiometers, number of other observations like synoptic observations we made at Bhuj site, and we try to find out that particular site, a radiometric utilization for the calibration purpose. Now, if you can, this is the methodology that we adopted. If you can see here over the Calwell side, and then we have taken the spectral reflectance by spectroradiometer, AOD, O3, that is a aerosol optical depth, ozone, water vapor by microtop 2, and then we have utilized the radiotic transfer model, that is a 6S. 6S radiotic transfer model which converted to the TOA radiance, and then finally error analysis and calibration coefficient were going on. So this is the site which I would like to highlight here, that the vicarious in situ calibration site, that is in Bhuj. Vicaria is an area where we are used to go there for twice a year. We try to compute the coefficients of whether our sensor of visible is going to degrade or it is in a stable state. So these performances are regularly, routinely being monitored, and whatever coefficients we are generating, we are also putting into our multi-mission data processing system, which is situated in the New Lodi Road, New Delhi. I think most of you have also seen our MMRDPS system at SatMet division. Now, with the successful launch of Insect 3DS on 17 February, now our task is to how end-to-end real-time data processing system could be utilized this calibration coefficient, and we can enable the acquisition processing so fast that every 7 minutes data we are receiving, and it is a 2-tier objective type storage capacity of 2 petabyte each with 324 TB SSD. And then side by side also we have, as I mentioned, that the G6 and CGMS group, we are also contributing to the how our Insect 3D data is being working in line with the other observation. This is the one example, that Severi MIR comparison of last year that we had, and it is matchable. And then there is a many products which is based on MIR channel. Why I'm putting the MIR channel? Because it is the main important, because it is we are deriving fog, we are deriving the dust, that many other nighttime products also being derived. So the accuracy and those things also been very well computed by the bias computation using matchup data set with the reference satellite data also been from Severi. If you see TIR1, TIR2, similarly other channels also being compared regularly. This is a site where recently last year we had a Calwell campaign. And in Calwell campaign, if you can see, surface reflectance using ASD, aerosol, ozone, water vapor, microtop 2. Then Calwell campaign is also taking care of our ground observation and the upper air observation. if you can look at radio sound observation were launched in 18 to 21 January of 6 UTC. So every 6 UTC, and during the campaign mode, we have a radio sound balloon were also been sent. And then surface observation like dry bulb temperature, dew point temperature, wind speed were also taken through the surface observatories. This is the site, if you can see, and then the area where we can went into, and then you will find out the 5 days have been covered in the entire those grid. Visible is having a 1 kilometer of resolution. So we had to make sure that the observation we have to take in a 1 kilometer by 1 pixel, at least more than 7. So after 7 pixels, or you can say once you on 5 days, 7 regular uniform pixel will give you we can say it is in the then it will be stable into the performance or calibration of the pixels. This is a spatial uniformity and spectral homogeneity. You will find out the AOD at the different layers, and it is also found is very, very you can say ideally site. It is, you can for ideal site you will find out the AOD is 0.4 and less. So it must be a 0.4, 0.5 to less than it is your observation being used for the your 6S radiative transfer model. This is a radio sonde data. This data is being used as a temperature profile, humidity profile, and temperature humidity profile. Both we have seen for the 5 days. This slide I already have shown. I think ASD hyperspectral radiometer, where reflectance from 350 nanometer to 2500 range. If you can see here, the range is almost 350 to 2500 of the range hyperspectral visible reflectance data we are taking. Now the important part is here that how our data is being used for the G6 purposes. Unlike there are many applications in IMD where we are utilizing for different kind of weather phenomena interpretations. Storm index is experimentally derived at every 15 minutes by integrating OLR, reflectivity from precipitation radar. Storm signature represented by low OLR values were compared against high reflectivity from PR of large data set to establish a linkage between reflectivity and OLR. This is the kind of a paper. Why I'm putting this paper? Because once your pixel has been calibrated, these kind of product can be derived like LST products. Similarly, the development of finer spatial resolution of OLR. This product have been developed and been disseminated to the user and stakeholders. And this is agromet products. They are for agriculture purposes, land surface albedo, potential evapotranspiration, actual evapotranspiration, net effective radiations. So these products all have been supporting to these our G6 and GRWG activities. One of them is a fog detection. If you can see here, the large part of North India, including region like Bihar, Uttar Pradesh, Uttarakhand, Haryana, Delhi, Punjab, grapple with heavy fog with fog. So here, if you can see, the alert and warning are very, very important for us. If you can see here, the comparison with the cloudy and fog clear sky, the comparison has also give us the confidence to forecast for a day or short medium range forecast. For Calwell activity portal, this is the recommendation. IMD is also planning to put all our Calwell activities, which will have information about performance of our currently used sensors, information regarding the sites, instruments, methodology will also be taken care of. This is a data supply system is also there, where we are soon we'll be going to have a data portal where a user can download our data directly from the site. And then this is another one activity that UMETcast services. The data has been received through UMETSat services at NCMRWF, sister concern of IMD, or you can say MOES agencies, through the National Knowledge Network infrastructure under the license agreement with the India Meteorological Department. The imagery and product hosted at this website are for internal use of IMD. So we are also utilizing UMETcast data for our day-to-day forecast. So very soon, new rapid is also going to be launched, where all the data on the real time could be put into the website, where the data can be analyzed digitally. With this, I would like to thank everybody, and I would would like to thank DGM and all ISRO counterparts, because last 1 decade we have a very good journey, because we have seen that after INSET 3D, once year's calibration is being not it is usable, we have shifted to INSET 3DR and now INSET 3DS. Thank you.
Thank you, Dr. Mitra. This is very important talk for calibration of INSET 3D, 3DR series of sensors. So any question from audience? Any question? Okay. Okay. So
The final slide that you showed prior to your penultimate slide, you showed a web link where you can access this information.
Yeah.
And you mentioned that it will become available soon.
Yeah.
Will it be related to the existing INSAT web, the viewer, where you can view the satellite imagery?
Yeah, but with a number of other products also will be integrated into that, like radar product, surface observatory products. All these products will also be in line with the new rapid system.
And it will be a multi-layered
Yeah,
display.
and
All right.
GIS based.
Great. Thank you.
Next talk is by Danish Hussain.
Please do the presentation. Okay, thank you. Myself, Danish Hussain from Space Application Center, Ahmedabad. And today I just want to present the some initial results of the INSAT 3DS imager calibration with regard to the visible and switch channels. So as all we know that the regular monitoring of the performance of the satellite sensor is a very important task when we require some accurate geophysical parameters, which is dependent on the L1B products. And as Dr. Mitra told that as we don't have the visible calibration on board the INSAT imager, so we rely on the some vicarious type of calibration and some inter-satellite calibrations. The part of the vicarious calibration is being presented by Dr. Mitra, and I am just going to present this intercalibration, which utilizes the G6 protocols with regard to the visible and switch channels of INSAT 3D imager. So this calibration is being done with respect to a standard satellite, which G6 has announced as the MODIS onboard Aqua. So we have used the data from the INSAT 3D imager for July, August, September 2024, and the same concurrent passes for the MODIS Aqua. The methodology we have used, the well-established the ray tracing methodology, which utilizes the geostationary sensor, which is by which we can calibrate some. The geostationary sensor can be calibrated using a previously well-calibrated sensor, which is a standard, which is announced G6 as MODIS Aqua. So the NASA's MODIS onboard platform Aqua is being used as a reference calibration sensor for the G6, and we have calibrated the INSAT 3D imager or INSAT 3DS imager using the same Aqua radiances. So the steps we have followed are the G6 protocols, which is nothing but a 5-step processes. The first step is subsetting the and regrading the data on the same footing. That is very important because we can compare the two satellites data when we put all the data on the same footings. So the calibration is done the Indian Oceanic region. The region is taken to be 45 degree east to 110 degree east and minus 20 to 20 degree latitudes. After selecting the calibration domain, the raw counts corresponding to the visible and switch channels are graded within the 0.5 by degree, 0.5 degree over this domain. And the corresponding MODIS Aqua passes, which were over the said domain, were selected, and the corresponding radiances are graded within this domain over this 0.5 degree, 0.5 degree. We have selected this large domain and grid size to reduce the spatio-temporal matching and the navigational errors. The second step is the co-location of INSAT and MODIS Aqua data. The pass of the MODIS Aqua observation, which have a difference greater than 30 degree minutes from the INSAT images, is not taken for the calibration purposes. After the spatio-temporal co-location, a check is applied to ensure the geometrical matching and closeness of the data, and the threshold of the zenith angle, satellite zenith angle, and azimuth angle is applied. For INSAT series, we have applied the solar zenith angle, satellite zenith angle, and azimuth angle is 15 degrees. Now, the spectral correction of the data. MODIS and INSET have same channels, but different SRFs, satellite response functions. So the spectral correction of data is very, very important process. For that purpose, we have used the LARC website and we have corrected the INSET SRF with respect to the Shiamaki data. For that purpose, the convolved radiances from a Shiamaki satellites are being calculated for both of the geostationary satellite, which is INSET, and the MODIS satellite, and the ratio of this image pair convolved radiances is found. And this ratio is known as the spectral band adjustment factor, which is applied to the correction. The fourth step is the data filtering, which is nothing but to check the homogeneity and the standard deviation within the 0.5 degree by 0.55 degree, and to remove all the pixels which have the sun glint probability greater than 10%. And the final step is the to calculate the calibration gain coefficient by applying whatever we have done in the 4 steps, and to calculate the gain coefficient, and this gain is applied to the final radiances of the INSET 3D. So this is the scatter plot between the Shiamaki convolved radiances and the aquamotive radiances with respect to INSET 3D data. Because we don't have the currently we don't have the INSET 3D as SRF, so we have used the 3D SRFs to calculate this SBAF. The SBAF for visible channel is come out to be 0.958, and for switch channel is 0.956. So these are some initial results for the monthly calibration of INSET 3DS imager visible channel for July 2024. As we have seen that after that G6 correction, the INSET 3DS radiances and the MODIS radiances is coming very close to the 1-to-1 line. We have performed 2 exercises, in which the first one is we have fit the data with respect to forced origin. Means we have fit the data by the line which is coming to the origin, which is recommended by the G6, and for that exercise the coefficient is coming. The gain coefficient coming is approximately 0.89. But if we fit the data by linear regression, then the gain coefficient is coming with some offset, -6.8. More or less, the probability density function, which is shown on the right hand side, is matching. But in some cases, for 100 to 150 visible radiances units, they are matching, but not very much for the July kind of data. For August, the situation is not very different, but when we pass the line through the origin and the force phase the data, the gain coefficient is coming to 1.03, and for post fit, not the force phase, for the best fit, the line coming from the point, the gain is coming to 0.99 with very offset, very much offset of 4.19, but the PDF functions are matching very well after correction on the July data. This is for switch channel, August data. Switch channel is also performing very well, but for values of 7.5 to 12.5, some differences are observed. This is for September. September has the flip, INSET 3D imager flip data. So that is why some corrections is also required. So we will do again this exercise, and we will apply the corrections accordingly. The same is for the September data for switch channel. So the line passing through the origin is 0.98. So it is more or less coming good for switch channel, but not for visible. And this is my final slide, which shows the actual calibration, means the plots between the counts of the INSET and the radians corresponding to the MODIS, which shows the calibration coefficients when passed through the origin are more or less same, but the coefficient which we gain from the best fit line is varying. Means if we fix the space counts for some value, then we can get the offset for the best fit line which coincides with the force weight line. So this is the exercise we have done for the INSET 3DS for 3 months of data. And after the G6 correction, we can conclude that the data is coming of good quality. Thank you very much.
Thank you, Mr. Danish. Any questions? Because what you talked is very relevant, and we have been doing this ground calibration also. So our job is to, as Dr. Mitra was saying, we'll have to go to that expedition with the equipment and do the actual ground calibration for 3DS. We haven't done it yet, so that's the job now. Next maybe few months we'll be carrying out that. Yes. So let's hope it comes out properly. I mean, whatever you have shown is very encouraging. So thank you.
Thank you, sir. Thank you very much.
Next talk is by Scott from University of Wisconsin.
So I kind of feel like the odd man out in this session, since I'm not talking about calibration or validation at all. I'm talking about telling forecasters how to use the calibrated and validated data. So weather satellites are, unless they're small sats, but the geostationary satellites that I typically train on are billion-dollar investments. So you really want to get the forecasters to exploit that so you can demonstrate to your government that, yes, we're spending your money wisely. We want to relate the satellite imagery to the ability to provide great support for decision makers. So that's kind of the thrust of what I do. I want to advertise this again. Alan mentioned this yesterday. I mentioned it during the training as well. There's a community satellite processing package that is a suite of software resources that are available for satellite imagery. There's a users meeting that's occurring in April in 2025. You can see the URL there that will talk about that gives you information about the meeting. So if you're interested in especially polar orbiting satellites, this is a great meeting to go to. So SIMS scientists do create a lot of useful imagery. I've seen this mimic TPW a couple times. This is from about a week ago. So we have the future Ferg doll. I like this animation because as frequently happens, when you get a cyclone in the northern hemisphere, you get a mirror image of the cyclone in the southern hemisphere. That one in the southern hemisphere, I think, did not develop into a tropical cyclone, but it's just beautiful imagery. But you notice there is a training video there. So to describe these products to the forecasters so they can better understand them and make better use of them, SIMS provides training that's available, and the data are available in real time as well. There's also this SIMS turbulence product for aviation that shows the probability of moderate or greater turbulence. So if you're doing any kind of aviation forecasting or aviation support, it's a useful product. And there's a training video there. So usually when there's a SIMS product, there are training resources available for it. So here's what I flew en route to Delhi. This is on the second flight from Detroit to Paris. And as we got close to Ireland, the pilot told everyone to sit down. And because we are flying through a region where the probability of moderate or greater turbulence was increasing, I didn't feel anything, but there were some observations as are noted on this slide. So to train forecasters, you really have to have access to the imagery. I was pleased to see the RAPID site from IMD. I'll probably be accessing that when I get back to Wisconsin just to look at the imagery. That's easy to do in real time. Once it's a week past an event that you're interested in or a month past, suddenly it gets really hard to find that I really want to express my thanks to the national agencies around the world that do have, that do make it easy to find their data. There's another great resource that I use a lot is NASA Worldview. That has a lot of beautiful imagery on it. So for example, I was reading the paper here on Monday and I saw this little snippet in the Times of India. City AQI improves to best since October 29th. So I hope, like everybody else in this room, you thought, I wonder what the satellite imagery looked like on October 29th. And with NASA Worldview, you can go back and look. So there's October 29th. And here we have December 1st. Looks pretty much the same, I guess. And then December 2nd. And if you were looking at this site in between October 29th and December 1st, you saw some pretty ominous looking satellite imagery. So that's just a little anecdote from kind of how my mind works. So where do you find data? There's a lot of data on the NASA NOD. That's the NASA Online Data Delivery System. So they have Amazon, Google, Microsoft data repositories where you can find JPSS data, GOES-R data, GK2A data, Himawari data. It would be great if I could find European data on there or India data. I'm most familiar with the Amazon Web Services because that's what I use. So you can see some links there. And during the training on Monday, I showed ways to display data from VIIRS or HAMS or newcaps or mirrors. Direct broadcast data is another great data source. So polar orbiting satellites like in the JPSS satellites have the ability to direct broadcast information if you have an antenna, and then you can use CSPP software to create imagery. And that software is designed to create imagery that looks just like you'd get it if you got it from NOAA. And then you have CSPP software, polar to grid and geo to grid, that creates imagery. So polar to grid, no surprise, works with polar orbiting data. Geo to grid, also no surprise, I hope, creates imagery from geostationary satellites. So you have to have a reader for the data. So that, as far as I know, readers don't exist for all of the satellites. Geo to grid and polar to grid are using the SatPy libraries, the Python libraries. So all you need to do is find a clever programmer to create a reader, because the output or the format needed for SatPy is known. So what kind of data readers exist now? They're listed here. So ABI, AGRI, AHI, AMI, FCI, and GLM as well. Polar data readers also exist. There's a nice list here. The nice thing about polar orbiters is they're global. So if you have geostationary imagery, sure, it covers maybe 40% of the globe at one time, but polar orbiters give you the entire globe every day. So why does SIMS create software for polar orbiters? Well, we manage a lot of direct broadcast sites, and they're shown on this particular page. So Guam, Hawaii, Alaska, Wisconsin, Miami, and Puerto Rico. So it's important for SIMS to be able to create the image, to have software to download the data from the polar orbiters, and then create imagery or files that can be used either by the National Weather Service or by NWP centers. So the software, there's software from the two different types. Notice how similar it is. If you go to the documentation looks similar. So once you know how to use one, it's pretty easy to use the other one. And the one thing I like about this is because the software is so similar, you can create imagery on the same grid. So this software allows you to create imagery on a particular geographic grid that you define. So we can compare things like ABI data with GCOM to 36.5 gigahertz. So I'm always telling forecasters, don't rely on just one data source, rely on more than one. And this is a way you can compare the two to when you're training, you can say, well, look where all the low level moisture is with this 36.5 gigahertz imagery. Or you can look at the 89.5, the 89 gigahertz as well. So here's an example from Guam where we have the forecasters looking at the GCOM2A in the 89.5. I hope you can see the circulation of moisture with this developing tropical system and the GCOM2A winds where the convection is. I believe the maximum wind speed there was about 40 knots. So they knew it was a impactful system as it was approaching the Marianas. There are lots of examples on the SIM satellite blog. They're listed here. And there are just a lot of examples that show very cool imagery. So I encourage you to look at those just to enjoy the beauty of satellite imagery, which is why I like my job, because daily, if you look at satellite data every day, you see something beautiful every day. Just a reminder, there's a meeting coming up. You got to tell people more than once. So SIMS manages the CSPP software that can use to read data, to produce imagery. And I'm happy to answer questions if you have any. So
thank you, Scott.
And now
It's
back
nice
to Val
talk, yeah.
Val.
Any question? So, yeah, it's very nice talk summarizing all this data will be very important for forecaster as well as trainer. So next talk is by Ayaz. Yeah, one question.
So thank you so much for the presentation. As you said, like this platform is combining data from many sources. So is it kind of real time that we get the output as?
The geostationary data is pretty near real time. There's a latency of maybe 45 to 50 minutes with a low Earth orbit.
Okay.
So is that real time enough? It could be better. It could be better. Yeah.
Okay. Thank you so much.
Thank you. So next talk by Lee from KMA. Hembil Lee from KMA. Not there? Okay. So the next one is by Manik Balu from NOAA, University of Maryland.
So I'm Manik Bali. I'm from the G6 Coordination Center, and I've come from NOAA, and my job at NOAA is basically to lead the G6 Coordination Center. G6 stands for the Global Space-Based Intercalibration System, and some of the presenters like Ashim Mitra and others have spoken about G6. So I won't take too much of time, but now the goals have slightly shifted, because now I would just walk through some of the capabilities that G6 has developed. And I hope, and some of the tools that we have developed collaboratively, and I hope that these are, you would be able to use them. So I'll just introduce you to so I'll go through some of these topics, like what is G6, what are G6 products, what are the codes and the data that G6 has and which we can give free to you. And then I'll give you some examples of in-orbit calibration of satellite instruments. And the goal here is basically to introduce you how this calibration can be done at a mere minimum cost and collaboratively. So just to start with, so G6 is a consortium of 15 satellite agencies. We have come under the, we have been formed by CGMS and WMO, and we have come together because we wanted to ensure that the measurements taken by weather satellites across the world, we wanted to make sure that they are traceable to internationally accepted references, which means that if you just look at this image here, this image has the Earth in the center, and it is and this is being observed by satellites of different countries. These satellites have different architectures. They orbit the Earth in different kinds of geostationary or LEO orbits. And because their architectures and everything is different, there's no guarantee that these satellites measure the Earth in exactly the same way and will produce exactly the same measurement. So we all came together and we decided that we'll first identify common references and then calibrate these satellites with those references. So these agencies on the right are like these pictures. NOAA is a member of G6. NIST, JAXA here in India, actually we have IMD and ISRO, both are members and contributing exhaustively to G6 mission. At NOAA, we have the coordination center headed by Larry Flynn, and I'm helping him as his deputy director. So once the instrument is launched, its characteristic can change. That's the main idea. So before the launch, the instrument is calibrated in a TVAC environment, thermal vacuum chamber. It has all the perfect settings, and you give a design specification. Based on the design specification, thermal vacuum testing is done with the hope that once the instrument is launched, it will retain its characteristics and we will be able to take measurements accurately. However, once the instrument is launched, sometimes the story is different, as the instrument characteristics can change in the space environment. A lot of things can happen. So the G6 algorithm, actually, as I mentioned, like it tries to compare a reference instrument with a monitored instrument. And this is the way it does, like it identifies targets that are viewed by both the instrument around the same time under similar viewing conditions. So these two satellites are looking at the same spot. And when you zoom down, what exactly they are doing, they actually pixels are overlapping each other. And we identify these overlapping pixels and pixels that timestamps are nearly same within 15 or 20 minutes. And they have the similar viewing angle. And then they are compared, and you'll get a graph like this, a regression plot like this. I think Danish already shown an application in a different for a different instrument, but here I'm showing for IR that the monitored instrument radiance compared with the reference radiance, and you see a line here. So this is what we are after. And once we get this distribution, we plot a regression line, and then we monitor it. So if you do it for different instruments, this is the time series of the monitoring that you get. This on the top is actually one example of MSG being monitored using ARC instrument. And if you see the time series on the top, actually, this is what it is. Very rocky. Different channels have different biases, and they go up and down. And when these are monitored using G6 algorithm, we obtain bias and offset. And when you apply these bias and offset, actually, this is this more than time series that you get. So actually, this is the magic that G6 does. It first monitors, and then you have the ability to correct those biases and then give it to the users. On the right is so we are actually monitoring like over 80 satellite instruments over time. We have monitored. So, for example, all the MSD series, the in the ISRO INSAT, in Korea actually GK2, then Himawari. So in Europe actually we are monitoring the GOES series of instruments, and we have cataloged all these on the G6 product catalog. If you go to this website, actually you will be able to see the biases of different instruments monitored over time. So I request you, I mean, if you are interested in how good quality, what is the quality of data that is originating from the satellite, then just visit this and you would be able to see the time series of how good the satellite is. And then you would also get the opportunity to apply any corrections to it. So this is some of, so those are actually the G6 products. This is something beyond G6 products actually. So in addition to the satellite monitoring, we are also delivering hyperspectral reference radiance from JMA, like Masai is here, he can talk about it. Basically, the co-location between Himawari and ERC, those co-located pixels, convoluted pixels are actually, you can find them and you can do science on it. We also have the spectral response functions from visible channels, and these are actually used for simulating lunar radiances by gyro. So this is another thing that we are giving to the public. A third thing is the intercalibration tables from MSU. So these are also, in addition, actually every agency also has its own G6 website, which is called GPRC. And you can get a lot of data, intercalibration data, satellite monitoring, and a lot of details about satellite instrument on these websites. So you can just click on these to obtain this. A particularly interesting one is the GPRC of Roche Hydromet in Russia. Actually, this meteor is actually on a Magellanic orbit. So you would be very, it has a different orbit, and therefore you can easily see like how the measurements are different from the rest of the instruments that are launched globally, like geostationary or LEO, which are in geostationary or LEO orbit. So these are some of the deliverables that we give. In terms of actually references, for each channel we have a reference. So for instance, for infrared, actually we have the ERC series, ERC A, B, C as global references. In the visible, actually we have the NOAA 20 and NOAA 21 VIIRS. These follow the MODIS references that were used globally, but if you want to monitor visible instruments, you can use these. Then for the microwave also we have reference, which is the microwave MSU FCDR, Fundamental Climate Data Record. What has happened actually, Cheng Zi at NOAA, he developed a long time series of microwave by stitching together the MSU time series of instrument. And then he further applied a very unique algorithm that made that stabilized this entire time series spanning over more than 20 years. And this is the most stable time series as on date, and therefore we are using it as a reference time series for calibrating microwave instruments. Also, the ATMS is highly stable, but it has a shorter time series. But this MSU spans a large spectrum of the microwave channels, and you can use that one. So coming to what we are also giving to the community. So one of the mandates actually we took in the G6 data working group, and at that time Ashim was the chair and also Masaya was helping us, was that while we give calibrated radiances, we also give correction coefficients. But now we have this new method, like wherein we are also giving code and data processing platform together. In addition to, so you just don't just get a piece of code in data, but in G6, but you also get GPU. You also get which you can access online. You also get the code to read that data, and you also get the code to process that data. And this is bundled with Google Colab file. So if you ever have experience in accessing G6, a Colab notebook, then in a Colab notebook, you have a Python kernel, you have a GPU. You can also access a Python code, which we have developed collaboratively. and then you can access G6 data. And this is one of the examples on the right where we have put together a code on the Jupyter, on the Colab notebook, and we have processed solar data on it, HSIS solar data, and you can see this different solar data overlapping onto each other. So if you just press a button on the Colab, you will get this. So I think you request, kindly explore these. I've provided the links over here. This is again analyzing the and comparing different solar data sets. If you click on this link here, because this presentation is not dynamic, but if you click on this link in my presentation, you will see this code on your on the browser, and then when you press the run button, you will get this plot, and this plot is basically the comparison between different solar data sets. These solar data sets are widely used for calibration, particularly calibrating UV instruments. So I encourage you to visit this. This is another platform that we have built. This platform actually allows one to compare any two observing platforms. So for example, if you want to compare balloon sounds with satellite measurements, wherein the balloon sounding is underflying the, where the satellite is overflying a balloon sound, then you need two things actually. Of course, you need the balloon sound measurement, but you also need a radiative transfer model that will simulate the top of atmosphere radiances that is measured by the satellite. And so in this platform, actually, you have all these things. Like first, you have the readers for the satellite data. The second thing is that you have access to a ARTS radiative transfer model. And then you have algorithms that you can compare any two, compare those two. These are actually available free of cost, and if you want, I can give access to you. This server is located at University of Maryland, and this is one of the outputs of it. We recently published a paper wherein we compared our gluon-based radio sound with ERC, and you can see the time series, and this was done on this platform. It is public and available, and you can see this reference. So, of course, this comparison can be extended to ship measurements. It can be extended to other kind of measurements. Here, actually, we have several subgroups dedicated to individual channels. For instance, in the visible, actually, we have Dave Doling leading the visible channel. But in the UV, actually, Larry Flynn is leading the intercalibration or the calibration of UV instruments. And in this part, actually, OMPS is the JPSS UV measuring instrument. And he has done solar measurements from different UV instruments and compared them. And this is the output of this. Actually, instruments degrade over time, and in the case of the ultraviolet instrument, the sensor actually looks at the sun every week and also every month. So this is over different channels on the solar views. And when you do a principal component analysis, you could actually correlate the principal components or the loading functions with the variations or with physical quantities. And you can see here that the solar activity patterns are of magnesium 2 scale factors, and you can track solar activity and differences after subtracting the shift in activity patterns. So this basically also can give us this the instrument anomalies that originate from shifts in spectral measurements. So this is one analysis that we did, and you can have the code for this as well. This is another thing where I did principal component analysis for the GEMS satellite, the Korean satellite. And this is the image reconstruction of this. So basically the idea is that if you do a principal component analysis of the solar measurement, solar view, then you basically get the main features, and the noise is the one that is what you can say is, if you separate out the noise, then you can actually correlate your principal component with the variations in the with the variations in the satellite instrument. So this is another key calibration step. So basically here we applied this PCA on OMPS, and then here we are applying it on GEMS instrument, and therefore we were able to figure out the anomalies in the GEMS, and now this instrument is working very well. This is in the microwave actually. In the microwave, we have climate. Sorry, this is in the IR actually. So in Korea actually they have this TK2 instrument which also takes measurements in the IR, and we had a collaboration with one of my colleagues, Lee Kan Wang. So in the water vapor channel, actually this was the original time series. You can see it has a drop initially, and then suddenly there is a jump over in the blue. After recalibrating using G6 algorithm, actually we were able to straighten out and correct the anomaly here. So this is another example of working collaboratively and applying commonly accepted references and then correcting the instrument. This is the DCC method. Earlier Danish spoke about the ray matching, but in DCC is the deep convective cloud, where you use deep convective cloud as a transfer to calibrate two visible instruments by comparing them. So, so here actually they use DCC, and you can see this Weir's 11 band, and this consistency between the monthly probability distribution functions of these two. So this is a very stable method that we have used. We have collected the data for deep convective clouds, and we are routinely using. And from I think ISRO, when I went to Langley, and they worked on DCC for quite some time. This is another example of the DCC. I don't go too much detail, but basically we have all the algorithm and everything. We also have a space weather subgroup which we recently found, and the goal of this is to intercalibrate space measuring instrument on board geostationary satellites. So they use magnetic conjunction approach for cross calibration of high energy particle sensors. And we had a special issue on G6 newsletter that is dedicated to space weather. I'm sure that new space companies would be interested in this, because the new CubeSats are majorly impacted by space weather incident. So anyway, this is one of the examples of our work on space weather. This is another example of working collaboratively. So as I mentioned earlier, that we have globally accepted common references. And here actually, this is a heat map of several biases of several instruments when intercalibrated with ERC-B. So on the left, actually, you can see MSG4, MSG3, MSG4, and then Himawari, and then GK2A, which is the Korean and the Japanese satellite. For each channel, we have a bias with respect to ARCB, and it gives, so every year, actually, we generate this plot, and this plot gives us a complete overview of how different instruments across the geostationary instruments across the world are behaving in the infrared channel. So as you can see, like there's some common bias in the 3.9 micron channel, and also in the water vapor channel, which is common to most of the instrument, but rest of them are very close to the reference instrument and have nearly no bias here. So this is another one. This gives a complete picture of how the instruments are behaving globally. And if you click on this link, actually, you can generate this plot yourself. And you can even add your own instrument into it here and get this one bar over here for your instrument with respect to ARCB. So this is, I believe, can be helpful in identifying, like, for instance, insight we would like to add here. So this is the G6 newsletter. So I'm also the editor of this G6 newsletter. It is a newsletter that is issued, that is published every quarter, and it has articles focused on intercalibration, and it has a wide audience, and I encourage you to contribute to this newsletter. So we have over 400 subscribers, and last issue was actually a special issue on space weather, and it had over, I think, 50 co-authors. But before that, actually, there was a special issue on CMA, actually, which we published last year. And I think that also like 70 co-authors and authors in together, and over 11 articles. So it has wide audience, and it carries the message of calibration to a large community, and you can get feedback on your instrument readily. In fact, this the last one actually we also announced the AOMSUC, and Alan had sent his announcement for the AOMSUC. So this is that. So in summary, actually, the 6 intercalibration system was created. It's a framework that has been created to monitor satellites globally, detect anomalies in them, and then correct them. And we have recently added a space weather subgroup, and new algorithms are being built to exploit lunar viewing, account for calibration. I'd also encourage you to visit this slide, because it has links to various code data on calibration code, and you also can run these directly from your browser. We also have a plotting tool here, and for anybody interested in calibration, I would suggest that please visit this slide and click on these links. Use this as a starting point, or for calibration. So this is all I can give. Yeah, thank you.
Thank you, Dr. Pali, for the detailed and extensive details you have provided about the G6 activities. I'm sure it will be very useful and informative to all of us. So, any questions? Okay, thank you. The next one is radiometric performance of Himawari. Dr. Masaya Takahashi from JMA.
Thanks, Chair. Okay. So first of all, I'm very pleased to know the Himawari data are widely used not only in the Eastern Asia but also in India. So my talk is calibration performance of the current Himawari 8 and 9 satellites. Only the visible and near infrared channel bands, but I hope this talk will be of some help of your applications. Yeah. Yes, please. Okay, sorry for that. I will start. I'll be talking about radiometric performance of Himawari 8 and 9 AHI's linear bands. Okay. So in this presentation, first, I will briefly introduce Himawari 8 and 9 satellites and instruments. Then the AHI has an onboard calibration equipment. So I will talk about onboard calibration called solar calibration. And also I will talk about the solar calibration validation methods and results. And finally, I will make a summary. As you may know, Himawari 8 and 9 have 16 band visible and infrared imager called AHI. So the AHIs and the specifications of the satellites and instruments are identical, but a little bit different in the spectral response functions, almost similar. At the bottom of this slide, there are spectral response functions for AHI 8 in red and 9 in blue for the linear bands. And as for the satellites, both satellites are located at around 140.7 degrees east. And Himawari 8 had operated until 2022, and now it's in orbit backup of Himawari 9. Himawari 9 took over its operational role in December 22, and to be operated until Japanese fiscal year 2029. Before the switchover of the operational role, there was about 2 months parallel observation period. Okay, so during this parallel observation period, we did a direct comparison of AHI 8 and 9. This animation is one-day loop of albedo difference, AHI 9 minus AHI 8. Sorry, it's anyway, so we don't see any significant diagonal variation in the differences, but in band 1, 0.47, and band 3, 0.654, and band 5, 1.6. There are about 3 to 5% differences between AHI 8 and 9. As I showed, spectral response functions are almost the same. So these differences are mainly caused by calibration accuracy. Okay, then let's move on to calibration. So AHI has an onboard calibration equipment called solar diffuser. And this solar calibration is performed by using onboard solar diffuser and deep space observations. Calibration equation is quadratic, and quadratic term is pre-launch characterized fixed value. Okay, and offset is updated using deep space observation in real time. As for the linear term called gain, is estimated from solar observation using solar diffuser. Solar observations are performed twice a month, but at this moment, the results and the estimated gain are not directly reflected in Himawari standard data, which is equivalent to the level 1B. So how to use the gain estimated from solar diffuser? In the case of AHI 9, mean calibration gains derived from solar observations before the start of the operation are used for the HST's radiance calculation. In addition, calibration trends are calculated on annual basis and included in HST as a trend correction information. On the other hand, for Himawari 9, we are still using pre-launch gains, but some detector response differences are corrected by using solar observation before the switchover from Himawari 8 to 9. And the calibration trends are not yet included in the HST at this moment. This is a current issue, or challenging thing to be done in future. Okay, so this slide shows the solar calibration results for AHI 8 and 9. These figures show the inverse of calibration gain, which indicates instrument sensitivity trend. X-axis is just 1 year, and each line shows a different year. So when we want to see the annual degradation of the instrument response, the difference between the lines in y-axis is the annual degradation. Okay, so in the case of the band 3 of AHI 8, annual degradation rate is about 0.6 to 0.7%, and yes, then when we compare AHI 8 and 9, left and right, the seasonal variation is higher in AHI9 compared with AHI8. So the AHI9 seasonal variation is about 2% higher than AHI8. And for the band, longer wavelength bands, band 5, it's a very stable in time. But we also have a very big seasonal variation. The potential reasons for these seasonal variations of gains are imperfect solar observation timing due to operation constraints, and also the uncertainty of the solar diffuser BRDF, the root causes and the investigation. Okay, to validate the solar calibration results, we are using 3 different approaches. The first one is called vicarious calibration using radiative transfer simulation. So in our vicarious calibration, the target, main calibration target is water cloud soap. So we use the Dr. Nakajima's retrieved package called Capcom to retrieve cloud optical properties and simulate the top of atmosphere radiance by using R-star. And the second approach is ray matching. This is almost the same as ISRO implement. Ray matching intercalibration. And this is a direct comparison of observed reflectance between AHI and the VIIRS. And the algorithm was developed in the framework of G6. Right figure shows AHI observations divided by reference values. Reference means the simulated radiance or VIIRS observation in the parallel observation period of AHI 8 and 9. The reddish bars shows AHI 8 results, and the bluish bars show the AHI 9 results. For each instrument results, left-hand side is a vicarious calibration results, and the right-hand side is a ray matching results. So when we take the difference between reddish and bluish bars, this is equivalent to the AHI 8 and 9 radiance difference, which I shown in the first slide. Okay. And the third validation approach is lunar calibration. So lunar calibration is a comparison of disk integrated lunar irradiance between observation and the model. So at this moment, we use G6 standard model called 0, G6 implementation of the RORO model. And the AHI lunar observation is performed by using just one scan of the region 5, which is a 30-second super rapid scan mode. Upper right figures show the example of AHI 8 lunar observations for 6 billion channels bands. And the simulated lunar irradiance is calculated by using this 0 model. Actually, RORO model is implemented in the 0. At this moment, lunar calibration is a very high relative accuracy, about 1%. This is very suitable for satellite instruments, medium to long-term monitoring. The bottom right figures show the AHI 8 irradiance ratio for about 7.5 years. X-axis is a lunar phase angle. 0 degrees means the full moon, and plus minus 19 means the half moon. The annual degradation ratio can be seen in the difference in the y-axis at a certain phase angle. So when we look at the band 3 results, we see this arc shape phase angle dependence. This is not a natural dependence, but caused by our integration of observed radiance. So we need to update in future. On the other hand, for the band 6, there is a V-shape dependence. This is caused by the model. So we now have this kind of phase angle dependence in the lunar calibration, but this dependence has few impacts on the trend estimation. So we are using the lunar calibration, one of the validation methods. Okay, then this slide shows the AHI 8 calibration performance and validation performance. These are the time series of relative calibration bias for 6 linear bands. And each color shows different the calibration methods and validation methods. So for the shorter wavelength bands, band 1 to band 4, the annual degradation rate is about 0.4 to 0.7%. And all the results are in good agreement. Lunar calibration results in blue, and the solar calibration results is in purple, ray matching in orange, and vicarious calibration in green. We can also see the scattered, very scattered light blue plots. This is the lunar calibration results, which I mean, I said there are big phasal dependence, but in the trend estimation, there is no very few impacts. Okay, and also here is the results for the AHI 9. This is just only the 2-year validation results. We also derived similar results compared with AHI 8, but all the plots are very scattered. In particular, the solar calibration results in purple dots are very scattered. So that's the current issue for us. And also the estimated annual degradation ratio for AHI 9 is quite higher compared with AHI 8. So we need further samples, or we need to improve our calibration methods for AHI 9. Okay, so summary. So radiometric performance of linear bands for Himari 8 and 9 AHIs are validated. Direct comparison of observed albedo shows 2 to 5% differences in band 1, band 3, and band 5, which are caused by calibration biases. And the calibration gains for AHI linear bands are derived from solar observations. And for AHI 8, the calibration trends are calculated on an annual basis. But for AHI 9, it's not included in the current level 1 data due to the seasonal variation. The calibration trends estimated by lunar calibration, Vicarious calibration, and rain-matching intercalibration are good agreement with solar calibration, but we need further samples, and we also need to update our methods in future. That's all. Thank you.
Thank you, Mazaya, for the excellent talk. These results are very exciting results from HI 8 as well as 9. 9 slightly there were differences are more than the 8 Himari 8. So what is the reason for that? It was in orbit sphere for a longer time, no?
Yes. Actually, Himari 9 was launched in 2016. So 8 years ago. But it was a long time in orbit backup of Himari 8.
But Himari 8 is still working fine. It is better than even Himari 9. So what is the reason to discontinue that?
So in this talk, so when we compare the Himari 8 and 9s and the calibration performance, maybe Himari 8 looks better, but it's just one of the performance. So when we totally compare this Himari 8 and 9, the performance are comparable. See?
Thank you. Any more questions from audience? So this is the advantage of the last session because everybody is tired. So most of the talks, there were no questions. Thank you very much. And I think we have finished our session in time. And I think we have also saved the question hours. So I hand over to, okay, so I hand over to organizers. Thank you very much.
So still we have 3 papers in session 5. So we have to complete today.
Thank you very much. And thank you for accommodating the changes. I hope it's been very interesting for you. I would ask, we have 3 presentations, and I would ask, just in the interest of time, that we hold questions until the very end, and that the presenters try and stay as much as possible on time, even go a little bit quicker, because it's been a long day already. We've come to the end of the allocated time, so we're now running into overtime. So I also want to respect our hosts and yeah, thanks again for your patience. So I will now introduce Shivika. So thank you for your patience. I think I said 2 hours ago that you're up. Thank you for sticking around and bearing with us. So Shivika will be presenting on ground and space-based multi-Earth observation enabled geodetic framework for extreme weather monitoring and consistency analysis for Indian Himalayan region. It's a bit of a mouthful, and I'm sure you're going to explain it all to us very nicely. Thank you very much. Welcome to the podium. Thank you.
So it's good evening, everyone, 6 p.m. I'm Shivika Saxena, and I'm a PhD student at MNNIT Allahabad under the supervision of Dr. Ramji Dwivedi. So So the essential climate variable that I'll be talking about is PWV, precipitable water vapor. These are the contents. So basically, I'll be talking about the workflow that we have followed in analyzing PWV as a precursor to rainfall events. So precipitable water vapor is essentially atmospheric water vapor precipitated into an atmospheric column of unit area. So we started with just correlating extreme rainfall events in the state of Uttarakhand with the PWV estimates calculated from GNSS data obtained from Survey of India course network. Then we thought of integrating two space geodetic techniques, that is SAR interferometry and global navigation satellite systems. So we processed SAR interferometry data to produce PWV, differential PWV data, and then moved ahead for absolute PWV estimates. And then we understood the various atmospheric dynamics that is associated with water vapor, that is vertical stratification, etc. So we thought of building a ZWD, that is zenith wet delay model for the state of Uttarakhand, because when we focus our work to a region, especially that is a mountainous region, then the accuracy is better. Then finally, we will move on to proposing a geostatistical framework, preferably collocation, to transfer the data from a high resolution platform, which is in a scattered manner, to a more regular grid network. So the motivation behind integration of two space geodetic techniques is that sometimes, for example, more specifically in a region of high mountainous or highly undulating terrain, we don't get very good consistent meteorological observations at the frequency that we want. So, so we can use multi-source PWV that complement each other, for example, GNSS and INSAR. So the small scale variations in PWV will be captured by high resolution data, that is INSAR, and the long wavelength, long scale PWV variations will be captured by GNSS. So atmospheric water vapor dynamics is very variable. So we have vertical stratification going on, we have turbulent mixing going on, as well as we have seasonal variations which are very much distinct in the state of Uttarakhand. We will try to accommodate all these phenomena in our work. So short scale variations are of the degree of less than 10 kilometers. So they can be picked up especially using high resolution data, that is INSAR. And we have processed a total of 39 Sentinel SLC, Sentinel 1A SLC in a GMT SAR software environment. The long wave trend we have captured using GNSS data, which along with elevation dependent phenomena has been captured in, inside the novel model that we have developed using a network of GNSS course data. So this is my study area, that is the state of Uttarakhand. It shows the Survey of India newly established GNSS course network and the ascending pass and descending pass of the Sentinel 1A data. For validation purposes, we have used MODIS PWV as well as ERA5 reanalysis PWV. So space geodetic techniques are GNSS and INSAR meteorology. So for GNSS meteorology, we have the advantage of having the high temporal resolution, but we have the disadvantage of having point measurements. So a little bit increase in accuracy could be achieved by developing a site-specific model for water vapor weighted mean temperature, that is TM model, for the state of Uttarakhand, which we have published as our previous work. So from GNSS estimates, we get zenith total delay, that is ZTD, and which is a combination of hydrostatic and non-hydrostatic. In more colloquial terms, it is wet and dry part of the wet signal delay, signal delay. Then the wet part is utilized by multiplying the pi factor, which is a function of the water vapor weighted mean temperature, to obtain PWV estimates. As far as INSAR is concerned, we obtain interferograms from the INSAR processing. The interferograms contains a lot of factors, topography related, displacement related, troposphere related, ionospheric related, orbital errors, flat earth errors, and some thermal noise, etc. So these out of these components, we utilize the tropospheric phase difference, phase error, and that again is divided into wet and dry components, just like that we had in signal delay from the GNSS. So that part is analogous to how we process the GNSS GNSS data. So for GNSS processing, we used gamut, and for INSAR processing, we used GMT-SAR environment. So the high resolution differential measures are captured using the pair of SAR acquisitions. And for better DEM removal, we used Cartosat instead of SRTM data for multi-temporal INSAR processing. And then from the differential measurements, we moved on to the absolute values using LSQ approach. So this is the GNSS INSAR framework, which is the novel ZWD model for the state of Uttarakhand. So we start here from GNSS data. We develop the elevation dependent model, which follows a negative exponential, showing the characteristic of atmospheric water vapor. Then we include the seasonal dependency, because there is a large season distinction found in the Uttarakhand region. Then we design the long wave model, which captures the regional essence in terms of space. So we model the ZWD with the longitude and latitude of the region. Then we combine these to get, then we combine these two portions of the model to get non-turbulent of ZWD. And then from the INSAR data, we get shortwave signals. We capture the shortwave signals, which forms the turbulent mixing part of the atmospheric water vapor. And then we finally combine these both to get the full atmospheric information. Then final, there is the conversion of ZWD to PWV. So this is the pictorial representation. We have 50 million stable pixel points from the MT INSAR processing. And on those pixels, we obtain our model values. Summation of this will give us the combination PWV. These are the model fits. We got a fairly good goodness of fit. These are for representative purposes, these dates. This shows the seasonal dependency in our data. And this is the long wave model picture captured. So for results, we validated our results with modest PWV. For the data available where it was non-cloudy, it was very difficult for us because most of the our results are focused on monsoonal period where it is very difficult to get non-cloudy data. And we got a good correlation between them. Then for those days where non-cloudy data was not available, we did the validation with ERA5, that is mostly all the monsoonal days of the year. We got a good correlation in ERA5, but there was a slight underestimation in ERA5. Also, there was an issue here in the top right corner, which shows the very less in meteorological information being assimilated in this region because of less meteorological coverage, instrument coverage. This is the concept of water vapor weighted mean temperature, which we developed in-house, known as TEM SSM, that is site-specific model. So this utilizes the linear relationship between surface temperature and water vapor weighted mean temperature. And for a region where meteorological observations are tough to find, consistent, so this TEM model is a boon. So this is the physics behind this, using the water vapor ratio to PWV. So for concluding remarks, I would like to say that turbulent mapping of PWV is essential, especially in mountainous terrain such as Uttarakhand, where local tropospheric effects are highly dynamic during extreme events. So we found our combination PWV performing well while validating with ERA5 and MODIS PWV data. So we obtained a fairly good RMSE, 1.2 to 1.3 millimeters with MODIS PWV, and especially for non-rainy days. For rainy days, it was a little bit higher. And with ERA5 reanalysis for the days where non-cloudy MODIS was not available, the range was 3 to 5 millimeters. We also found that PWV combination values at Dehradun was estimated higher using our model, which resonated with the rainfall scenario during an extreme rainfall event in day of the year 217, having 100 to 150 millimeters of rainfall on comparison with IMD rain. So the need of the hour is we look forward to have a better meteorological setup in the state of Uttarakhand, because mountainous regions needs a little bit denser coverage of meteorological data. So multiple Calwell sites will also be appreciated, where we have multiple sources of instruments, like multiple sources of PWV coming from different sources, so that inconsistency in one source can complement the other. For future work, we are aiming to transfer this data from the PS, stable pixel density to a regular grid using least square collocation. Thank you.
Thank you very much. Thank you, Shamika, and thank you for keeping to time as well. That was very interesting. I think the two biggest challenges we have globally in terms of monitoring and forecasting are in the tropical regions with the convective weather, but also in the mountainous regions. Many countries that are part of the early warnings for all are really facing these big challenges with very sparse ground stations and so on. So we really appreciate your work. Thank you for sharing it with us. As I said, we'll hold questions until the end, if you wouldn't mind sticking around. And we'll move to the next presenter. And it is Jana Bora. Is Jana here? Yes, wonderful. Jana's going to be talking to us about the evaluation of OceanSat-3 scatterometer derived winds using buoy ship and scatterometer observed winds over the Indian Ocean. Thank you very much. Welcome to the podium. To be fair, your time will start when the presentation is on the screen.
Good evening, everyone. I am Jharna Bora. I am a second-year PhD student from NIT Rourkela, and I am going to present on the topic evaluation of OceanSat-3 scatterometer-derived winds using buoy, ship, and scatterometer observed winds over the Indian Ocean. Probably everyone present here knows about scatterometer, but in this workshop, I think no one has much discussed about scatterometer winds. I will just briefly discuss what scatterometers are. Scatterometers are active remote sensing instrument which measures wind speeds, and it works in the microwave part of the spectrum. And though scatterometers gives wind speed, it measures wind speed indirectly. So how indirectly it measures? As we can see from this figure, that when the ocean is totally calm, then the microwave radiation which comes towards it, it will be totally reflected. The ocean surface will act like a mirror. But as the ocean starts to become rough, then scattering occurs from the ocean surface, and more rougher the ocean surface becomes, the higher will be the scattering from the ocean surface, and it will be detected by the scatterometer. And ocean surface winds, as a scatterometer measures the backscattering coefficient, so it depends on different factors like wind speed, wind direction, then sensor specifications as mentioned in the slide, and also different oceanic conditions. So this geophysical model function is an empirical function, and it is derived using different backscattered data from different satellite observations, and by comparing it with in situ and airborne and satellite data, as well as model and reanalysis products. And these are combined, and an empirical function is derived, which is then used to give the products to the users. Now coming to the motivation of my study, why we need scatterometer winds and why their evaluation is necessary. Ocean surface winds, as we know that our Earth is covered by 71% of our Earth is covered by oceans. So it is not possible to deploy in situ instruments in every part of the ocean. So due to the large gap in data sets, scatterometer data sets are quite useful in oceanic studies as well as air-sea interaction studies. Also, ocean surface winds can be used in numerical weather prediction model by the process of data assimilation to improve its initial condition and to give a better forecast. Now coming to OceanSat 3 specification, it is a Ku band scatterometer, and with two differently polarized beams which scans the ocean surface, and it has a pencil beams scatterometer which scans the ocean surface in a circular manner. And for this study, I have taken level 2B 25 kilometer resolution data, although OceanSat 12.5 kilometer data sets are also available. And generally, as it works in the microwave part of the spectrum, so it gives wind speeds in almost all weather conditions except when there is some heavy precipitation. Now, for comparing my data set, I have taken the data set for a period of 1 year and taken data from OmniBuoy data, which is available from INCOIS, then RamaBuoy data, ship data, which is available from IQuotes, and SK data. And for SK data, I have taken level 2 data of 25 kilometers spatial resolution, the same resolution as that of OceanSat 3. Now, for my study, these buoys which are available over the North Indian Ocean are from INCOIS. So this OmniBuoy, and those available over the South Indian Ocean are the RamaBuoy. During my study period, these 4 buoy data were only available for the Southern Indian Ocean. And we know that OceanSat 3 gives, or other scatterometers gives wind speed at 10 meter height, equivalent neutral winds at 10 meter height. So as ships or buoys measure wind speed at different heights, like buoys measure wind speed at height generally of 3 meter, but ships has variable heights. So those heights can go up to 32 meter. So those to collocate both observations, we need to convert the winds available at different heights to a height of 10 meter. And for that comparison, I have taken this formula, which gives equivalent neutral wind at 10 meter height. And for collocation, I have taken for buoy and ship data, I have taken if any buoy or ship data is available within a 25-kilometer radius as that of the Oceanset 3 measurement location and within 30 minutes temporal resolution, then I have taken it for collocation. And for SK data, as SK data wind vector cell is itself 25-kilometer resolution, so I have taken half the spatial half its resolution for collocation, and the temporal resolution I have kept the same as 30 minutes. Now here are some of my results. As it can be seen, the correlations are quite good, but for wind direction there is some negative bias. And however, for RMSC, and one point to remember is that Oceanset 3, the mission goals of Oceanset 3 is to give wind speed around within an error of 1.8 to 2 meter per second and wind direction errors within 20 degree. But here we can see that wind direction errors are more than 20 degree. And so to decode this, why we are getting higher errors in wind direction, we did one monthly statistics and we have found that the errors were higher during the monsoon period. It is due to the high wind speeds which are prominent during the monsoon period. And furthermore, these omnibuoys are available only in the northern Indian Ocean. So we can attribute this high errors to the monsoonal winds. Again, comparing Oceanset with Rama buoy, I have seen that RMSs were quite low for both wind speed and wind direction, and also the correlations were high. Again, comparing with that of ship winds, we can see that for wind direction, it is almost approximately within the mission goals. However, for wind speed, it was higher than that of the mission goals. So as from IQOTS, I have obtained my ship observations from IQOTS data. There for most of the data sets, height information was not available. So from previous studies, I have considered wherever height information was not available, from previous studies, I have considered that height as 32 meter. So probably because of that consideration, the errors in wind speeds were found to be higher. Now, however, I have taken the earlier 3 studies by comparing with in situ data. But in situ data, the way it measures the winds versus scatterometers, it is different. So there can be some pseudo biases. So if we compare scatterometer with scatterometer, then there is a probability that our collocation will be better. So by comparing, I have seen that wind speed and wind direction for Oceanset versus SCAT, it is within the mission goals. So I can conclude from the study that for most of the data sets, wind speeds and wind direction are within the mission goals. However, as I have stated earlier, for ships, wind speeds errors were higher, and it can be attributed due to the non-availability of height data. And for wind direction, it may be attributed to the high wind speeds which are prominent during the monsoon season. And for biases, negative bias in wind direction for all the observations were found except for omnibuoy, as I have stated earlier, and also for SCAT, while negative bias in wind speeds was found for omnibuoys. So I can conclude from this study that Oceanset 3 can be incorporated in NWP models for a better prediction of extreme weather events. However, as errors are present to some extent, we can give observation errors as we can correct the observation error in the model and do our assimilation studies. Thank you.
Thank you very much, Jana. That was very interesting, and I think it gets us well on the way to solving one of the world's biggest problems in terms of filling the observation gap over the oceans, because oceans drive a lot of our weather. And while this is focusing around India, I think it has much broader applications in other parts of the world. So thank you very much for doing this work and for sharing the results with us. It's very, very encouraging. Questions, hold on to them, write them down, keep them in your memory. We're moving on to the next speaker. Thank you. We'll come back to you if you have any questions. Final speaker for today, is Shibin Balakrishnan. Welcome you to the podium. Shibin is going to share with us the investigation of extreme heatwave spells over the Indian subcontinent during 2022, giving us a satellite perspective. So thank you very much. I look forward to your presentation.
Thank you, Chair. Very good evening. I've been tasked to give the last presentation of the day. I'll try to keep it as simple as possible. This is a part of my work which we are doing in collaboration with my colleagues. The heat waves over the North Indian subcontinent, specifically over the northern parts of the country. So as Dr. Ben rightly pointed out yesterday with respect to the EW for all. So this is a snippet from a WMO site where you can see the extreme weather events, be it a heat wave, be it the floods, be it the urban heat island affecting almost the world over areas, be it Pakistan, be it China, India, and affecting different areas of population and people with financial restrictions. This is a figure which I taken from website of NASA. So this gives actually there are two figures that is not clear here. This is the annual mean with respect to the long-term average from 1882 to 2023. So 2023 being the year with, I think this is very much known, with year with the maximum temperature on record for March and April month. Again, these are a few papers which I've just shared to just show the importance or the significance of heat waves and its impact world over. Studies over countries like Thailand breaking the heat wave records, over China or Vietnam, areas over the Indian subcontinent. So when we are talking about heat waves and we are being in a urban conglomerate like Delhi NCR, so I thought maybe we should even look into the land use land cover area. So this is from this is plotted from the NRIC data set. This is the 2005-6 LULC cover over Delhi NCR, where you can see the areas and with built up land and the crop land, and 2023 mostly covered with the built up land and your crop land and other areas getting you can say depleted. This is another very significant heat wave which struck the Indian subcontinent in 2015. So this is a data set which you can see where the extreme heat waves are seen spanning right from Pakistan, where we generally take it during the pre-monsoon period, which is the March, April, May for the Indian subcontinent. Heat waves spanning right from Pakistan all the way over the Indo-Gangetic plain till central parts of the country. Another thing which is also seen is the heat wave generating as a result of the wind movement. This is the heat wave generally over the region is attributed to the strong anticyclonic circulation which is present during these months. So these anticyclonic circulation push the northern and northwesterly winds majorly over the northern parts of the country. So as a result, you get continuous temperatures over this region, and this anticyclonic circulation also stops your moisture incursion from the Bay of Bengal, which is a major source of your reduction in temperatures during the pre-monsoon period. Looking into the scenarios of the country, so the figures on the, I think these two figures are not very particular, I'm sorry for that. The figures on the extreme right are the heat wave episodes during March, and the one right below the heat wave episodes over the country during April 2022. So when we say about heat wave is a very subjective term with respect to countries world over. When we look into India Meteorological Department has specific category for heat waves. So it is categorized with heat wave and severe heat wave. It is about when places, specifically the plain areas where the temperatures are above 40 degrees Celsius, and we have the departure of temperature. When we say departure, it is the deviation of the temperature from the climatological average of the last 30 years. When it is between 4.5 and 6 degrees, we categorize it as a heat wave, and when it is more than 6.5 degrees, we categorize it as a severe heat wave. Similar is the case with the extreme heat wave. It is when the temperature or the observed temperature is more than 47 degrees Celsius. This is the observed temperature for the month of April over the country. So you can see the northern parts of the region, specifically parts of Rajasthan, parts of Delhi, Uttar Pradesh and Madhya Pradesh having extreme temperatures during the month of April, and you are having high anomalies, which you can see from the temperature plot there. So this is taken up from the LST from MODIS. During the specific period, I have considered two heat wave episodes, one in April and one in May 2022. You can see the heat wave spells originating from Pakistan. Pakistan during the pre-monsoon season generally has the phenomenon called as a heat low, where areas like Abbottabad has the highest temperatures of around 55 degrees Celsius. So the northwestern winds support the movement of this heat wave getting transferred all the way to the Indo-Gangetic plain and affecting the Indian mainland. So you can see the temperature plots here showing the heat wave right from the 10th of April entering into the mainland, and till the April 17th, the heat wave persisted majorly over the parts of western Rajasthan and central parts of Madhya Pradesh, where temperatures were as high as around 45 to 50 degrees Celsius. This is the LST from WIRS data. So there are research which suggests the WIRS data, which can MODIS data which I showed previously, underestimating LST during the daytime. So I thought, why not I look into WIRS data where you can see temperatures on a much higher scale, much more closer to the observed temperatures over this particular period. So we looked into the observation, we looked into satellite. So I think NW is a part which we cannot avoid. So I thought I'll just plot the ERA 5 reanalysis data just to see how as the heat wave, how is the model able to pick up the heat wave signatures. So this is over the Indian mainland right from the 9th of April, where you can see the red spot, which is what we call as the state of Rajasthan, which is generally prone to heat waves, and that particular patch gradually shifting eastwards, where you can see the patch slowly developing over the Indo-Gangetic plain, which is all the way from Punjab till your parts of West Bengal. The heat wave persisting till 16th of April 2022. So you can see it here. And next case which I saw is this is our own INSAT 3D data, the LST data, which I've taken. This is for this next episode in May. So I thought we look into the LST variable which is seen and how is the heat wave progressing over the region. So this the shapefile which is overlaid here is the district map of Delhi. So you can see the LST or the high values of land surface temperature slowly progressing over the southwestern parts, where you have mostly predominantly industrial area having high temperatures of or high land surface temperatures. So this is again the next case on the 20th of May, where you see the southwestern parts of Delhi, which is mostly Gurgaon and other parts of Bahadurgarh, having high values of your land surface temperatures. As part of this, we are also looking into part of this research into few data of eco-stress data, which is very promising. This snippet is taken from the 5th May 2022 data, which is just before midnight. So you can see this is the eco-stress data, which is on board the ISS, the International Space Station. So this has a spatial resolution of around 70 meters. All these dark patches which you can see are predominantly the land areas, or you can call it as urban areas. And I think Delhi is kind of cut off here in the image. Delhi has a maximum signature there. Other areas being the grassland or the less populated areas. Thank you.
Thank you. Thank you very much, Shivian. I think that's a good one to end on. As I mentioned in my presentation, heat waves are increasing in terms of intensity and duration, and they're really affecting many parts of the world and particularly this region. And I think last year, 2023, and also this year, we've seen some significant events there, very troubling from a human health perspective. But there is a lot of good work being done to complement what you've just presented on the Global Heat Health Information Network set up by WMO and World Health Organization is very active in this space, sharing information. So if you're not tapped into that already, I would encourage that very much. And this is also a reminder about the UN Secretary General's call to action on heat health, which was announced a few months ago. And some of those statistics you put up earlier are very compelling. I'd be very interested to know if this work that you're doing, this is a sort of monitoring things that have happened in the past, if that could be turned into a predictive tool, I think that would be very, very, very powerful. So thank you very much to all the presenters. I did promise there'll be a bit of time for questions. I'm going to take 3 questions to any of 3 of the presenters. So we do have a little bit of time, but we're going to try and wrap this up in about 4 or 5 minutes. So can I ask anyone in the room if you have a question for any of the 3 presenters, and thank you again for those fabulous presentations to round off the day. Any questions, or has everyone run out of puff? Bodo, yes, sure. Here, can I hand you the mic just in case there's anyone online? Yes.
No worries. So maybe Shibin, just a question with that heat wave that came over, I think, May, and you pointed out particularly over Delhi, the areas most affected, and you mentioned it was the industrial area in the southwest. But what about all the residential area? I didn't see too much of a heat wave. There was all the colors, enhancement colors were yellow instead of red. How do you explain that?
When we are saying the yellow color, they are not something which are a very lesser side.
Okay.
Compared to that stats, the southwestern parts had temperatures around 48 degrees Celsius, but the inbuilt or the landlocked areas, if you say the residential areas, at temperatures as high as 45 degrees.
So very hot still. Okay, thank you.
I'm glad you asked that because I was thinking that as well. And I think what this actually speaks to is the colors that we use in our graphs, because mentally I was thinking, oh, that's not so hot. But I looked at the bottom and looked at the scale and I saw that sort of yellowy orange was in the mid-40s, and that is very, very hot. So thank you. Any other questions for other presenters or for, I saw that hand first, so I'll come back to you, Dr. Mitra. Thank you.
I have a question to Jana Bora. Yeah, you mentioned your validation for the ocean set 3. So maximum wind speed is up to 50 meters per second. So you mentioned that in the under heavy precipitation, you cannot observe it. But I think that kind of situation is not applicable for the tropical cyclone, especially strong surface wind. So I'm just wondering how can your ocean set can measure the kind of very windy condition of ocean?
Sir, for my study, I have taken the quality flag. So when I consider the flags, then actually during the cyclone time, I was doing the study. So most the high wind speed region, actually, if we consider the flags, then those part are removed actually. So if we do not consider, without considering the flags, then I was also doing the study again. So it was able to predict the, it was able to locate cyclone centers from maximum vorticity and minimum wind speed criteria, sir. So it was according to my study, sir.
Thank you. I'll come to Dr. Mitra, but before I do, can I ask if it's a question for Shavika? And if not, can someone come up with a question for Shavika so everyone has an opportunity to answer a question? But Dr. Mitra, if you could just identify who your question is directed to.
I think it's really a very good presentation. Excellent shown about how temperature variation plays a very, very important role, particularly the warm temperature. As Ben has mentioned that it was also be discussed in the WMN UN Council. Here my question is, your study shows that every city now creates a new kind of a work, that is the urban heat island. So town planner and all those whoever stakeholder, that has to be seen these kind of a work, so that they can decide whether urban heat island will make any impact on it. So do you have any, IMD has any planning for making all the cities UHI, that urban heat island plan for making with LST data and satellite data remote sensing?
Thank you, sir. Sir, actually, there are studies which are showing like bigger conglomerates like Delhi, Mumbai have extensive work on UHI. The smaller developing cities are actually facing the issue now because population explosion is taking place there and proper measures are not being addressed. So currently we are doing for different cities. We have started up with this LST data for different cities where we'll come up with a kind of a threshold for that cities based on the previous data. So that will kind of give a signature. How is it going to reflect from the values? Thank you. So I'm getting the look from the organisers that we're running out of time now. So we are going to wrap up, and let's just think, if you weren't able to ask your question today, think of it instead of as a conversation starter for tomorrow. So try and catch up with the presenters and start that conversation and be curious and learn more about what they're doing so they can share that and we can all learn together. As Alan Hong said, you know, we're all in this together and we should really be inspired to learn from each other and share experiences and build our knowledge collectively. So thank you. I will hand back to Dr. Singh to wrap up the evening. Thank you.
Thank you all for your active participation in today's session. Your insightful question and contribution really enriched the discussion. Then again, tomorrow we'll meet at 10:20. First, the weather briefing is there in both the hall number 6 and hall number 2. And then we have 5 papers tomorrow. And then 11:20 to 11:50, award for best poster presentation. After that, AMSU 15 announcement, and then a panel discussion is there. And after that, lunch 1 to 2. So thank you everyone for joining us.